Hello everyone, and welcome to the second day of Cloud-Native Geospatial event. My name is Sanket Verma, and I'm from all the way from New Delhi, India. Uh, I basically work as a community manager for ZAR. So I am sure you all must have been hearing about ZAR, COG, and all the other formats uh, in the past day. I would be so I do have like a talk and a tutorial later in the day, but this time I will be moderating a couple of lightning talk sessions, and it's so great to see everyone and all of you. So yeah, we got a couple of speakers in our list. So the first talk is by Bjorn Hartel, Flat Geobuff straight from the horse's mouth. So that seems like a interesting name to me. So Beyond Hartel's talk is basically a recorded presentation. So you would be seeing that on your screen just now.
Hi, and welcome to a lightning talk about FlatGeoBuff. My name is Björn, and I'm a Swedish programmer and have been into spatial stuff for a long time. A few years ago, I created FlatGeoBuff. So, what is FlatGeoBuff? It is a fast binary format for spatial data and attributes. It's lossless and with similar flexibility as GeoJSON. Initially, my idea was to make a format similar to the shapefile, but faster and without the limitations.
You can start the video.
So why did I make
Organizers, you can
FlatGeoBuff?
start the recorded video now.
I think it was initially due to that I wanted to know how Mapbox vector tiles work. As you might know, they're based on something called protobuf, which is from Google. I like to think about that thing as a kind of XML, but for binary. I was also triggered by that the best format out there for some use cases was still the shapefile. Then I found a project called FlatBuffers, which is also from Google, and it's like protobuf but faster. I also found Flatbush, a tiny and nice implementation of the R3 spatial index by Vladimir Agafonkin, who you might know as the creator of Leaflet. So Flatbush helped me understand how R-trees work, which is something I had wanted to learn about for some time. And to create a format to beat the shapefile, you really need an efficient spatial index to support making spatial filtered queries against the data. So around September 2018, I made the initial commits to implement what became FlatGeoBuff. It went through several iterations, also at the spec level, and finally in January 2020 I was happy enough with it to consider it more or less done. I implemented support in GDAL, and it was released in GDAL 3.1 in May 2020. That was an important stepping stone for FlatGeoBuff to make it available, for example, in QGIS. FlatGeoBuff is also available as a plugin in GeoServer, so you can use it as a data source or as a WFS output format. So I haven't mentioned Cloud-Native. Well, that is because I didn't consider Cloud-Native when I made FlatGeoBuff, but it turns out it's pretty much Cloud-Native, perhaps by accident. A design goal of the final spec was to make the format I/O efficient. That was to support streaming and piping, and that also makes it works well in Cloud-Native. Okay, so a quick demonstration of an example that is also on the FlatGeoBuff webpage. And so what happens here when I panorate the map is that the browser makes range requests just for the data within the bounding box. Okay, so to sum up the use cases that I have in mind for flat GeoBuff is to use it as a drop-in replacement for the shapefile, JSON, or GML. But you could also use it as a system-to-system communication protocol, or as an output format for WFS or OGC API.
Yeah. Hello. So seems like the video played well, and if there are any questions for Bjorn, he is in the he can see the questions in the chat, questions chat. So I don't really see any questions over here. So yeah, we can take that over to the Gitter. So we have our next speaker with us, Brandon Liu. Hello, Brandon. Uh, I can't hear you.
Hello?
Yeah, yeah.
Okay,
Perfect.
it's working now. Sound good?
Yeah. Hello, how
Awesome.
are you?
Doing well.
Yeah. So Brandon is from Protomaps LLC, and he would be talking about no two clouds are alike. So take it away, Brandon.
Are you able to see my screen share?
Yes, I can.
Okay, awesome. Hey everyone, I'm Brandon. I'm going to be talking about cloud storage today. For context, I'm working on a system called Protomaps. It's an end-to-end system for both packaging and styling maps using only static files. That includes geodata, that includes tile formats, that includes rendering. And it is cloud native from the ground up. It has a tile format called PM tiles that's being developed alongside it. And it's made of mostly open source components that are on GitHub. This is also in the context of a new product I'm starting to roll out called Mantle. It's a vector-based map product on your own cloud, built on Lambda or Cloudflare workers. And an important part of this is that it is vendor neutral. So it works the same way on Amazon or on Cloudflare and hopefully other vendors in the future. So a bit more about PM tiles. The idea behind it is kind of like cloud optimized MB tiles, where MB tiles are a SQLite container of ZXY tiles. These are agnostic to the actual tile content. They can be vector, they can be raster, they can be scientific data. It has an open source spec on GitHub. It has implementations right now for Python, for Go, as well as direct to the browser from storage. With Leaflet, I have a plugin for Map Libre, and I'm working on CP output. And this is similar to other projects at this, there's other talks at this conference, like Kotar, ComTiles, TileBase. Same idea, which is a range-based indexed sort of archive container for tiles. So PM tiles is built on cloud native principles, HTTP 206, spatial indexing, and most importantly, commodity cloud storage. So what about cloud storage? I'm going to tell you what I learned from real world deployment of vector PM tiles on different clouds, not just S3. It also applies to other formats like flat GeoBuff, like COGS, like Copix. The challenge areas I'm going to briefly go over are around performance, security, and freshness. Performance, there's this quote, which is, don't underestimate the bandwidth of a station wagon full of tapes or shape files going down the highway. So that's one definition of performance, which is bandwidth. That concept of performance is usually not what we're talking about with cloud optimized. Optimized means low latency, not high bandwidth. Low latency enables Slippy maps, it enables interactive queries, it enables grabbing a piece of the data from the full data set. And one really important part of latency is HTTP version 2. Now that enables multiplexing where you can have many of these requests in parallel. But most vendors actually don't support HTTP version 2 on their base storage product. They usually reserve that as part of their CDN. Of the big ones, I think Google Cloud is the only one that has HTTP version 2 as a default. byte serving plus compression. For vector formats, they don't have a domain-specific compression built in like PNGs or JPEGs. And partial content is incompatible with the default content encoding, sort of gzipping of the web. Browsers don't support a general purpose decompression API yet. And multi-part ranges generally are not supported on cloud storage. Security. Serving files direct from storage to the browser is good. That's a really compelling use case, but that's cross-origin usually. And of the major cloud providers, not all of them allow multiple origins to be defined for cores. S3 allows it. Other storage providers only allow one origin or just the wildcard. And if you have the wildcard, there's this problem which I call the Napster or Mapster challenge, which is that if you have range requests to download a part of the file, well, your users can just download the whole file. It's almost like Napster for maps. You can just download these data sets with no DRM, and that risks these runaway costs. If you're paying per gigabyte of egress, then anyone can just download the entire data set. It might cost $1 per user, but that adds up pretty quickly. There's no way to limit on these storage providers, only 206 range requests. And I think requester pays is a good solution, but right now that's very vendor specific. Freshness. Even though cloud optimized formats are read optimized, the world is changing. The data does update. The convention is to just replace the whole file on cloud storage. And storage providers, they all implement e-tags. There is one e-tag string corresponding to each version of the file. And implementations and caches should use these e-tags to find out when a file is stale, to know that there's new data available. So specs can take advantage of this. Conclusions, performance, security, freshness should influence the spec and implementation of cloud optimized geodata. Cloud storage is widely varying in capabilities. It's competitive, it's evolving, and don't build for S3 only. Try to make your system work on other cloud providers. That's all I have. Happy to talk about this on Gitter. You can find me on Twitter, GitHub, or email. Thanks.
All right, thank you, Brandon. And Brandon would be around here on the Gitter for the chat and questions. So we have another speaker with us, Matthias Mohor, and they're from WWE Münster, and they would be talking about OpenEO. Hey, Matthias.
Hey, yeah, that came a bit quicker than expected, but anyway.
Yeah.
Which screen is shared now? Again, it doesn't show it.
I can see your screen.
Oh, that's good. And also the slides?
Yeah, but they're not in the presenter mode now. But they're
oh, there. Yeah. Okay, great.
Yeah.
So I will talk about OpenEO, which is basically cloud-native geoprocessing. So not about a file format here, but about an API and process descriptions, basically. I'm working for the University of Münster and with another couple of companies in the European Union. We're developing this since 2017. So why did we do OpenEO? Well, basically you have a number of programming languages and clients like R and Python that all want to do EO processing. And there are a number of cloud providers that do that, like Google Earth Engine and Sentinel Hub and others. But they all have their own API. So what we have right now is this mixture of things, and that doesn't really work out for people because they need to learn a lot. So we defined, or our vision was to have an API that sits in between and translates all the requests and focus on what the user needs and what he wants to achieve, and not how to do it, right? Not to learn a specific API for each of the providers, wherever the data set is that he needs. And of course, I'm working for a university, so it's always good to have reproducible results so that you can check whether what you get out from your cloud environment is actually what is the right result, and it should also be, in this case, interoperable, of course. So what is it? Well, it is a language basically for geospatial processing, so an API and a set of processes that you can run, basically an extensible set of processes. It is cloud-based, it is open source and community-driven. So anyone can contribute to that, can propose extensions, can propose new processes, and it's all centered around data cubes, so that the data access is really easy, and you don't need to fiddle around with like files or any specifics here. What is it not? Well, it's not specifically another cloud provider. I mean, there are implementations out there, of course, for example, Open Your Platform, but it's not like a single one, right? Everyone can implement this API and processes on their existing stack of tools that they have. It's also not another geoprocessing software, of course, and it's not using the traditional GS style where you have files and tiles and where you need to figure out how to combine them. It also handles time natively. So the API is covering a couple of things like discovery for the EEO data for the processes. It also covers authentication via OpenID Connect. You can, with the predefined processes that we have, also define new, more complex user-defined processes and store them and reuse them again in another user-defined process. You can upload and download your files, of course. You can process the data that you've selected either synchronously or as larger batch jobs. And you can do on-demand processing via web service. So if you have a web map and a workflow that you want to run, you can do that on demand so that you can see or the data is just computed on the fly, basically. We have a set of predefined processes, I think roughly 150 at the moment, mostly centered around EO processing, but it's extensible. So it is basically possible to also go to other domains here and extend it. You can define user-defined processes based on the predefined processes and other user-defined processes. And then there is a concept of user-defined functions right now implemented in Python and R. That means you can upload custom code that you have previously written in Python and R and make it part of your processing chain. We have clients implemented in JavaScript and TypeScript, which power the web editor as well. So we have a browser-based client. We have Python and R as very common programming languages in the EO world. Both integrate into Jupyter as well, so you can see nice UI widgets coming out of them if you run the clients, and also works well with RStudio and R Markdown. We have a Vue.js client, but that's unmaintained right now, but we'll pick that up again in the future. So this is basically then an accept of the code that you could run. So it's really just you do all the processing on the write all the code on the client side in a language that you know, similar to how you have done it before. It's really well integrated here in Python, for example, and then it's just translated into a process that is transmitted to the backend and can be run there. The same looks very similar in R, so it's very, very easy to get used to that, I think. And if you don't want to program, you can also use the web tool, the web editor here, which is a nice UI component which covers everything, including map, showing things on the map, etc. There are a couple of backend implementations which are all open source, which you can reuse and set up. For example, for GeoPySpark, GeoTrellis, We have multiple instances running on Open Data Cube, which proxy that interface, or GraphJS, Rasterman, WCPS is also interfaced. And we have prototype implementations also for Google Earth Engine. So you can basically run anything on the Google Earth Engine as well, using our processing environment. And Sentinel Hub is also in the making. One thing that I'm working on and is basically a successor or thing that we worked after OpenEO was funded is OpenEO Platform, a federation of multiple of these backend implementations. So you can also go to that, and it proxies a number of implementations out there. So you can have everything in one place. Yeah, that's it for me. Thank you for listening. I'm in the chat for questions. I can't hear you, Sanket.
Yeah. Thanks, Matthias, for delivering a talk. Hello. Hello. Am I audible? Hello.
Oh, yes.
Yeah.
Is it okay?
Hi, Sylvain. Can you hear me?
Hi, thank you.
We hear you.
So I am Sylvain Brunato from CS Group. At CS Group, we work on geospatial data, and I am very happy to talk about EUDAG in this fantastic conference. Sorry. Yes, EUDAG is for Earth Observation Data Access Gateway. Came from the observation that there are lots of different Earth observation data providers like USGS or the Copernicus DIAS and many more. And for each of them, provides different APIs. For data discovery, we can have, for instance, more or less customized OpenSearch, CSW, or Stack that is more and more adopted as the new standard for search APIs. We have different interfaces for authentication using a token, OAuth, or OpenID. And for data access, we can also have HTTP download, object storage, or direct file access. EUDAG provides a unified API for search, authenticate, data access, and also to metadata using OGC OpenSearch for Earth observation extension as reference. For search purpose, EUDAG can be seen as a client for Stack API, Static Stack, and many more other protocols. EUDAG has a Python API and command line interface that are as simple as possible, like EUDAG search and EUDAG download. You can filter your searches using standard spatial or temporal parameters with many formats supported for geometry, like well-known text, bounding box, shapely geometry, or even a location name from a shapefile entry, like a country. You can also use any other criteria supported by the providers, like cloud cover percentage, orbit number, online or offline data, file ID, etc. You can also list all providers or only the ones for a given product type, list all the product types or only the ones for a given provider. You can apply crunches to your search results, which are advanced local filtering, and also order and download offline data and do many more advanced stuff. Using the command line interface, you can run nearly the same commands as in Python, and also run EODAG in server mode. For providers that do not have a stack interface, this feature can be very useful. EODAG will act as a stack API proxy to the non-stack provider, and the user will transparently benefit from all the stack ecosystem, like the stack browser for his non-stack provider data. Collections will be mapped to available product types, and the catalog tree will be generated using dates, countries, or cloud cover percentage ranges. EODAG is built around plugins and keeps being extended to handle new APIs and have new capabilities. You can install EODAG Cube for having direct access to product data through Xray. And if you search on a stack provider, you can get data from an item asset pointing to a cog, or you can also only stream to a reprojected subset of your choice. This is done internally using REO Xray. You can also use the same method to get data from a downloaded netcdf or JPEG 2000 inside a Sentinel Safe product. Other EODAG plugins can provide you access to specific data providers, like EODAG Sentinel Sat for Copernicus Access Hub. EODAG has also a JupyterLab extension, providing you a simple and useful user interface. Located in the notebook side panel, it will help you search for data, withdrawing your area of interest, selecting dates, product types, cloud cover, or other criteria of your choice. Search results are then graphically displayed with quick looks and metadata. For downloading using EODAG, the extension will automatically generate a code snippet and insert it in the notebook. EODAG is open source, so feel free to use it or contribute on GitHub. You can post there your bugs or feature requests. You will also find on Read the Docs a well-furnished online documentation with lots of examples and detailed notebooks. Thank you.
Yeah, thank you, Sylvan. So before we start the next talk, we have some time for questions. So if there are any questions for the speakers who have already delivered their talk, please post them into the chat, and we will be more than happy to take it away. Also, all of the speakers are on the Getter channel. So if you want, you can also ask questions over there. Yeah, so seems like the next talk is by Joe Hammond, which is like one of the recorded talks. And
Thank you.
Thank you, Sylvan, for delivering your talk. It was a pleasure having you.
Thank you.
All right. Hello, everyone. My name is Joe Hammond, and I'm going to be giving a quick talk on XPublish, a Python package for serving Xray datasets. So, quick introduction to Xray. Xray is a Python package that provides a data model and a toolkit that works with multidimensional labeled arrays and datasets. So the data model itself is built on netcdf, so you have multidimensional variables, data cubes like this one that are three-dimensional, but it's arbitrary dimension. Arbitrary dimensions are supported. It has coordinates, so latitude and longitude in this case are coordinates. It has dimensions, x and y and t are the dimensions of the example data set here. And then it has arbitrary metadata, things like units and variable descriptions. And on top of this data model is built a toolkit that supports a wide range of data analysis and data processing tasks. So things like arithmetic, resampling and group by. It does parallel processing via the Dask library. And then it has a wide range of backends for reading and writing X-ray data sets. Second project I'm going to introduce here is ZAR. So ZAR is an open source format for the storage of chunked, compressed, multidimensional arrays. The arrays are split into chunks, and then they're compressed with a wide variety of codecs. So BLOSC and zlib are two of the popular ones. The ZAR is in many ways just a specification for a storage format, although there's the Python implementation is the most commonly used one. There are others. There's JavaScript implementations, Julia, C++, and Rust. On the back end, ZAR stores are really just key value interfaces. So you can use a directory, a file system directory. You can use a zip file. Cloud Object Store is supported, databases, etc. This is what a ZAR group looks like. So a group is made up of multiple arrays or one or more arrays. And then the metadata for these groups and for the arrays is stored in JSON. So the Z adders, the Z array, or the Z group objects. And then the chunks themselves are binary blobs that are arranged based on their layout in the overall in-dimensional array. And so xpublish comes in and provides a tool for serving data over the internet. And this is actually not particularly new. We've been reading remote data with X-ray for quite a while. So there's a tool called OpenDAP. It's a protocol for serving NetCDF-like data over the internet. So here's an example reading a precipitation data set using OpenDAP and X-ray, and you point at an HTTP endpoint and you get back a data set. In recent years, we've also done this with FSSpec. So FSSpec's a library for accessing data over a bunch of different storage protocols. So you can use X-ray and FSSpec together to do this, and this actually doesn't require OpenDAP, and it's you can just point at an HDF5 file directly. And then finally, there's ZAR. So ZAR supports Cloud Object Store, and the API can read and write directly to the object store, and so X-ray supports that as well. So we built xpublish a couple of years ago with the idea that yes, we can read data via the ZAR API in Object Store, but we could also serve ZAR data from an X-ray data set. So it's kind of flipping that read API around. And so an xpublish application is made up of X-ray as the data model, a fast API front end. And so fast API is a Python framework for building web APIs. And then when combined with Dask on the back end, we get a lazy parallel execution framework for serving chunks of ZAR data to client applications. So how this works in practice is you have an X-ray data set, and that X-ray data set can be served with the REST accessor and some arguments. And then on the client side, you can point to that same that host and that port, and you can open this data set as an X-ray data set using ZAR. So some key points here. The first is that X-ray or xpublish supports publishing X-ray data sets over HTTP. We use ZAR as the primary router, but additional routers can be added, and I'll talk about that in a second. One of the coolest things about this is this allows for the serving of on-demand data. So, level 3, level 4 data could be computed on the fly rather than stored as a separate copy. And then we're using this at CarbonPlan as essentially as a tile server. We're starting to explore using xpublish to serve data in ZAR format to our web front ends. So Kate is giving a talk later today on how this works. So yeah, I mentioned before that there's we have a plugin system for routers, and so the ZAR router is the one that we use mostly now, but we can add additional ones, and there's a pull request open for the XYZ router already. We're looking at multi-scale arrays, basically image pyramids for multidimensional data. And so combining X-Ray's data tree package, which is just an early stage of development, with the multi-scale spec is kind of a frontier. So you can try XPublish for yourself. You can pip or conda install it. You can also contribute to the package. It's an open source package. Would love to see more contributors in this space. And if this tech stack or application set is interesting to you, please get in touch. My contact information is here. Great. Thanks for listening.
All right. So that was a talk from Joe Hammond. Seems like it was a recorded talk. So if you have any questions, you can post them on the GitHub. Next up, we have Fabian with us. Yeah. Hello, Fabian.
Hello, can you hear me?
Yeah.
Awesome.
And I can see your screen too.
That's awesome too. So just a second, start the show. All right. I'll be talking about Geotiff.js. So Geotiff.js is, I think I've already talked about it in the past on an event like this. So it is nothing new, and we already heard about it in a couple of other talks. This is really cool to see that so many people and so many projects are already using it. Quickly about us. I'm working for a small Austrian company called UX. We supply data and services for the European Space Agency and other companies. Please check out our homepage. We have cool stuff and a blog. Okay, what is Geotiff.js? So first off, Geotiff.js is a pure JavaScript open source library that supports reading of tagged image file formats data, so TIFFs. The geo is basically as a bonus. It aims to be feature complete, so that every TIFF image that you throw at it can be read, and you can extract data from it. And it also allows you, for example, if your TIFF has very esoteric compression or whatever, that you can extend the GeoTIFF's functionality by adding a decoder, for example, a plugin, so that you can actually read your data. It is also intended to be easily used, even if there is a lot of complexity behind it. But the idea is that you just give it a URL, open it, get the image, read the raster, and be done with it. So the complexity is basically hidden within the library, and you should not see it when you're dealing with your day-to-day use cases. So Geotiff.js actually predates the definition of the cloud-optimized Geotiff, but it actually benefits a lot from it. So here we have a TIFF file as you can find it in the wild. So you start with the header on the left, and then you have this linked list of image file descriptors, which themselves point to the data. So this can be quite inefficient because you have to jump around in the file back and forth to read your data. But with cloud-optimized GeoTIFFs, we know that these IFDs and the tile data are structured something like this. And Geotiff.js makes use of it because it requests data in blocks. So it starts with the block 0, and whatever is already requested doesn't need to be re-requested anymore. So in this example, we would get all the image file descriptors in just one go. And then we would use a second block request for the rest of the data. Whenever you request so much data that it spans across multiple blocks, those blocks are joined to a single request, so we can even save on requests there as well. A little bit on the history of Geotiff.js. The initial commit was October 2015, so this was the ideal timing because the web standards have evolved to a level that it can actually be used for a thing like this. And 1 year later, there was this little piece of this on the GDAL webpage. This is the first mention of cloud optimized geotiff that I can find. And this is where really things took off, and the interest in TIFFs reinvigorated, and cloud optimized geotiffs were suddenly everywhere, and geotiff was there to exploit it, which was really cool. For now, I have to say it's really easy without too much work on the user part to actually use geotiff.js. So for example, OpenLayers has it completely integrated since version 6.7, which was a really cool experience. So first we had to really work to get the rendering to work, especially for complex examples, but now it's easy. You just use the library capabilities and it's there. For Leaflet, it's very similar. There's also plugins to use it. Here are some examples. So Cog Explorer was actually predating the geotiff support in OpenLayers. So this is an example where we really had to fiddle with the rendering and everything to make it actually work. But it still works, and I implore you to use it and try it out with your own TIFFs and see if you can make a nice visualization. Then the circle came full, so my work came full circle. So I had to write a small app to visualize digital elevation models. And this is what I came up with. And the integration with the map, I'm using again OpenLayers here, was quite easy, and it was really fun to work with and experiment with what we can actually do with this actually kind of boring data. Right. I also like to mention our product UX Cloudless. So this is a cloudless mosaic of comprised of Sentinel scenes. So we cloudless, most cloudless pixel for every point on the Earth, and then we make a huge mosaic and we provide it. We're using real data as well, so you have the UN16 data, not just single RGB, and we also supply the near-infrared bands. You can see that cloudless.exit or S2Maps EU, and we're also using geotiff.js to make some nice visualizations. So for example, for each pixel that you can see the originating Sentinel scene, where it comes from. Yeah, here's some links for the project and for related projects. And I'd like to thank you, and I'm available for questions.
All right. Thank you, Fabian, for delivering the talk. We have like I would say 15 minutes of time for questions. So if all the panelists who are basically present here, if you have questions for each other, you can go ahead. And yeah, if attendees you have any questions, you can post them into the chat, and I would take it away. Just to reiterate, like some questions I see on the Gitter. Matthias, can you hear us?
Yeah, but I've spoken already.
Yeah, I have a question I saw on the Gitter. So okay. Would you like to reiterate the answer over here?
Sure. Was it the question about the GEE?
Yeah. So what prompted the creation of OpenEU?
Yeah, it was meant to standardize the processing interfaces, right? So that not everyone needs to have its own API interface, and you, as a user, need to learn it for each different provider that is out there. And it is not meant to be a competitor of Google Earth Engine itself. Like, of course, an implementation of OpenEO, which is a specification, could say they are competitors or meant to be a European alternative of Google Earth Engine, but that was not the intention of the specification, basically.
Okay, all right, thank you. So let's see. I don't see any questions in the chat as of now, and not on the Gitter. So yeah, I'm just trying to fill in the time over here, because the next session doesn't start until the top of the hour. So if panelists if speakers you have any questions for other speakers other than yourself, then you can also ask them. All right, seems like no questions as of now. So Fabian, how are you liking the event? How the event has been going for you?
Really great. Yesterday there were a lot of cool tasks. I hope that there will be some recordings for the past
Yeah, there will be.
talks, because I missed some in Europe.
Yeah, there will be,
Not.
and yeah, this basically calls up for a special announcement. If you check Chris's Twitter, he has tweeted basically a link for the Google Drive in which there are a couple of presentations from the previous day, and I think the rest of the presentations would be coming up very soon, like maybe in a day or two. So yeah, all of the recorded presentations, all the live presentations, both of them will be available on the Google Drive. So yeah, you can look out for them.
That's great.
All right, so I think let's end the session over here. Thank you, Fabian, again for joining us, and it was a pleasure to have you.
Thank you.
Hello.
Hello, pleased to be here.
Yeah, how are you doing?
Perfect, fine. And you?
I'm good. It's like afternoon in India.
No, here it's like it's still the morning, but I think that in the US it's like the real morning. It's like 6 o'clock, something like this.
Yeah.
6 a.m. So it's a bit soon. Maybe maybe I think the panel is mostly composed of European people.
Yeah.
I don't know.
This part of this part of the conference is basically for the European and also for the Australian folks, like the mostly Asian folks, like yeah. So yeah, for the attendees, we have, correct me if I'm wrong, Basil.
Yeah. So I'm
Yeah.
extremely pleased to be here to be able to speak a bit about how we work at NetCarbon, what we have designed, and how all this work of the community is like helping us to develop and to improve some of our algorithm. I have some slides, and it's going to be easier.
Yeah. And Basil will be talking about how to turn satellite data to insights at scale. So probably we'll be talking about the satellite data and scalability, like both of these important things at the same time. And it's a tutorial. It's an hour-long tutorial, and we are starting like a few minutes earlier. So yeah, Basil, you would have like 5 to 6 minutes like extra, so you can basically extend and explain more about your talk. So without further ado, Basil, take it away.
Thank you very much. So exactly, we will speak a bit about how to turn satellite data at scale. Mostly the tutorial was based on the land surface temperature, but we have changed some different features in order to compute some different indexes. What we are going to speak during this tutorial is mainly based on like the three main part of a UTL, which is extract, transform, and load. And if we have some times, we will speak a bit about how to build the pipeline on top of it, because we will need obviously like some different packages, some different function to run those different algorithms. But at the end, we also need like an orchestrator in order to be able to compute the pipeline like at each at some different time, like every day, every 2 days, every month, whatever. So if you have some time, we will speak a bit about this part also. Before that, I want to very quickly introduce NetCarbon. So NetCarbon is a pretty young startup. We are working on satellite data in order to monitor carbon. Here, the main idea is to say, okay, if we want to improve carbon, if we want to improve carbon sequestration, but also if we want to reduce CO2 emission, which is another part, we have to measure it. So that's the main topic. And the main possibilities which are offered by satellite data is to be able to measure something at scale and like in an homogeneous way. So that's why we are using mostly satellite data. Maybe I can start the tutorial. I don't know if I can wait a bit, like 5 minutes more. Can I start? Okay. So before I will very quickly explain who am I. So I'm Basil Goussa. I'm the CTO and the co-founder of NetCarbon. And as I said just before, the main objective of NetCarbon is to monitor carbon. I work in the Earth observation domain on big data and AI, mostly for different companies. And we are part of the Pangeo community, not the Pangeo community in Europe. The main idea, and if anyone want to join and want to keep some news on Pangeo, we are here, and we will be pleased to explain a bit what is Pangeo. And I already saw a lot of people who are part of Pangeo, mainly in the US. So Pangeo is an ecosystem that is helping us to build some like big data geospatial tools and platform and pipeline. We are using a lot, obviously, Stack within NetCarbon, because it's allowing us to be able to monitor and to catch some different type of data. and to use like different satellites, and at the end to be able to do some fusion between those type of satellites. We won another challenge, which is the Copernicus Master. It's a challenge which was led by Planet, it's definitely allowing us to use some different type of data, because we are now using PlanetScope and L3 data, which is a specific type of data without clouds, for example, and also to have a bit more of ads on NetCarbon. So this tutorial will be based on like 4 different parts, obviously the major part of the tutorial will be focusing on the Jupyter Notebook. But before to dive in the Jupyter Notebook, I would like to just introduce very quickly NetCarbon. So as we all know, we have to fight against climate change, and we all know that the temperature of the Earth will increase by the end of the century. So we definitely we have to act. We have to reduce CO2 emission, obviously, and we have to increase carbon sequestration. So to be a bit more clear, carbon sequestration is the power of the soil, the power of the plants to store CO2, mainly based on photosynthesis. But at the same time, to reduce and increase carbon sequestration and to reduce CO2 emission, we need to be able to monitor it. We will need to be able to see trends to improve carbon sequestration based on facts, based on measurement. So that's what we are working on at NetCarbon. We are working on a way to measure CO2 sequestration with satellite data. So all these possibilities is directly linked to satellite imagery. So we are using different type of satellites. As I said, we are using Sentinel-2 Copernicus data, but also Planet imagery. And this satellite is allowing us to retrieve some different indicators that we have correlated with different measurements that is allowing us to be able at the end to measure the CO2 flux. That's the first part. And the second part, which is also extremely important, is to be able to detect practices, to see like, okay, if there is a difference in CO2 emission, CO2 sequestration, it's directly linked to these practices on agricultural land. Okay, so that was what we are doing in NetCarbon, but what we need in order to implement our vision, in order to implement a way to measure carbon sequestration, we obviously need to retrieve insight at scale. So here it's a little schema that we have done at NetCarbon, and that we are going to explain during this tutorial, and explain how it's possible now, based on different type of technologies, to build some indicator at scale. So the first step, obviously, is to extract some different satellite data. And as I said before, one type of extremely important package libraries and catalog is Stack. So why it's important for us? It's because it's allowing us to be able to connect to those different type of data without the need to rewrite all the code each time, to have just one API which is able to connect to different type of satellite data. And I was extremely happy to see that EODAG is directly adding X-array at the X-array, like EODAG cube. It could be very interesting for us to implement EODAG here in order to have a different type of satellite data provider more easily than adding by ourselves some different API. So that's the first step, the extraction. And after, I will speak a bit about the transformation, how we can compute some different indexes based on Pangeo, obviously like those packages like X-array, Dask, And mostly one thing that we are extremely, one thing that we find extremely important, it's and a really game changer for us, it's Coiled. And I will dive a bit on Coiled and what is Coiled. Mainly Coiled is allowing us to deploy our code. So to deploy our directly within the notebook, you can run all your code within the cloud based on Coiled, and Coiled will build all the cluster that you need to compute the code. So it's an extremely efficient way to scale your processing without the need to have like the infrastructure monitoring, and without the need to go out of your notebook. Obviously, we need some different packages like the Flux, but also the vegetation, the cloud mask, etc., etc. And at the end of this this session, we will dive a bit on how to load the data after, and what are the main challenges that we are confronted at NetCarbon to load this data. Today, we are using some different database, and one of the database that we are using is Google BigQuery. It is allowing us to push some different indicator within the cloud and to retrieve and to compute some different indexes on top of our database. And the last part that we are not going to speak during this session is some API that you can build on top of your database, obviously. As I said before, the last part will, if we have some time, we'll focus on the pipeline. So here you have the first step, which is the extraction. You have the second step, which is the transformation, and the last one, which is how to load the data. But if you can't do it like at the right pace, and if you can't monitor the output of your data, you will miss something. So here it's like a way to orchestrate everything and to have something which is more robust. Okay, and now we can dive directly in the Jupyter Notebook. Can you see the screen? Okay. So here we are directly in one notebook, which is the OGC notebook for this this session, and I will explain exactly what all these different functions are doing, and we will dive directly on it. So the first function here, the first packages that I have to import is Coiled. So as I said, Coiled is a way to compute your compute your code directly at scale within the cloud. So it's managing the creation of a cluster, a Dask cluster, directly. After we are using NetCarbon Prefect, which is the way to compute your web workflow in order to like design what is the task, what is the flow, the case, the parameters, etc., to be able at the end to have something which can really like be an extract, transform a lot, a real ETL, and which will be able to run every day, every 2 days, every month, etc., etc. And the last one, which is just for visualization topic, I'm importing KeyPlayerGL, which is some libraries, which is helping anyone to see geospatial data and to explore this data. So this is the 3 packages that I'm importing, but obviously there is a lot more packages. For the purpose of this talk, I have I have merged some different function directly within some different function, and I will dive a bit on it, but very, very quickly. The main objective is not to speak about something that was already explained, so X-array and all these components. So we have like 6 functions, 6 packages. Sorry. The first one is extract API. So here it's something that is like very internal. Is to extract a location. So you can obviously, like here, replace by GeoPandas and read file to just retrieve the location. So it's here just to retrieve the location, and we have a specific ID for this location, which is easier for us to run some different pipeline. You have the extract Sentinel-2. So the extract Sentinel-2 is mainly composed of the SAT search, sorry. So here you have the SAT search Sentinel-2 function. So you have the bounding box and the dates. And based on this, you just have to use the URL of Earth search, which is the endpoint of the catalog, a stack catalog. You have the collection Sentinel-2 L2 cogs, and you can search for several items based on your different parameters. So here the collection, obviously, to retrieve the Sentinel-2 in cogs format, the dates, the date time, which is put here, the bounding box, and here. And you have here some different very simple function. So to the geometry to bounding box, the idea is to put a geometry and to retrieve a bounding box. And the one which is important is this function, create data cube. So I think we can, maybe we will try in the future the EODAG cube in order to create data cube more easily. Today we are using those 2 functions. Here it's important to see that it's extremely easy today to build a data cube based on different satellite data, thanks to the work of all these communities, sorry. Because I'm not using a lot of packages. As I said, for search Sentinel-2, we are using just SAT search in order to search within the catalog, the stack catalog. And after, an awesome packages, extremely helpful to design very quickly some, to compute and to imagine very quickly some new insights, to compute very easily some time series is the stack packages. So what is stack? So it's extremely simple. The output of SAT search is based on the stack. So you will have a stack item list, and based on stack, it's building a data cube. So you will have several items, and you will have at the end one data cube with all the different items. And that's it. That's the function that we are using. I'm directly moving to the rest of the notebook, and we will dive a bit more within these different packages when we will need them. So let's retrieve the location. And now let's use the packages that we have shown just before. Okay. So what is very interesting here is that you can retrieve so extremely easily directly a data cube with the different parameter that you have put at the beginning. So let's check here. For example, we have the input location just here, which is Libourne. It's near Bordeaux in France. We have extract the Sentinel-2 data based on these packages, and you will have your data cube with all the different timestamp with respect to the location that you have. You have the same with all the different bands and all the different timestamp. So here it's the end of 2019 until 2021. So I have my data cube. It's not a huge one, it's 8 GB. And after, I can do just some filtering on the data cube. Here I'm filtering by cloud cover. It's, I don't know, it's, yeah, 30. So I will keep just value with the cloud cover below 30. So I can check it now if it's here. So you can see that we have just now within our data cube, we have just elements, items with a cloud cover below 30. So obviously all this processing is not done directly because you are working with the metadata, and it's why it's not very like it's not time consuming. It's just like building a graph, a computation graph. And after, we can directly move to the interesting part. So here we have mainly 3 different functions, and those 3 different functions are allowing us to build directly some processing at scale. So the first one is like the main idea of this talk is to explain how it's possible to do some processing at scale today based on Cold. So what we are using here, it's the packages that I have imported at the beginning of the session, is Cold, and I am using the cluster function. I'm saying that I want for this session, I want a cluster with 6 workers with 8 GB of memory based on software NetCarbon AWS and the name NetCarbon. And after, so just to maybe spend 1 minute more within this different input. So here obviously is the number of workers, here the memory. Here it's not the tricky one, but one of the most important is just when you initiate the cluster at the beginning, when you go to, I think you can go to cold. Okay, so when you go to cold, you can directly create some different software environments, and these software environments are based on different conda packages and pip packages. So it's extremely easy to start with. For example, here you have import cold. Cold creates software environments, the name, the channel, sorry, and you just have to say, okay, conda forge default and the dependencies. So here I'm using the NetCarbon AWS packages. So these packages is mainly composed of Dask, Xarray, and Rio Xarray. The name of the cluster is NetCarbon. So when you have built your cluster, so what is important is to connect your cluster with Dask, because you want to do your computation not within your computer, but you want to do your computation within the cloud. So here I'm using from Dask that distributed import clients and saying that the clients, so where the processing will be done is directly on the cluster that will be created. So where there will be 6 workers and 8 GB of memory. One last thing that I'm using is just to retrieve the link of the cluster, because it's important for just to see if the cluster is working well. Here, just after, we have some different function. So we have the function Sentinel-2 Cloud Mask. It's a very common function. It's just to compute the cloud mask within the data cube. So we have just data cube with less than 30 percentage of clouds, but we still want to compute the cloud mask. So here the main idea is to say, okay, let's select the SCL, which is the SEN classification, and there is the cloud mask within the SCL, and to keep the value that are good based on this link, and to compute the binary mask, and after to select just the value where you have you don't have any clouds. This is based on the send to core because we retrieve the data from AWS. So here, so at the beginning, the idea was to compute the land surface temperature. That's one indexes that we are using at NetCarbon, but finally we will compute the SAVI indexes. So one of the reasons was that the connection with Landsat 8 seems to be a bit more difficult now on AWS than before. So we decided to connect to Sentinel-2 and to use the SAVI directly, to use the Sentinel-2 data directly. So what is the SAVI? So it's a bit exact. It's a bit the same than the NDVI, but with one major difference, which is there is less correlation with the soil. So okay, let's suppose that this is the NDVI. That's not the important part of the tutorial. So here I'm just going to compute the mask, but as said before, we are not going to compute directly the masks. We are just going to build the computation graph. So the Sentinel Cloud mask run in that run data cube is going to prepare the data cube for the real computation. So now I can check the data cube, for example. So I have still my data cube here. Okay, just one thing. Maybe that's something that you want to ask why I have adding a run here. So it's because there is this decorator, which is task. It's a perfect way to build some different tasks. But if I can erase this and just compute the value without the run, but you will see after why it's important to keep the task here. And now let's work on our data. So here I'm saying that I want to compute the SAVI. So first step, I want to create a cluster. So create a cluster will directly use this function, create a cluster. So we'll ask Coil to create a cluster for me with 6 workers and 8 GB of memory. And after, directly will connect to the task distributed, so to my client, will connect my client to the cluster. So what I can see here is that they found the software environment. So they say, okay, the NetCarbon AWS is exists. So that's the first good step. And after, it's starting to build my specific cluster. So it could take 1 to 5 minutes. The cluster was supposed to be online and to be here, but if you don't run any computation on your cluster, the cluster is like ending by itself. I think you have like 30 minutes. This is the time that you have to do any computation, and if after sorry. So you have the cluster is ending 30 minutes if after any computation was were done. So here I'm waiting the cluster to run, and I can check on the dashboard that they start to build the cluster. So here I have the number of workers is 0 on 6. So let's say that I don't have any worker for now because the cluster is still is still like creating. They are creating the cluster, and they are creating the cluster directly on my AWS account with all the parameter that I need. So I can check so I can check on my AWS account. Up. And now I can see on my AWS account that I have several instances that are in execution. So that's extremely helpful. And the cluster is okay, and I can check to the cluster directly. So here is the view of Dask, and I can see that the computation is already done. So I'm going to do the computation again. Up. So it's going to connect to the cluster. And normally I should see. So I can see the computation of my indicator directly. So here it's not a very huge data cube, it's 8 GB, but we can go and work on 1 tera, 2 terabytes, etc., etc. Okay, so the computation is done. So we run the Savvy and the Cloud Mask for 1 year of data. After I can do just another computation, which is the spatial mean and the temporal mean. And after, the main idea is to retrieve this data. So today in the pandas, but it will be extremely helpful to retrieve this data in Dask data frame. But the connection between Dask data frame and BigQuery is not very well defined today, or we have the feeling that the connection is not well defined today, or we have to work on it. So today we are using pandas, but it could be a bit tricky to work with pandas as we are working with like very huge data. So now let's retrieve the indexes for the temporal mean and the spatial mean. So now it's like processing time to data cube to data frame. So here is just some function that we have in the post processing, and it's not very like a very complex function. It's just okay, time data cube to data frame is to say that we are retrieving the data cube. We are using the name of the data cube. We reset the index, and we are using after pandas for the rest of the session. So now we have the Savvy for 1 year, and this is mainly thanks to Coiled and for this different function, as well as Dask, as Xarray, and all this ecosystem. It was definitely not possible to do it before. We were obliged to download all the data and to do it within our own computer, which could lead to a very time-consuming processing. We have the index the savvy in the spatial mean, and after we can just visualize the data directly within the notebook by using keyplayer.gl. So let's visualize the data. Let's say we want a new layer. We are going to use, the layer name is savvy. Oh, no, we know OGC. Tuto. So we want to use point. And the fill color, we are going to use savvy, and we are going to use red to green. Okay, so normally we should have our data in somewhere near border. Yeah. Okay. So as we for working with Sentinel, I think we can go to 5. And here we're just going to put the savvy. And as we would like satellite data, we're going to use the base map, satellite base map. So here we have the data, the computing data. So we can see like the savvy for different type of different area near border. And this was directly, this is the mean for 1 year without the clouds. Okay, so now that I'm pretty happy with my data, I want now to save this data. So today there is obviously several ways to save the data. I can just write GeoTIFF and a calc file directly to my bucket, my Google bucket or ArcBase bucket. Here today we prefer to load this data to BigQuery. Maybe that's not the right way, and I think we can discuss on what is the plus and what is the gain to do it. But we really like to push our indexes on BigQuery when these indexes are very important for us. So here it's not the relevant example because the savvy is not very time consuming to, but we have a lot of different indexes that are extremely time consuming. So we like to keep it and to build some different application based on this data. So now we can push it directly to the cloud. So what we are using, it's load to BigQuery. So it's in the load. It's extremely simple. We are using the pandas to BigQuery, Google BigQuery. And that's an extremely powerful libraries. It's an extension of pandas. And we will be extremely it could be extremely helpful to have this exactly same extension, but with Dask data frame. Today, that's not the case as I know, but it could be very helpful to have this type of function. So maybe there is some work to do like some cooperation to implement this type of possible function. And so that's done. Now we have our indexes on Google BigQuery, and we can directly retrieve these indexes on the Google BigQuery. So maybe we have a bit of time still, so I will explain a bit something that we really like, and that's a real game changer for us. Is okay, now that I have like all my, not my pipeline, but I have all my Jupyter notebook with the extraction, the transformation, as well as the, so the visualization part is like just in the notebook. We will not use it after, but we have everything: the extraction, transform, and load. We want to build some flow based on it, because we are not going to compute, obviously, each time a notebook to retrieve our data. So here we are using an extremely powerful libraries, an extremely powerful library and open source. They have also a cloud Geo, a cloud interface that are very powerful also. So it's perfect. It's the library that we have import at the beginning of the tutorial here, and that's the reason that we have each time we have .run in our function. It's because each function are task, are a prefect task. So when you are working with a prefect task, you need to add the .run. It's allowing the function to understand that you are not working with task, we are just working with the function. So what is the main benefit of using flow, a prefect flow? It's because after you can directly use all the power of task, all the power of Xarray, and all the power of our pipeline. Prefect is directly, it's I think native, Python native. I'm not sure. I have to check it. But you just have to enter your parameters. So here the parameter of the project, the start here, the end here, the cloud cover, the indexes. So that was the Savvy, and directly it's going to do like all the different steps. So the retrieve the location, the project, build data cube, build the processing, etc., etc., etc. So I think I have missed something here. Up, it's main. Okay. Up and see main. Mm-hmm. Mm-hmm. Okay, so I'm not sure that it's going to work because there is a several step, but here you have directly like all the flow with all the tasks. So it's extremely good to have some log to say, okay, I'm going to do the task 1, the task 2, the task 3, etc., etc., and to have like all the computation graph. So I'm going to do this task. It's building the cluster, so I can go directly to the cluster. Okay. And after is adding the metadata, the H3 indexes. And you have the result, which is directly online. So here you have all the pipeline to extract, transform, and load. And after you can obviously, and you have obviously, to retrieve this in a Python function, and you can deploy it directly. After you can check it on the perfect view. And you will have directly on the prefect view like the state of each of your different tasks. Thank you very much. If you have any question, I will be pleased to answer, and thank you for your time. And all these different possibilities are just here and are just possible because of all the work that we have all done, and all the packages that are existing with the Cloud-Native communities. Thank you. I think I can share directly. Okay, I can go maybe directly in the chat. Okay, and obviously I will put the notebook online. The main idea is to have something which is reproducible, and the main idea obviously is to promote all the work of this community, to be able at the end to have something which is easy to use, and also we should and we will try to integrate EODAG within this type of UTL. Could be very interesting to have the extraction part directly with the EODAG package. I see no question. There is no question, I think, on the chat. So I'm happy to leave the floor for the next session. I don't know who will be in charge of the next session. And obviously, if you want to have any if you want to have any news on the, or if you have so many questions on the main strategy of the extract, transform, and load, and on the packages that we are using, I will be happy to answer. And my email is basil.coussa@netcarbon.fr. And obviously, we have LinkedIn. I think it should be something like this. Yep, should be something like this. So maybe there is. Or you can just go to LinkedIn and you will obviously you will find us. Thank you for your time. Bye. if I have some time, maybe I can just share something. Concerning maybe the pricing, even if I'm not working at Coiled, so that's definitely not my purpose to sell you to. Yeah, I'm going to share the screen. Can you see the screen? Yep. So concerning the costs of Coiled, so here I can see that we have deployed 6 worker, and the cost is less than €1 per hour. So it's still something, but definitely if you have to do some like very big ETL, some very big extract, transform, and load, and you really need a lot of computation power, it could definitely be very useful for you to use it, because it's not very it's not very expensive, and it's definitely extremely easy to use, because you can just stay within your notebook, and just within your notebook you will have like just like 3 line, yeah, 1, 2, 3, 4, 5, 6, 7 lines to add, and just with this 7 line, if you are just already working with Pangeo and Excel and Dask, just with these 7 lines, you will be able to do some computation at scale. So the cost is like extremely compared to what you can like deploy very easily, compared to what you can do with it. I think there is the comparison is extremely easy to do. Okay, so that was the last thing that I want to add. Thank you. Bye.
Thank you. Hello, I think you can hear me now. Welcome to this session. We are going to start a bit earlier and use these extra minutes perhaps for the Q&A at the end. So welcome to this section about organizational perspectives, where we're going to see a lot of use cases of Stack and Cog within different organizations. I'm going to, after like around 4 minutes and 30, I'm going to show you this paper as a warning. And then at 5:30, I will show you this one. And then at 6, I will intervene, but not before that. And so for the audience, I mean, if you can post your questions either in the chat window or in the Gitter channel. We can go over those through the end, or I mean, in the end, maybe you will also be able to unmute yourself and ask questions. So please feel free to post your questions, and we'll try to address those at the end of the presentations. So we'll start, without further ado, we'll start with a presentation from Monica Diaz from Geosat about cloud optimized services from Geosat. And she's going to tell us a bit about the challenges of migration from in-house catalog of satellite imagery to the cloud-based environment and techniques. So looking forward for this presentation. Over to you, Monica.
Thanks, Diana, for the introduction. So let me just share my screen. Okay, thanks. So could you just see my screen now? Could you see my screen?
We can, yes.
We can see your screen.
Okay,
yeah.
okay, great. Sweet, thanks. So thanks for the introduction. I would just like to thank the organizer for just being able to express what are the main challenges that we address throughout our, let's say, transition into this cloud environment from the local one that still we are in train of just closing this up, but yeah, just to overview of to have a small overview of what are we doing in Geosat. So I will have no introduction of Geosat company. We are just an SME located in Spain, which owns and operates 2 Earth observation satellites, Geosat-1 and Geosat-2, formerly known as Deimos-1, Deimos-2. So we basically work on the data provision, customize and fully tailor services to clients. And obviously this cloud impact of the new techniques and new powerful capacities that the cloud allows to us, it's each time more demanded by our clients. So we had to, over the last decade, have this perform this transition. Obviously, geospatial data has become just a habitual trend in the industry since it has become easier and more accessible, and the storage options definitely has increased significantly at the same time. So basically, these new ways of geospatial data collection technologies, such as satellites, have brought new data storages and processing requirements that are more complex and more demanding. But anyway, this requirement could be met with cloud computing technologies with the support of these new main 2 standards that we feel like should be embraced at Geosat. The first one is the COG, really GOG allows for just fast and efficient access to pixels. We, for the very first time, we launched our first satellite, GeoSat-1. We have been working with GeoTIFF every single time. So this transition into GOG is really smooth, and really we are happy to get this on board. So really kudos to all this community that had allowed to get GOG as really a powerful standard with a lot of libraries and capabilities all around the libraries and the open source capabilities. Also, since it's fully supported by or the full ORGC protocols, WMS, and all so forth, so really it's quite easy to work with. And also with T. Tyler, with Vincent, really made a great tutorial yesterday on what to do and what not to do with GOG. It was really quite easy to integrate through GDAL and T-Tyler this GOG products into our complete workflow. And what we are now just finishing up is the standardization to a stack, really to have this capability of searching and discovering the catalog from our satellites, and to be able to normalize these missing parameters with regards to the rest of the missions, such as the Sentinels or other partners and in the EO community, such as Planet or Airbus. It's really powerful, and it's the customers are happy to get that. Okay, so regarding the stack implementation approach that we are following, it's based on FastAPI. We have just checked that really there are some great tutorials on FastAPI, and we really are confident that really this kind of platform, Python-based, it's really making a game changer in the current situation. Obviously, the extensions are needed as well regarding the context fields, etc. But really, the main challenge that we are facing now, it's imagine that we have a very large time series, very large catalog. So with the GeoSat, we have been working since 2009. And we have been just covering the world several times now. And this paging support for very large collection are just some tricky, but I'm sure that we will be just resolving this anytime soon. And we are trying to implement this stack support also in a serverless, so as to be able to scale up in case of different applications being needed. So really, it's the time is really the needed one for the implementation.
Monica, just to warn you that we are coming to the end of the time. If you
Okay,
could
perfect.
wrap up.
So,
Thank you.
Yeah, thanks. So regarding the what were the implementations that we are planning, it's just to automate and orchestrate the deployment and the requested steps on the geospatial processing of our data to be in a scalable platform that runs in every single cloud provider. There are lots, and certainly there will come a lot more, but we have to make sure that every single step or every single application that we offer to the client are fully compatible with any of the cloud providers in case they want to fully integrate their systems located in some of the cloud providers with our processing chain. So regarding the Amazon Web Services, we have been implementing different steps and functions, plus the Lambda functions and the Fargate containers, allowing to just perform a seamless integration of the geoprocessing by changing JSON, which is also a quite powerful file for this purpose. With Azure as well, there's some Logic App service allowing to integrate the different Azure functions, also to carry out with the full processing chain. And with Google Cloud as well, there's this workflow services, but it's still the workflow are quite more difficult to manage in the sense that it's limited to just HTTP requests that are triggering these Google Cloud functions. So we are still back in time with the integration into Google Cloud. But anyway, these workflow definition models are commonly used to define these GeoSat processing workflows into ready-to-use COG-RD products for GeoSat 2 mainly, which is, as you may know, it's a very high resolution with 75 centimeter, which allows just to get it integrated in other further applications that any client may have. So sorry for just wanted to perform a very quick introduction. But anyway, please feel free to come back to us with any question you may have. This is my Twitter and my email, and I would be happy to come back to you with any information. Thanks.
Thank you very much, Monica. And I'm sure we have some questions for you. So let's give the word to the next speaker, Rhys Evans from CDA, and he's going to tell us about STAC at the UK Centre for Environmental Data Analysis. Over to you, Rhys.
Can you see my screen? No.
No, we can't.
Okay, I may have to quickly leave and join again if that's all right. Someone else can go before me if they need to. Sorry about that.
So while we wait, maybe if we have some questions for Monica, we could. Let me see. Okay, Monica, I don't see any questions for you just now.
Yeah, neither. I was just checking on the Twitter as well.
So I have a quick question actually. So you have experience processing with different cloud platforms with AWS, Azure, and Google Cloud, right? Do you see it as a very different, the processes that you had to configure in the different providers? Is it like you have to start from scratch, or there are some similarities?
Yeah, well, there are kind of similarities in the way that there have their tools to provide this workflow definition, and obviously you have to dig into all the tutorials and documentation, supporting documentation, in order to know exactly what are the functions. Also, there are differences towards what kind of serverless implementations are available. Amazon, it's quite advanced in that way. But I'm sure that as Basile just showed with COIL, it's many other options out there that could be leveraged to get let's say in a competition and which is the one that we are looking forward to see many other competitors enter into the market and being able to get the most of any of them.
Okay, thank you very much. So I think Rise is already able to share his screen. Yeah.
Oh yeah, sorry about
that. Welcome back, and the floor is yours.
Okay, thanks. So yeah, this is my talk about how we're trying to use Stack at CEDA. So I'll just introduce the problem we were looking at and how we're using Stack to try and solve that. So a bit of background. CEDA stands for the Centre for Environmental Data Analysis. One of the main services we provide is the CEDA Archive. This is a large data store of atmospheric and Earth observation data. And this data is collected from a wide range of sources and different data providers. And these all use different instruments, different formats, different storage types, etc. And this has led to this highly heterogeneous archive, which has become very difficult to search across. Additionally, this has become a bit of a moving target as we're still growing our archive by hundreds of thousands of files per day. So we wanted to allow users to search across the entire archive with one application. This solution would need to be able to generate the metadata from our archive, which means that it would need to work with the different domains, formats, vocabularies, and everything that our data providers use. And it would also need to be scalable with our archive. We didn't think this was a problem that we were alone with, so we wanted to join a community project and produce a solution that was reusable, and that's where we found Stack, and we thought it was a good fit. We saw three main areas of work. Firstly, generating the metadata, then making it searchable and interactable, and then finally making that functionality accessible to our users. For generating our Stack data, we settled on a plugin architecture. This was mainly for our own benefit, so we could reach different areas of our archive, but it also has the added benefit of enabling it to be more reusable for others. So data is initially fed in using input plugins. We've already created input plugins for walking file directories and object store buckets, as well as reading rabbit queues and intake catalogs. The generators then use this to extract the required data using a set of extractors. Which extractors are used and what data is extracted is configurable through what we've called our item descriptions. And then finally, that extracted data is output again via a plugin. For us, this is Elasticsearch, but different plugins can be written for different use cases. The flexibility of this framework has also allowed us to use it for asset, item, and collection generation. Back when we started the project, the community API had a relational backend. I understand that they've now got an Elasticsearch version as well, but we decided to create ours from scratch, following and basing it on the current StackFast API, but obviously with an Elasticsearch backend. In addition to this, we've also proposed some extensions to the API specifications. Some of our users prefer to having a text box to search in, as it's more familiar thanks to sites like Google. So we put forward the free text search extension that enables this. We've also added an extension that adds some collection information to the context. This is mainly to aid our user interfaces. And we're currently working on enabling multi-level search. So that's search that's not just done at the item level. Similarly, when we started back last year, there didn't seem to be any web clients that fully met our requirements. They seem to either be for static catalogs or seem to be more map-based. So we designed this kind of quick and dirty React app that allowed us to get early feedback from people that may be not comfortable working directly with the API, and we're still developing that today. For our users that use Python, we've worked on the StackPy client to try and include our API extensions. So what do we plan to do next with Stack? As I mentioned, we're working on search at different levels, so not just the item. We're also looking at possible integration of our generators with the vocabularies that our data providers use. This is mainly to simplify search for our users, and so they don't have to know the different terms in the different vocabularies. StackPy seems to have stopped development from our viewpoint. So we're looking now to see if we can shift to start using PyStack instead. And finally, as always, we're looking to work with other people. So if anybody does want to get in touch, I'm more than happy to chat. With that, I'll say thank you for listening, and I'm happy to try and answer any questions now or in Gitter later.
Thank you very much, Rice, for this presentation and also for keeping with the time so well. So I think we can answer some questions in the end. I'm sure there will be some. I've got some at least. So let's give the word to our next speaker, Valera Zalienko. I don't know if I pronounce correctly your name. I think I didn't. You're smiling.
Yeah, it's the first time I'm using.
Can you pronounce your name actually?
Yeah. So my name is Valera Zakhlenyuk. It's okay. Ukrainian name. That's why it has so many Latin letters. I'm apparently showing the wrong screen. Just give me a second to adjust it. Now I think it's
okay. So Valeria is going to tell us about StackSpec as the unification layer for geospatial data hosts. So over to you, Valeria. You're sharing the screen.
Cool. Thank you a lot for introduction. And let me start with a slideshow. As I told, my name is Valera Zakhlenyuk. I'm a software engineer at Up42. And suppose you have never heard about this company. Up42 is a development platform where one can buy commercial geospatial data and process it using our infrastructure. And as you might already got out of the title, I want to quickly showcase which role Stack as a specification played at Up42 system and how we adopted it. And also one important thing to mention, one of our goals in the company is to make users be able to access data from a variety of sources. And from the engineering point of view, we have several steps of integration of these data sources. It's data discovery, data ordering, and data delivery. And if we dive deeper to the discovery part, one of the challenges that my team has been trying to solve is how to search for available data over archives. And to frame it a bit, let's assume we have a backend system that has a public API to search over geospatial data over archives. This search API could be compatible with Stack. Why not? Because Stack is mature enough and sophisticated standard, and it also meets all our needs. And there are also different kind of hosts that can provide data, and they also provide some kind of endpoints or any other interface to crawl metadata. But there is a question how to integrate these two. So if these hosts they support Stack, there are already tools available for this integration. However, it turned out that the real world situation is slightly different and could be described by this meme. It was created by our product manager, Mikola, a few months ago, and a phrase, "You use Stack, right?" became a phrase of the year. So it could be just a joke. However, it's hard truth about this market. Very few data sources provide Stack compatible search API, and moreover, if they don't, there is a high chance that their search interface is unique. And here it's a table where I try to combine different kinds, how different companies or different API described the same entity, so to say. And if you look on this table, the variety is extreme. So for example, along with bbox and intersects to describe area of interest, we found geometry, location, bound AOI, and even AOI and GeoJSON. This is my favorite. And it happens not only to area of interest, but it also happens to things like date or ID, which is not even geospatial specific. I also included collections. However, I know that this is not as it's not like stack, it's rather stack extension, but also I find it curious how different comparers describe the same thing differently. And yeah, having this in mind, we actually decided to adopt stack, but we also implemented a unification layer. And technically speaking, there are like several running components that can transform like between stack version 1 and all other varieties, including some other standards that are unique. Yeah, and in this case, not only our users, our public users can benefit from the stack and from our public endpoint, but also our backend system can use all stack benefits, so to say. And at the very end, I would love to share a few takeaways. So first of all, lack of standardization leads to low availability of plug-and-play integrations, as a consequence, a try and fail first principle stops working. The second one, having a universal standard is important for the long run, because as soon as we have it, we can concentrate on other challenges. And after listening to different talks yesterday and today, I know that Stack and cloud-optimized GeoTIFs are a foundation for further innovations in the industry, and it's essential part for us to adopt it sooner. And I think that's basically it from my side. Thank you for your attention. And if you have questions, you can drop me a message in the chat or email me or connect in LinkedIn. That's it.
Thank you very much, Valeria. That was an excellent presentation. Thank you. So let's move to our next speaker. So it will be Idas Bouwens from Nazca Maps, and he's going to tell us about the crucial role of COGS for identifying high hint areas globally. So over to you, Idas.
Hi, yes, thank you, Joanna. I'm not sure if you can see my screen.
Yes, we can. Yeah.
Okay, great. Well, yeah, first of all, thank you also for the organization to give us this 5 minutes to talk a bit on how we started using COGS and how it was on our side really a revelation back in 2017 when we started using it for the first time. So I'm a bit an outlier in this session, I see, because I see everywhere stack, and I'm going to talk a bit about COGS. But I guess then it's good to have some, how to say, some variation, right? So I choose a kind of a dramatic title to get some attention and to be sure I got in, and I succeeded. So that part worked out fine. So let's go on. Very short one slide on Nazca Maps. We are a very quite small company from Belgium. I guess most of you don't know us. We're about 10 people located in the beautiful city of Leuven in Belgium. GeoICT company, but really with the focus on building web applications focused on location. Some of us have a background in remote sensing as well. So that's also why we got a bit involved in working with this COG formats, etc. as well. But today I want to talk about the Global Wind Atlas. Global Wind Atlas is something we worked on since 2017. And to be very clear on that, it is not a project that is our project from Nazca. It's an initiative from the World Bank in close cooperation with the Danish Technical University, ESMAP and Vortex. It is not suitable, I have to tell you, I get this question a lot. It is not suitable to be used to know if you will have a lot of headwind when taking the bike and going from A to B. It is about looking for places for suitable for wind energy resources. And the main aim of the World Bank is to provide a free tool, let's say, that is accessible also for non-experts, to do the first exploration to find suitable sites for wind energy farms. So the assignment was, let's say, to combine a lot of layers, a lot of information into a tool that is accessible for policymakers, for investors, etc., to explore the potential. So there's a lot to say about this Global Wind Atlas. I cannot say it in 5 minutes. Just go to the URL and take your time to visit it if you're interested. So, but Cox played really a crucial role when building this interface back in 2017. And it was crucial for 3 parts, let's say. First part back then was to get map tiles on the fly. Second part was to be able to do clipping on the fly. And then the third part, which seems a bit trivial, but which is very crucial, is the interactive coloring. So let me take 1 minute to go deeper into the map tiles on the fly. So in 2017, we made the calculation, suppose, because we're talking about global coverage, suppose we would pre-cook all tiles and store them on S3 or something up to the deepest zoom level, which is zoom level 20. It would cost us, I think it was a couple of million or even $1 billion to get all the data on there. So it's something that is not really interesting for our young company back then. So we were looking for solutions. Okay, we're not going to zoom level 20, but even then, processing on a global level with data that has a 250-meter resolution, it's quite intensive. So when we built a system where when we go to different parts, depending on the zoom level the user is on. So we do a pre-cooking of tiles up to zoom level 10. We store those on S3, that's doable. And then when a user goes deeper than zoom level 10, it's being redirected to the Lambda. Today it is T-Tiler. Back then we used the Marble Cutter Virtual, which was kind of a hassle to get everything installed, but we were very grateful that it was there, of course. We used it in combination with Lambda, and it worked out pretty fine. We were even thinking of every time a user would go deeper to a zoom level and the tile is generated on the fly, to store that one then on S3 as well and reuse it, etc. But that didn't, it's technically possible, but it didn't show out to be much of an advantage. So, but this showed for us a very good principle, and we use it also in some of our other maps that we are making. The performance is almost identical, so you don't really feel a real difference from a user point of view, I think. So that was the first crucial part for us when starting to work with Koch files. Second thing is a clipping on the fly. So we have all these different layers that we have in the Wind Atlas. We have them sitting as global files. Each one is a separate global Koch file, one Koch file. Sitting on S3, and then we have a GDAL service running on an instance in the cloud as well. We build a small API on top of that, and it allows the user to, when it's drawing custom areas in the interface, to get really a clipped section of a specific file downloaded to his local machine. We're not doing the exact polygon because that takes a bit too long, we noticed. We're just taking the bounding box of the area and then sharing the GeoJSON plus the bounding box and letting the user proceed with that. So this was also a very interesting way to use the Kochs into the Global Wind Atlas interface, and something that was much harder to do before, let's say. So that was the second one. And then the third one, that's a bit the most, I don't know if I can use sensational, but I'm going to use it. So the most sensational one.
We are, just a warning that we are arriving to the end of the time. Okay.
Okay, I'm going to.
Let's continue.
So this is an important one. What we do with T-Tiler is we're getting the map TIFF tiles to the interface instead of the PNG tiles. So we get the raw data on the client side, and we do the coloring of the TIFF tiles in the canvas of the browser. And that allows us to do a very, very dynamic coloring of areas. You see here Uganda, which is obviously seems a bit like not windy enough to do something in it or hard to find the right spots, but using the coloring, it makes it very intuitive to find interesting spots. It also allows us to do, on the bottom right, interactive legend. You get the values when you hover your mouse over the map, etc. So it allows you to make the values very interactive, let's say. And that's my last slide. So we have some other maps where we worked with Cox as well. We have a land cover tool coming up, which will be freely accessible, where you can compare Esri land cover data, the latest, or I should not say Esri, Microsoft, I'm not sure. And the one from ESA, you can compare both, you can download, etc. And we are supporting or building heavily on the Koch principle, let's say, as well over there. That was it. I hope I was still on time. And yeah, I want to thank you once again for the invitation, and also especially also for all these people that work on these open formats, because they are very, very valuable, I think. So thanks a lot.
Thank you, Iris, for this presentation.
You're welcome.
So we're gonna move to our next speaker, Basile Gossard from Net Carbon. He's gonna tell us about the power of Stack for Earth observation. So over to you, Basile.
Hi everyone, thank you very much for your time, and I'm going to share the screen. Is it okay?
Yes, we can see your screen, yeah.
Okay, perfect. So I'm going to try to not say exactly the same thing that during the last presentation, because you already know that Stack is it's an extremely amazing tool, and that we are using a lot at NetCarbon. Here I'm going to dive a bit more on how to use different type of satellite data based on Stack and the power of it. So at NetCarbon, we use mainly like 3 types of satellites. We are not today. Today it could be an extremely nice idea to use a lot of different type of data. Maybe Up32 will be a game changer for us to implement those new type of data. But for now, we are using just 3 type of data, which is the Landsat 8, mostly for the thermal temperature, for the TIA sensor, Sentinel-2 from Copernicus, as well as PlanetScope with a large panel of satellites and this is allowing us to have the revisit that we want for different type of algorithm. But by working with different type of satellites, you are working with different, sometimes you are working with different catalog and different way to search this data. And if you want to build, like as we say, if you want to build a robust backend, if you want to have something which is like a bit agnostic, which is easily able to connect the different provider, you will need to have something which is a bit with a bit of standardization. So here, that's one thing that we are deeply involved is to still keep every time to keep Stack as one of the foundation to explore those data. And that's a bit the same with Cog, honestly, because if you have a Stack catalog, but the data is not stored in Cog, it's extremely tricky. So mainly we will have we have the Stack, and the Stack is pointing to a Cog file. So as I said, this is exactly what was the main topic here. It's to be able to connect a different type of satellites, so Landsat 8, Sentinel-2, and Planet, and to use each time Stack, because based on this, you will be able to do your processing by your own without the need to change everything on your backend side. So we have decided to use this type of data, and if the satellite provider do not have any Stack catalog for now, we do not connect to this satellite provider. So that's a very tricky choice from us, but that's a choice that is allowing us to focus on the on how we are building the solution. Maybe just to, sorry, I keep the last slide. To have a very quick example, so we are still in the same area than during the tutorial. So it's Libourne, near Bordeaux, because we are a French company. We are in Bordeaux, so I will. It's easier to study something that is near from you, because you can see it in real after. But here we have the vegetation. Mostly we have the NDVI, and the NDVI is based on the Sentinel-2 data, because we have data at 10 meters, but we can imagine exactly the same with PlanetScope at 3 meters. And based on this data, we will have the NDVI at one specific day. Thanks to Stack, we have exactly the same extractor, but just the transform is a bit different, because we can compute the land surface temperature based on Landsat 8. The land surface temperature will not be at the same resolution, but we have like different gap of resolution, but we can use some indexes and some grid to be able to retrieve the location. Mainly H3. It's a very good tool to do this, to use a grid. But what is very important here is that concretely the extraction is exactly the same based on the Copernicus, Sentinel-2, and Landsat 8. All this because and thanks to Stack, and the computation is done based on thanks to different code, for example, but we can use a lot of different providers. And at the end, what you can do, and what was very tricky before, it's to do some very some very small correlation. Here we took the same day, so the image, the satellite picture was taken at the same day between Sentinel-2 and Landsat 8, and we have done a small correlation, like to plot the vegetation index of the NDVI in function of the soil surface temperature, to see if there is some trends between both. And that was pretty interesting for us to see this type of correlation, in order to be able to study the vegetation, and after to study the temperature, to do some simulation, for example, etc., etc. But the main topic here is to say that this is possible mainly based on this this same connection between different satellite providers. So in the future, I just hope that everyone will go for Stack, and that we'll be able to use all this processing with all this provider easily.
But Basil, just a warning that we are coming to the end.
That's the end of the presentation. Thank you very much for your time.
Thank you so much, and thank you for keeping the time as well. So we still have 2 speakers before opening the floor for questions. So now we'll have James Conner from Stylight View, who's going to tell us about Stack for lightning fast experimentation. So over to you, James.
Thank you very much, Joanna. I think there was a typo in the schedule. It's actually Satellite View is the name of the company. But thanks to Chris for organizing the conference, and thanks, Joanna, for chairing the session. My name is James O'Connor. I'm a geospatial engineer with a new space technology company called Satellite View. Just quickly introducing the company, we're a high-resolution mid-wave infrared thermal imagery company. So we plan on launching a series of satellites over the next few years, which will collect this high-resolution thermal data. We're based in London, and the first launch we have planned on board a SpaceX Rideshare in early next year. Before we launch, we're obviously collecting some data. We've got a replica of the camera that will go onto that satellite, and we have it on board a plane. So we're collecting flight trial data. And the way we're organizing that is, unsurprisingly, using Stack. So I'm here. So two of the projects that we depend on quite a lot, neither of them have logos, so I took the liberty of generating some logos. One's called StackFast API. We've heard about it. It's a really simple way of standing up a Stack server in a matter of minutes. In Satellite View, we do this using AWS Lambda, and we can write that infrastructure as code, which means that it's really fast to deploy and redeployable. And the other library I'd like to talk about is StackStack, which provides, as Basile mentioned, kind of great syntactic sugar, which allows us to take the results of a stack query and generate an X-array off the back of that. One of the other things I really like about StackStack is that it allows us to use stack as the majority word in some long sentences, like, for example, a stack.stack instance represents a StackFast API stack query results as an image stack. So, in case we weren't talking enough jargon. But anyway, as again, kind of repeating some of Basile's stuff, if we look on the left-hand side of the screen here, we can define an AOI as a GeoJSON polygon, a date range, and then in 2 lines, we can kind of generate this X-array using the StackStack library. So at the top example here, we have our stack query going in. This is just a HTTP request to a URL. And then the second line will return us this clipped X-array. And so if we want to point to a different stack URL, it's just a matter of changing the URL. It's the only parameter we need to change here. This is quite a simplification because obviously I'm leaving out pagination and things here. But one of the things I like about StackStack is the flexibility that you can just pass it a JSON object and it will interpret it. And a top tip, if you don't want to worry about pagination, just pass any cloud cover filter if you're working in the UK and Ireland, and you don't have to worry about page 2. So this kind of format allows us to generate this X-array very rapidly. And for Satellite View, that means we can run the stack query rather than passing files around, and then generate the results inside a Jupyter Notebook. So just for this example, I've gone to geojson.io, I've drawn a polygon, and using the code in the previous slide, generated one image. Oh, sorry, I stopped sharing the screen for a moment. Oh, apologies. Can you see that? Oop. Yeah, thanks, Reese. So we've generated our images, and one nice thing that StackStack also provides is the ability to set the pixel size and the CRS so that actually when we retrieve these results, they're mapped onto one another, so we can start looking at downstream applications or kind of deep learning, that kind of applications. I think one thing Chris mentioned in his opening comments about the conference is this kind of idea of meeting people halfway, so extending kind of an olive branch to simplify a lot of the geospatial querying and things so that other developers can come into the fold. And I see StackStack as very much going more than halfway to simplify how we query geospatial data. So quite like it for that reason. Just one other thing I'd like to mention is our public stack that we've released 5 image samples just from the flight trials that I mentioned. I'll be adding this to Stack Index in due course, but I think I might have made a mistake on some of the extensions. But regardless, you can go, I'll pop the link in the Gitter to go and look through it yourself. And if you're interested and you think you might have other applications, I know Basile probably does, speaking about land surface temperature in the previous talk, please drop me a line. Yeah, that's all I have to say, and I'm on Twitter if anyone ever wants to chat. Thanks.
Thank you so much, James, for this presentation. And we're moving now to our last speaker of this session. So it will be Tom Krolidis from the Meteorological Service of Canada. And he's going to tell us about stack usage and considerations in weather, climate, water workflows. So over to you, Tom.
Excellent. Thank you, Joanna. Can folks see my screen?
Yes, we can see it.
Okay, excellent. Thank you. So I'm Tom Krolidis. I'm with the Meteorological Service of Canada, and today I will give a brief lightning talk on our usage of Stack in weather, climate, and water workflows here at MSC, as well as considerations for using Stack in international weather, water, and climate data exchange activities with the World Meteorological Organization. So firstly, I'll provide an overview of some of our services. We have an API platform here in Canada for our weather, climate, and water data. It's called MSC GeoMet. It's a mission-critical 24/7 platform. It serves a number of the OGC standards, both the first-generation standards as well as the evolving OGC API standards. And we also provide a Stack catalog as part of that API platform. We have over 7,500 layers, whether it's real-time data or archive data, or we have our North American Weather Radar composite that's made available, as well as high-resolution global forecast model, so our NWP data. We get around 15 million hits per day on the API service. It's publicly available for anybody that wants to use it, and there's a link to the documentation down below. And it's used in our national mobile weather application for Canadians, as well as other downstream applications. We also have a flat file server, which we call MSC Data Mart, which provides all of our real-time and archive data through an HTTP service. We generate around 2.4 terabytes of new data on that infrastructure per day, and we get around 60 million hits per day. There's a documentation link there as well. So these are raw files on an HTTP server, and they're in NetCDF, XML, GRIP2, a number of different formats, and people can use tools such as curl or wget to interact with them or just browse them on their web browser. So what we do in our API platform is basically we've stood up a Stack catalog on top of our flat file HTTP server using the PyGeo API tool. So there's an example of some model data, air temperature. You can see some of the Stack metadata, as well as some foreign members in the rendering. So that's our use of Stack catalog as part of making weather, climate, and water data available through these standards as well. I'll shift gears to MSC's participation in terms of international data exchange. So in the international weather, climate, and water realm, or in the World Meteorological Organization, we're working on something called WMO Information System, which was stood up in initially stood up in 2007. Data exchange in WMO has been around for quite a long time. It was renewed in 2007, and we're in the process of renewing it currently. That includes defining the architecture, the transition plan, and the services that will result for WMO members as well as users. So we have some core principles in WIS2 that we're putting forward: simple data exchange, open standards, use of cloud technologies, APIs, as well as PubSub. So the landscape has obviously changed, which we all know, and WIS2 is sort of positioned to address that changing landscape. I won't get into the details on this diagram, but safe to say that the WIS2 infrastructure will provide global services for all users, including a global discovery catalog, which you can search, spatial searches, temporal searches, attribute searches, and so on. We will have a global broker, an MQTT broker that notifies of all of data as it becomes available on the network, as well as a global cache that people will be able to interact with through messages on the global broker or through searches on the discovery catalog. And this is designed to lower the barrier to the information for the usual suspects in the weather, climate, and water community, as well as beyond those communities, new information communities, the mass market, and general users. A little bit more on publishing data and metadata to WIS2. So we will have heavy usage of PubSub technologies, a lot of classic formats in the weather, climate, and water realm, and we will be using the OGC API records standard to provide the global discovery catalog. So finally, some Stack considerations. we use Stack heavily in MSC for our Stack catalog. We are renewing the architecture and our services for the future for the WMO information system. What are our perspectives on Stack, currently on Stack? Stack is a very powerful ecosystem of standards, strong community, and very viable, which is great to see. We would like to see some clarification and on the intersection of the Stack API and the OGC API records. So I'm co-chair of the OGC API records standards working group in the OGC. So we are currently working on that. So I did want to also mention that here. And if anybody has comments or thoughts around that intersection, it would be valuable because there is there is some overlap between them. And we need some clarification on some of the concepts and where to use Stack, where to use OGC API records, and so on. Other areas where some consideration would be valuable are potentially Stack extensions for weather, climate, and water data. So I showed a screenshot of a GRIB2 file, which was basically showing a bunch of foreign members in the Stack item. So can we envision extensions for the weather community around doing Stack item extensions for GRIB2? Or I know there's been work on climate and CMIP, for example. So there's numerous weather, climate, and water data types out there. Is there interest from members in our community and other communities to put into extensions for those actual files, the metadata of those files? And finally, is there a role for Stack in PubSub? So PubSub and message queuing protocols are very powerful and allow people to interact with data as it happens. The way that data is made available are through notifications. Those notifications have a payload. Is there appetite for introducing Stack in the payload so somebody can suddenly process Stack items as part of subscribing to a message queuing protocol or a broker service? So those are a few of the considerations that we're discussing, and I thought it'd be interesting to bring this forward to this community here to give you an overview of what's going on in weather, climate, and water data. And I'd like to thank everybody for their time. And there I am on Twitter, so I'd like to thank everybody for their time again, and enjoy the rest of the event.
Thank you very much, Tom, for this presentation, and also for mentioning OGC API records. I understand maybe a lot of people here in this call are not familiar with it, so it was good to point it out. So I'm glad to say that we still have about 15 minutes left for questions. So I'll go over Gitter and pick the questions that were unanswered. So we have one for Rise from James O'Connor, and he's asking, free test search is interesting. What fields does it search over? Are there certain annotations done to make the assets searchable or discoverable? So Rise, do you want to address this?
Yeah, so currently it searches across the items properties, but we are currently working on another extension for asset search, which would enable this also to search across assets as well.
I might actually, if I could, Joanna, that was my question. I might just kind of follow up a bit because I remember there was lots of data augmentation work being done by the GRASS community to kind of include a lot of metadata past the typical stuff with imagery assets. So I was wondering if that was the direction this is going, and one that comes to mind is that they had population counts of a given area in the metadata of the assets they were storing to search on. So is there any kind of thinking in the kind of design space around what kind of fields we might make searchable or queryable?
Yeah, so for us, we want to aim to make all our fields searchable. But having raised that with some of these Stack people, I think they're less inclined to make assets fully searchable, as we're hoping to do. But yeah, I think our aim is definitely to have all properties searchable.
And would you include kind of use case tags for that, I guess, agriculture, that kind of stuff?
Yes, I think so, yeah.
Thanks.
Thank you. I think most of the speakers did a really good job in answering the questions on Gitter. If anyone has a question that you didn't post on Gitter or you would like to see answered now, please go ahead. Otherwise, I'll keep scrolling. Okay, so there was a thread from James. He posted the catalog for his stack collection. And then Matthias asked, great to see this. Have you run a validator over it? It seems to have some minor issues with the license. The browser could also render the cogs. Yeah, go ahead. I saw you just answered it. Go ahead.
Yeah, I wish I would run a validator over it, but these are the things you could. I guess we've generated a number of times as the stack versions change, so I thought I'd just put it out before I needed to fix it again. But yeah, no, it's something I'll definitely look at today. So thanks to Matthias for the suggestion. But looking forward to getting it on Stack Index. It's good. I'm kind of like would like to see other new space companies use that stack dot subdomain to host some imagery samples. It'd be nice to see.
Thank you. Okay, so anyone would like to ask more questions to the speakers now? It was not meant to be read out loud. Sorry, I apologize. So maybe if we have a few minutes, Tom, maybe I can ask you to give a quick overview of OGC API records for the people on this call that may not be familiar with it, and what are its similarities and with Stack? How do they intersect?
Okay, good question, Joanna. So OGC API records is positioned to address the discovery and search story for geospatial resources using the OGC API approach. So Stack has, in relation to Stack, I mean, Stack has relations to OGC API in general, obviously through features initially, and we are looking at what the relationship is with OGC API records. So back to records, it's seen to satisfy the discovery and search at a very broad and a very generic level, not only for Earth observation type data or metadata records, but any kind of metadata records, whether it's water quality data or biodiversity data, any kind of metadata, and whether the data is actually a data set or a service or a process, absolutely anything. It's also, for those who are familiar with the first generation of OGC standards, OGC API records is meant to be the replacement for the catalog service for the web standard, the CSW standard that came out from OGC in 2007, which is still used out there, just like a number of the other first generation OGC standards, as we transition over to OGC API. So it's meant to address the same use case that CSW did, using modernized approaches, open API and RESTful design patterns, and so on. It's aligning to the building blocks philosophy of the OGC API specifications. So it's built off of OGC API features as a building block, with a few conformance classes. Basically, the idea behind OGC API records is you can provide any kind of metadata, geospatial metadata, in any kind of format, and allow that to be searchable through bounding boxes or date times. We also introduce a Q equals in OGC API records, and a sort by, which I think those are going into OGC API features proper as building blocks. So then we'll be able to reuse them from records, because Q and sort by can be used by can be used by much more than just catalogs. So having said that, that's the design. You can put any kind of metadata there. For example, ISO XML metadata or the previous generation metadata formats. There is a conformance class for GeoJSON, and we do define a set of core queryables. So you can make your data available in any format you want or any representation that you want, but the record standard also provides a set of core queryables so that regardless of your information model underneath, somebody querying the catalog will be able to say title equals, and that title equals, you may manage it a certain way in your catalog and somebody manages it a certain way in their catalog, but when doing a search, it is interoperable and it allows for federated interoperability in terms of doing core queryables. There's work going on with we're targeting the end of this calendar year or early next calendar year for a 1.0. We're almost at the point for public review. There's ongoing discussions on the relationship between Stack and what constitutes a collection in OGC API records and what's a collection in in the Stack ecosystem. Again, I see Stack as more focused on EO data as opposed to OGC API records, which is, I would say, a superset of that. So there are some synergies there, and Chris Holmes has been very helpful in working with us in OGC and in the SWIG to clarify and make the relationship more clear. I think from a weather, climate, and water perspective, we're trying to clarify that relationship in terms of data granularity. So we're, one idea is having Stack providing Stack items for the granules, and then OGC API records providing the metadata for the actual collections, which then points to perhaps Stack catalogs, which could provide the lower level granule metadata. So there's we need both in weather, climate, and water data exchange. We just need to we continue to architect where both of those things are and how they interact, and where we jump from OGC API records to Stack catalog and interacting potentially with a Stack API for doing data set level searches as opposed to data set collection level searches. So granularity is a big piece of the equation, and I'm glad to see that both communities are trying to address that. So I would say these are really good problems to have, given the fact that there's so much brain power and muscle going behind both the Stack ecosystem and the OGC API standards.
Thank you, Tom, for the it was an excellent overview. So this is something definitely to keep an eye on. I just posted the link in the Gitter, so if people want to learn more about this candidate standard. So if I don't see more questions, so I'm going to thank the speakers for these really interesting presentations, which showed like the power of Stack in real use cases within their organizations, and we can continue the conversation over Gitter if you want, and wish you a good rest of the sessions. Thank you very much.
Thank you very much.
Thank you.
Thank you.
Thank you very much. Bye.
It's okay.
Hello, Ryan. How are you?
I'm pretty good. Let's see. Let's get this into the link for our tutorial. I'll put that there. I'll see if I can put it in here. To chat. Okay. Is somebody going to introduce us or something like that?
Yeah, I think we can do that ourselves.
Okay. Let's just give a minute. We are still a little early here.
Yeah, I was moderating a session 2 hours before, and there were like a lot of great talks over there.
Oh, nice.
Yeah.
Let's see. Just give this a minute. So if you're online and you're here for the Zara tutorial, I see about 100 people online. This tutorial is interactive, okay? So I'll keep putting the link in there. And what you should do right now, if you want to follow along with the tutorial, is to go to that repo and click on this link to launch binder. Okay, this is going to take you to a special binder and GeoBinder. You're going to have to log in with GitHub, your GitHub user ID. All this does is prevent crypto miners from abusing our binder by requiring a login. And this binder is going to give you just a little bit more RAM and a little bit more CPU than a typical binder. And we also know that it's running in the AWS US West 2 region, which is where our data are going to live. So yeah, go to this link. I keep dropping it in the chat here, and click on that launch binder link. And apologies in advance. I'm a little bit sick. I got a little bit of a cold, so if I lose my voice halfway through this thing, hopefully we'll be able to recover. So it's really hard to give an interactive tutorial without any feedback. And the way this GoToMeeting is set up is that we're presenters and we can't see the attendees. We can't see any comments from them. So there's no feedback from GoToMeeting about the tutorial. Okay, so I see someone is having. If you get an error, just try again. Okay. What I'd really love to get is some feedback over in the chat here of who, if you've tried to access this binder, give me a thumbs up if you're launching your binder right now.
And just a small note for everyone, I would be keeping an eye on the Gitter and the chat. So if there's any question meanwhile while the Ryan is delivering the tutorial, let me know. I'd be more than happy to, like he has told me to interrupt during the tutorial because he wants to be like interactive.
Yeah. So if you're having an error, please just close the binder and try the link again. Okay, that is the solution to this problem. I don't know what these errors about global limit has been reached mean. Maybe that's GitHub complaining that too many people are trying to sign in too short of a period, but please just try again. Yeah, it's going to take you a little while, a few minutes to start up. Yeah, it's normal that it says it takes long to start up. You're loading a big Docker image with a bunch of packages here. Great. So I'm getting some feedback that things are working. I assume it's going to be taking us about 3 to 5 minutes for everyone to get their environment up and running. Okay. And so when you load it up, you'll end up in a notebook that looks something like this. And I'm going to make this bigger here and perhaps even full screen this so we can. So this is, actually the problem here is I can't see the Gitter. So I want to keep an eye on the Gitter. Okay, so Sanket, I'm going to rely on you to pass through any questions that come up in Gitter, and just say them out loud to me, because I want to full screen my notebook here, and that means I won't be able to watch Gitter. So does that sound like a good plan?
Yep, got it.
Okay, I'm going to wait a few more minutes and just give everyone a chance to get that binder up and running. This is telling me we have 140 attendees. That is a lot to do this interactive tutorial. So I only saw a few comments in the Gitter that people are actually planning to follow along, but that's great. This works better with a smaller number. So let's start talking about what we're going to do today and who this tutorial is for. Okay, this tutorial is aimed at intermediate Python programmers. Oh, I wrote programs. It's not actually aimed at programs, it's aimed at programmers. So it would be great and helpful if you're already a little bit familiar with NumPy and perhaps have also used Xarray. You'll get the most out of this tutorial. But even if you've used neither, you're welcome to follow along, and hopefully you're going to get something out of it. So this is going to be a live coding tutorial. Okay, I am going to type code in my into my notebook here, and I'm going to hope that you will follow along and type the same things, and that ensures I can't go too fast. Okay, so this is not a talk, this is not an overview, this is an actual lesson where we're going to teach you how to use Zar. But that only works if you actually follow along with in a blank notebook and try to type in the code yourself. Okay, so some of our goals for today: we want to really learn to identify the fundamental data structures in Zar, groups and arrays, and the key properties of arrays, which are shape, d-type, chunks, and attributes. Then we're going to learn how to create those arrays and groups in both local files and directly on S3. We'll learn how to create and edit attributes and put data get data in and out of these arrays. We'll look at some of the trade-offs of different chunking strategies in arrays. And then we're going to learn how to use Zar together with Xarray to write netcdf style data to S3. And then how we do parallel distributed processing. We're not actually going to do distributed processing in this tutorial, but we will look a little bit about how we use DAS together with Xarray and Zar. So any questions about that agenda or any concerns that people are having before we jump into the live coding?
There seems to be an issue for fail to connect to event stream.
Yeah, just refresh your browser if you get that error. Okay, if you fail to connect to event stream, just click refresh. Okay.
And can you also increase the text size, like zoom in a bit?
Great. Yeah, happy to increase the text size. Okay. So you'd often just refreshing the page will fix the fail to connect to event stream. Okay, I'm gonna jump in and I'm gonna go pretty slow. And please interrupt me if there are problems. So
yeah, just before you start, everyone is getting a 503 error, service temporarily unavailable after they are refreshing. Is it because of too many requests at a single time?
I guess we crashed our binder. Okay, backup plan. We are going to switch to, okay, the binder's back. I don't know, maybe we have overwhelmed it with 100 people trying to access it at the same time. So for me, it's back up and running. Okay.
So yeah, for some people it's working, for some it's not. So
okay. The alternative is to just go to regular binder. And so the way we would go to regular binder is take this link, plug it in here, and just put mybinder.org. And that's going to take a while to build, but it will work. So if you are truly unable to get, okay, you can also try this with mybinder.org if the Pangeo binder is really failing to comply. If you fail to connect to an event stream, just hit refresh on the page, okay? Let's talk about why we're doing this and why we're feeling this pain. So the reason we're doing this is because we're going to actually read and write to cloud object storage, okay? So that requires, that really works best if we're running in the same cloud region as where our data are living. So that's the reason why we are trying to use this specialized Pangeo binder. You can, of course, run the repo locally. However, okay, so we're having a real problems with this binder. So this is, yeah, this is going to be, it's going to be an issue. So the reason we're trying to do this is so that we can quickly get the environment with all the packages we need up and running, and then have access to that cloud data. So we're just gonna keep waiting here and keep trying. Let's see. So I'm getting, there's plenty of sort of errors being reported here in the Gitter, but is anyone actually in? If you're hearing me and you're actually in and you're staring at a blank notebook, can you just give us a little feedback in the Gitter and say, you know, thumbs up, like I'm in, just so we can gauge whether this is just a few people who are having problems or if everyone's having problems. Okay, Eve says he's in. Error. Okay. So someone says my binder is working, Stephen is not in. Okay, so we're having big problems with this binder. So far, Phil is in, Hadi is in. Okay, so people are in with regular binder. Okay, so looks like we're had some issues with the Pangeo binder, but with regular binder, we might be doing better. So looks like we've hit some of the scaling limits. Okay, well, this has been a learning experience for me, and I'm really sorry for the friction that people are feeling here. This is kind of what it means to run open source infrastructure in a community-driven project. Go ahead and clone the repo, but there's no environment specification in it because that was planned to be accomplished with Binder. So chances are you will not have the dependencies installed and you won't be able to run the examples that way. It looks like my binder is probably our best choice, and those seem to be working relatively well for people. So
yeah, I think we should start now, and you know, people could just follow along through the webinar.
Okay, great. Well, let's jump in then, because yeah, we've spent almost a quarter of our time on this, and so let's just dive into it. Okay, so in order to understand how to use ZAR, we first need to remember a few things about NumPy. So let's import NumPy and remind ourselves of how we create an array in NumPy. Okay, so I'm going to create an array, call it A, full of zeros. Now, when I create an array in NumPy, I have to specify a shape and a D type. So I'm going to use F8, 8-bit floating point number. So and those properties, shape, are attached to my array as attributes. Okay, so those concepts of shape and data type are really essential for understanding ZAR and ZAR arrays. So we've created an array with shape 10 by 20 with float 64 F8 type data in it. And it's useful to think about how much memory does such an array use, n bytes. Okay, this tells me the number of bytes in this data in my array, and that number is just 10 times 20 times 8 bytes per item. That's 1600. So you know, this NumPy array lives in our computer's RAM. So obviously we cannot create arrays any larger than the array, than how much RAM our computer has. And these binder environments really just have a couple gigs of memory. ZAR will let us create an arbitrarily large array using the same semantics of shape and D type. We could create an exabyte size array. Okay, let's also remind ourselves of how we get data out of a NumPy array. So we can use, for example, slicing. If I want to get a little piece of that array down in the corner, 2 by 2 slice of that array, I can use that slice notation, and it gives me back another array that is that matches that slice. We can also assign to arrays using the same syntax. So if I create a new array, np1s, I'll make this one bigger, shape equals 40, 50, and D type equals F8. I can assign to that array from another array. Okay, so now if I look at one corner of this array where I assigned A to it, 0, 0, that's going to be 0. But if I look at the other corner of the array, that's going to be 1. Okay, so just some basic, simple NumPy review, but these concepts of slicing arrays, creating arrays, specifying shape and D type are going to be important when we get into ZAR. So I'll pause for 10 seconds and let everyone catch up. Make sure you're thinking in terms of NumPy arrays, shape and D type. Now, forgot one important element here. Okay, so when it comes to ZAR, a ZAR array has not 3 but 4 important properties. 2 of them are shared by NumPy arrays, so shape and D type. But other attributes of ZAR arrays are this concept of chunks and attributes. And so we'll go to learn what those are. There's an additional property that is filters and compressors, but I've decided we're going to skip that in this tutorial. Okay, so to understand how to create a ZAR array, we're going to import ZAR, and we're going to create an array like this, zar.create. And just like with NumPy, we're going to say shape equals 40, 50. So it's going to create a 2-dimensional array. Chunks equals 10, 10. Oh, sorry, let's start with D type first. D type equals F8. And there's this additional parameter that I'm going to give to it, additional argument called chunks. Okay, and chunks is really what sets ZAR arrays apart from NumPy arrays in terms of the API. We are taking this big array and splitting it into smaller chunks. Okay, so now I've got this ZAR array here. It looks kind of similar to, the repr looks kind of similar to NumPy. To learn more about this array, we're going to look at this attribute called info. Okay, so this is a great way, info, to introspect ZAR arrays. So we can see here what is our type of our array. This is a ZAR core array. we have our data type float64. We've got both the shape and this chunk parameter. These things aren't that important. Order, read only. But here we can see some interesting attributes, which is the chunks initialized. So we've created this array here, but we have not actually initialized any of the storage in it. So I forgot, I'm reading this tutorial off of my phone in order to be able to give this live tutorial, and I forgot a very important argument when creating this array. So but this actually illustrates an important lesson. So right now, this array lives in memory, just like a NumPy array would. If we want to make an array that is stored on disk somewhere, okay, we need to specify an actual store argument that tells Zar where to write the data. So I'm going to add this keyword argument store, and I'm going to say test.zar. Okay, and I'm going to rerun these cells. Oh, you're not going to get this error. I ran this earlier this morning, so I'm just going to remove my old array, star.zar, and rerun this cell. All right, okay, so just rerun that and this will work fine. And so now we've created the same array, except it's now living on disk. And we can see that information down here. It says store type down here, Zar storage directory store. Okay, so no data has been written to this array yet. Okay, and so if we try to get any data out of it, say if I try to index it, I'm just going to get 0. And that's because this array has this attribute called fill value, that if data in our array is not initialized yet, it will just return this fill value.
So Eves is asking a question, not a question, but he's saying that I get zar.storage.kvstore instead of directory store.
Yeah, you probably forgot the store argument here. If you're getting that error, that if you're getting that you have a memory store or something like that, you probably forgot the store argument. Okay, well, I guess a good question, and we'll address this next. Hopefully it's creating the data on disk. Maybe this is just a slight version mismatch between my environment and yours. Let me try that actually over in the binder, because I think I just launched that binder. So let me just see the info. Yeah, so this is running in that binder. I do get the directory store. That's interesting. I don't know why you wouldn't be getting a directory store, but we're just going to move on. Okay, so if you specify the store argument, it will store your array on disk. Okay, so let's move on. So far we haven't written any data to our array, but we're going to do that right now using assignment here. I'm going to write data to my array using this as sort of assignment syntax. I'm going to just use this z, open brackets, colon, close brackets, equals 1. So I'm just going to write 1 throughout the array. And now I'm going to look at z info again. Now you can see this info is telling me I have 20 out of 20 of my chunks initialized. It's also telling me some interesting information. There's 16,000 bytes in this array, just like the same example we were using in NumPy. However, there's only 1,277 bytes stored. That's because the data were compressed, and because we're providing just all the same value, the storage ratio is very large, a factor of 12 or more to store all this data. And I think by tweaking the compressors or using different data types or filters, we could get that storage ratio much, much higher, because this array just has 1s in it. But anyway, it's rare that we would just have an array full of all of ones. Okay, so we're going to delve more into these chunks and things first, but I real quickly want to just talk about this other property of ZAR arrays that distinguishes them from NumPy arrays, which are the attributes. Okay, so we can put arbitrary metadata attached to these arrays just using as like basically a Python dictionary. Units, I'm just going to assign some units to this array. And if I just look at that, let's do it like this, right? I can see that attached to that array, I now have this dictionary of attributes that I can keep together with my data. And that's very useful for scientific and geospatial data. Okay, so let's look under the hood of this array a little bit. Okay, now I want to make a point here. This is what we're about to do is really one of the key properties of the ZAR format, that it's pretty easy to just look inside, peel back the covers. And that's not the case for most other binary data storage formats, right? So like for a cog, you can't just using the command line sort of peek inside what's inside a cog. Same for HDF file. The ability to look in a ZAR store and understand what's inside is a deliberate design decision by the ZAR project to make the format very simple and transparent of how the data are being stored. So in this case, the store underlying our array is what's called a directory store. That means the data are stored in a directory hierarchy. And I'm just going to use the tree command, test.zar. I'm just running the shell command to look in this directory. So this ZAR file I created, test.zar, is not actually a file. It is a directory. And here we're looking at what lives inside that directory. Okay, and what we can see here are two metadata objects, this Z array and Z attributes, and then a bunch of these 0.0, 0.1. These are the actual chunks of data. That is how the ZAR array is stored on disk. And there's 20 of those. So I want to show you what this metadata actually looks like. So Z array and Z adders are actually just JSON files. So we can just open them with JSON and look at what they are, what's contained in those. So I'll import JSON and I'll open test.zar.zarray as FP, and then I'll display JSON load FP. Okay, so this is that Z array file, JSON file, displayed as a Python dictionary. And this really contains everything, all of the sort of internal details that ZAR needs to know in order to materialize that data into memory. It tells us what the chunks are like, what the data type is, what the shape is, and what compression has been used to store the chunks. And that tiny JSON file is all that's needed to reconstruct the overall array. We also have the metadata. So I'm just going to replace this, copy and paste this with Z adders. And look at that, and we can see our metadata has just been stored into a JSON file with that units meters per second that we specified. So this is, if you're saying, whoa, this is like trivially simple, you're right. That is the point. This is kind of like the simplest possible way you could store chunked, compressed array data with metadata. It's so sort of simple and logical in a way that like multiple different projects have actually landed on this way of storing data independently and then merged and aligned as part of the ZAR project. So the best example of that is the N5 project that began in the bioimaging community. N5 sort of designed their own chunked, compressed on-disk array storage format, and it was so similar to ZAR in its design and its simplicity that these formats are actually interoperable. And you might also be noting some parallels to COG, right? We know from the talks yesterday that cog is a, internally inside a cog, there are various chunks of data, the tiles, and there's metadata. And so, there's definitely, some similarities there. Okay, so I want to do one more thing, and then we'll stop to take some, do some discussion and take some questions. So this property of this element of chunks is pretty important. Okay, and this is sort of the main variable and also point of confusion that people have when they start using ZAR. The main parameter, generally, we don't control the shape of our data or the data type. Those are things that are determined by the, the data we want to analyze, the sensor that measured it or the model simulation that was run. But we do control the chunks, okay? And chunks have a strong impact on the performance of ZAR. So there's two kind of rules of thumb to keep in mind when choosing chunks for a ZAR array. One is that writes can be concurrent. That is, they can come from different processes simultaneously if they do not touch the same chunks, right? Because these chunks, in this case, are just separate files. So many different processes can write them at once. So this enables massively parallel writing of data in the cloud, which can be really useful for some applications. On the flip side, when reading back data, if any piece of the chunk is needed, the entire chunk has to be loaded. Now, this constraint might be relaxed in ZAR v3, but as far as I understand, it's the same for cog. If you need to get a piece of a cog, basically you read only the tiles that are needed to be read for that data slice, but there's no partial reads within those chunks. Okay, so to understand this, here we're going to compare two different chunking strategies. Okay, so I'm going to create two arrays. ZAR create. I'm going to make these a bit bigger. I'm going to make arrays that are 200 by 200 by 200. And for the first array, I'm going to specify chunks equals 1, 200, 200. And we'll make the D type equals F8, and we'll put the store equals, we'll call this C.zar. Okay, so that's one chunking strategy. And I'm going to assign this time I'm going to assign random data to it in order to not have a lot of compression available to us, which could affect the results here. So what I'm doing in these two lines of code is I am creating the ZAR array with a certain chunk structure, and I am assigning random data to it. So now all the chunks are initialized. So what this chunk argument means is that the data are contiguous along this second and third axes, but along the first axis, they're chunked. So now what I'm going to do is I'm going to time a pattern of reading back data. Here's how I read data out of that array. I'm going to just get a single, you might think of this as a time series. If you're thinking of this as your time dimension, I'm going to get a single time series or just one-dimensional array at the 0.00 out of that. I'm going to run that cell. That took 504 milliseconds. Just bear with me here. Now I'm going to do the same thing with a different chunking structure. ZAR create shape equals 200. So same shape. However, I'm going to use a different chunking strategy. I'm going to say 200, 201. Same D type, F8, and I'll call this store D.zar. I'm going to do the same thing, assign to it in the same way. D equals NP random rand N D.shape. Okay, so I've written this, I've initialized all these chunks, the data are stored on disk, and now I'm going to read back this data using the same exact access pattern. That is definitely not what I was getting in my initial, oh, that's because I did C, D, okay, there, good. So it was over 100 times faster in this second array, D, okay? And so this is a really good place to stop and discuss a little bit. What we've just seen here is a really important property of ZAR arrays, which is that we can choose the chunk structure however we want, and that chunk structure is going to really affect performance. So let me explain exactly what happened here. In this example, we created this array C that was contiguous along the last two axes and chunked along the first axis. And then we tried to read a piece of data that spanned all elements of that first axis. And that was pretty slow, 504 milliseconds. That's because it basically had to read the entire array just to get that one piece. However, here we created another array, same exact shape, same D-type, but with a different chunking structure that was contiguous along that first array. And so when I went and tried to read that data, it went over 100 times faster. That's because it only needed to access one single file in order to get that data. Okay, so this is a huge power and flexibility and freedom that you have as a developer to choose the chunks that are optimized for your problem. There is no such thing as a universally perfect chunk size and shape. It's all about trade-offs, and some things that you need to consider when you're choosing these chunks are the access patterns for your data. How are the data going to be queried? The latency and throughput of the storage device that you're using, and constraints on the number of files. So obviously you could put every item in its own individual chunk, have chunks of 1, 1, 1, but then you would be creating a huge number of files. So these things all have to be balanced by considering what is the storage device where the data are being stored. And I think that's a good place to take a little pause and take any questions or get any feedback from the group. I'm going to switch over to the Gitter and see what people are asking for. So yeah, so someone asked how to change chunks on the fly, and it's actually not that easy to change chunks once you have created a ZAR array. If the data can fit all in memory, you can just copy the contents of one array to another. So for example, I could say, you know, C equals D, right? Assign the data from one array to another. That's not going to be particularly fast at all because it contains some, and basically I'm just loading all of the data into memory. So that's not a solution for big data. For big data, we actually developed a solution for this that's called this rechunker package. So rechunker is really designed to address this question of how do you transform the chunks of two arrays from one to another, and I'll put that link in the chat here. It is in general kind of a hard computational problem, and it's pretty nasty. And so we developed an algorithm, and that algorithm can be deployed using Dask or Prefect. Apache Beam was a couple of different executors for it, but it's not actually a trivial problem. So any more questions about the sort of the basic data structures? So someone asked, what's the difference between ZAR arrays and X-array? So ZAR is a data storage format. X-array is an API and a data model for computing. So I'll make an analogy. ZAR can be thought of analogous to a file format like CSV or Parquet. And X-array is a data analysis library like Pandas. Okay, so Pandas is not a file format. X-array is not a file format. It's a computational library that you can use to do data analysis. So ZAR is comparable to other generic array storage libraries like HDF5 or TileDB. They occupy the same space. ZAR doesn't really have much processing associated with it. All the Python ZAR API really does is get you your data in and out of ZAR storage, and then you pass it along. Once you materialize it, you can materialize it into NumPy or Xarray to do your computing. Okay, let's move on. One cool thing about ZAR is that it's really easy to resize arrays, right? So if I want to make my array bigger, I can just do it like this. right? So now I just increased this array. All I really did here was edit the metadata. And now you can see only half of those chunks are initialized. But that's really pretty convenient to be able to resize your arrays like that. If you make the array smaller, you'll discard data, of course, but that's your choice as a developer. Okay, so moving on a little bit. Now I mentioned compressors, but I'm not going to go into, I've decided for the sake of time, I'm not going to go into detail on compressors. Compressors are a very interesting and deep topic. Let's just say that ZAR has extensive support. Basically, every different compression algorithm that is publicly, available and widely sort of supported and is supported in ZAR. These compressors live in a separate package called numcodecs. We use BLOSC very heavily. That's the default compressor. And it's very easy to implement your own compressor if you have a new compression algorithm. And so we're seeing, we constantly see new compressors being added to numcodecs. So, but I'm not going to go into detail there. Yes, Sanket, what's up?
Yeah, there's a question on Gitter by John.
Yeah, John's asking about CF compliant metadata in ZAR mirroring.cdf. We're going to see that right now. And so that's a great question, John. And if you just can be patient for 2 minutes, we're going to get there. Okay, so for the sake of time, because we started late, I'm going to skip the section on groups. Groups are pretty straightforward. If we have many arrays we want to keep together, we can organize them into a group. And I'm going to skip the live coding on that so we can move a little bit faster. Okay, so now here we come to the fun part. We're going to write some data to the cloud using ZAR. I've actually created a bucket for us, and I've given you all the credentials. I'm going to disable these credentials as soon as our tutorial is over, but I thought it would be more of a fun tutorial if we can actually write some data to S3. So you now all have read-write access to this bucket. And what we're doing here is creating a unique path for everyone to work in. And so I'm going to show you, I'm just going to start typing a bunch of code about how we're going to create some data in S3. So I'm going to first define a target path using a format string here. So we'll put this in my folder, and we'll call this test.zar. This will go in S3. And to create this store, I'm going to use the following syntax. There might be something more concise, but this is the way that I find easiest. zar.storage.fsstore. So here we're using fsspec, the package under the hood, to create this store. And I'm going to pass as extra keyword arguments these storage quarks that contain my credentials. Okay, so now I'll get to that part on groups. We're going to create a group the following way, zar.group, and I'll specify the store is this store. And then within that group, we're going to create some arrays. Group create, name equals foo, shape equals 200, 200, and chunks, I don't know what chunks I used. I can't read it in my original example, so I'll make them pretty big, 50, 50. Then I'll put dtype equals F8, and then I'll create another array, group create, name equals bar, shape equals 100, 100, chunks equals 120, and let's make it like this, 20, 20, and we'll do dtype equals I4. You can create whatever you want. So now we've actually created this on S3. Takes a little bit longer for it to initialize these arrays. Shouldn't take too long here. Are my credentials working here? Okay, so wish it didn't take that long, but we initialized this array. So there, we're good to go. Now what I'm going to do is assign some data to foo. Group.foo equals np random rand n, and I'll just give it the shape of foo here to so there we go. I have now written data to S3. It's living it's living in S3. And if I do info here, yeah, I can see some similar information. I can see that all of these chunks are initialized. There is not much compression at all that I could achieve on this random floating point data, but this data has been persisted into S3. And we could read it back and do all that stuff. I'm going to skip the next section I have about consolidated metadata because we're really running out of time, and I want to get to the question about Xarray and John's question. So let's just move on into Xarray and just drive forward. By the way, all the code that for this tutorial also lives in that GitHub repo. So I've sent you to a blank version of this notebook, but in the same repo, there's a filled-in version of the notebook. In fact, you can see it right over here. If you just want to open that up and see all the code for yourself, don't worry about having to like take all these notes or anything. It's all in there. So let's dive into Xarray. Import Xarray as XR. As XR, import hvplot.xarray. And to get a data set going, I'm going to open the tutorial data set for Xarray. We'll call this is called air temperature. And I'll just run all that. So what I'm actually downloading a data set from the internet right now to load this tutorial. So I have to confess that I almost never use ZAR directly. I almost never import ZAR in my day-to-day science work. Instead, I'm always using ZAR through Xarray because I love Xarray. I love Xarray's data model. So this is an Xarray data set. If you've used NetCDF before, it looks very familiar to you. We can see our dimensions, our coordinates, lat, lon, and time, and our data variable, air, with dimensions time, lat, and lon. Okay, so we can see there's metadata attached to all of these. This HTML wrapper is one of the reasons we love Xarray. And so let's take this data set and just write it to ZAR, okay? And write it to ZAR in the cloud. And I think that's going to answer a lot of questions. So first, what I'm going to do is chunk it, because it's nice if we chunk our Xarray data set, we will automatically use those chunks when we're serializing it to ZAR. So I'll just remind you, this data set has 2,920 time points, and I'm here saying that I want to chunk it in time with 100 points in time kept together, and the other dimensions contiguous. DS chunked. Okay. And so having done that, we can see now that this data is represented as a Dask array. The total array is 14 megs, and the chunks are about 500 kilobytes each. Though that's actually really small chunks. We don't really need to be doing chunking for this type of data set. It's a small data set. I'm just doing this to illustrate the capabilities here. In reality, you would if you're working with ZAR in the cloud, you're probably working with much bigger data sets. All of this scales up. So this is just demonstrative here. It's not meant to be like, we don't really need chunks or Dask or ZAR for data this small. But anyway, so now let's do the fun part. Let's define a path where we're going to write this data to. So path equals, put this in S3, my folder /air temp.zar. And now I'm going to do one more thing. I want a progress bar for writing this. So I'm going to, from Dask diagnostics, import progress bar. Okay, so and then what I'm going to do to write this to ZAR, is I'm going to do with progress bar ds chunked to zar path, and I need to specify these storage options, storage quarks, right? So it's a little bit inconsistent naming here, but now I'm going to run that. It takes a little bit of time to set up the array, and then it's going to start writing all of those chunks to S3 in parallel. S3 seems to be running a little slow this morning, but there we go. So we just wrote that whole Xarray data set to S3. And now when we read it back, ds from S3 equals xr open dataset. Here's how we open it back. I know this is going fast, but I'm leaving this on my screen. So path engine equals zar, and then storage options equals storage quarks. ds from S3. And I guess I should put this down like this. So now I read the data back from S3. And I got a zar data set that looks like a netcdf data set. Actually, I think this data originated as a GRIB data set, but anyway, coming straight from S3. And to me, that's pretty magical, and it's super convenient. Now, John asked, well, how is this being stored? How is this, where is this coming from? Well, we can go under the hood again and open this data directly with zar. I guess I'll just stop there and let people catch up, because I've gone kind of fast and I typed a lot of stuff. So I'll just leave this on the screen. And
there's also a
any
question.
Questions, Sanke?
Yeah,
go ahead.
There's a question by Rachel, which goes like, if you open a zar with Xarray and then specify chunks that don't line up with what is in the source zar store, that doesn't actually change anything in the original zar store, correct? So you really shouldn't ever specify chunks if you're reading a zar store.
Yeah, so this is, I'm glad Rachel asked that question, because there's a couple different options that we can use when we're reading data back. As you can see here, by default, I didn't actually apply any chunking to this data set at the Xarray level. So we're not, by default, using Dask. If I specify chunks equals empty dictionary and run this again, you'll see what happens there is that by default, the chunks, the Xarray chunks, and the Dask chunks get mapped to the zar chunks. So here we have the exact chunks that we specified when we wrote the array. So that's chunks equals empty brackets. Another option is chunks equals auto. In this case, I think Dask will choose chunks for us, and in this case, it decides to just choose one big chunk for all of this data. Because actually it's not very big data at all. I think the heuristic is to look for 100 megabyte chunks. So if you want to make sure that your Dask chunks, when you open the data, line up with the zar chunks, you want to specify chunks equals empty brackets. And I'll be honest, I don't love that API there. I wish it was a little less sort of secret spell that you had to specify here, but it is well documented. If I do open data set and I look at the document on chunks, if chunks is provided, it is used to load the new data set into Dask arrays. If chunks is -1, loads a data set with Dask using a single chunk for all arrays. Chunks equals open and close curly brackets loads the data set with Dask using engine preferred chunks if exposed by the backend. Okay, so, and I believe the same behavior actually will work for HDF5 files as well. Any file format that has chunks underlying it, Xarray will do this mapping.
Yep. There's another question by James. Can zar store unstructured grids?
Czar can, people always ask that, and I would say the following. There are a lot of different ways to serialize an unstructured grid into into an array. So I believe Czar can store unstructured grids. I would kind of, the reason I think that is because most unstructured grids, if they're coming from a model, they're written to a netcdf file. And Czar can store any data that can be stored in the netcdf data model. So therefore, Czar can store unstructured grids. Now, does Czar have any understanding of what an unstructured grid is? No. At the end of the day, Czar is just storing arrays of rectangular arrays of uniform data. And it is up to the higher level tools in our stack to understand the connectivity between the grid cells, et cetera, et cetera. So that's my answer there. There's a new project called Project Regen, here, out of NCAR, that is designed to create some computational tools around unstructured grids. And all of these grids, all of this data are ultimately stored in netcdf data, and these are the goal of this is to build some tools on top of Xarray that make it easier to work with those sort of unstructured grids. So I would say Czar is pretty agnostic about what is the underlying structure of the data. It's just a way to persist arrays. Yeah, and I think we'll stop there. There's a bunch more examples, that you can go through. Like at the end of the notebook, if you want to go through it on yourself, this is like the completed notebook here. You're gonna see. Oh, we didn't do any plotting, but that's a lot of fun. You're going to see some examples of loading data like from the CMIP6 cloud data, right? So if you want to run through those examples on your own, loading some data from climate models stored in the cloud. We didn't get to make any nice plots. The Muir SST data set is this absolutely massive data set. Each array is 15 terabytes, and that's what the chunks look like. So that is a very intimidating but very cool data set. So if you want to run through those examples on your own time, you should definitely do so. We've ran out of time here, so sorry about the binder difficulties here. But hopefully you got something out of this, and we do have a few minutes for questions and discussion. So I'd love to just open it up here.
Yep. We have a question from James, which is it possible, planned, or appropriate to size chunks based on spatial footprint schema?
I don't understand the question.
You just need to scroll a bit. Yeah, that one.
Is it possible, plan appropriate to size chunks based on spatial footprint schema? So I don't understand some of the vocabulary being used here, and it's not, but in general, you can choose the chunks based on your application. If you have an idea of what chunks would be well suited to your query pattern, then you can choose them in Czar. Let's look at some of these others. So Rachel, Czar, unstructured grid. The utilities to convert netcdf and HDF files to Czar without losing anything. Yes, Xarray. We just did it, Pavel. Xarray is that universal Swiss Army knife of data formats. Xarray can read GRIB, netcdf, HDF5, all of that stuff, and then serialize it to Czar without losing any of the metadata. Czar itself also has some tools to do this. When I'm working with data, I almost always go through Xarray, but Czar itself has tools to do that. So Val asked, any reason you're using XR open dataset engine equals Czar compared to OpenZar for reading data back from S3? Basically, OpenZar is being deprecated, and we want to have all reading go through open dataset. So are there plans to implement data versioning and deduplication within ZAR? There's not currently plans for that. I maybe Josh could say more about that, but I don't think that's on our roadmap right now. Leaf Denby asks if he should make his large eddy simulation write directly to ZAR. Yes, you should. There was a really interesting study from NCAR evaluating the performance of ZAR as a HPC data format. I'm going to try and dig up that study after I close here, but it works great on HPC file systems. The main downside really is that it does create a lot of files, and some file systems, HPC file systems, don't like that. As for calling it from Fortran, well, you can, the NetCDF library actually now supports it. So maybe you can just even go through NetCDF. Okay, is ZAR plan to be supported by Stack? Yes, we're working on it. We've had a little bit of difficulty fitting Stack into the ZAR into the Stack data model, just because Stack is itself, ZAR, you can almost think of ZAR as a catalog, right? It's a catalog of chunks. It has its own approach to metadata. And so there's a lot of overlap in terms of concepts of you know, between ZAR and Stack. But yes, we need to make them talk to each other. We're getting some other questions, but I'll try and answer some of them in the chat. I think we need to move on now because we're at the end of the hour. So thank you all for engaging with that. Sorry for the friction around Binder. Hopefully everyone who wanted to was able to access the material, but in any case, it's all on GitHub if you want to follow up in your own time. So I'll stop there.
Thank you, Ryan. So yeah, the next talk, just a second. So the next talk is an overview talk about ZAR, and I'm just having a little bit difficulty. Yep, here we go. So seems like I need to rejoin so I can share my screen. So I'll be back in just a second. Stop. Is my screen visible? All right.
Yeah, I can see it. Yep.
Great. Yeah. So yeah, here we go. Thank you, Ryan, for giving the extended tutorial about ZAR. And so this is basically a two-part talk. So I would be giving an overview talk about what ZAR is and how things are done over in ZAR, and Ryan would be taking care of the cloud part, like cloud native part of the ZAR. So let's start. A little bit about me. I am the community manager for ZAR. I have just started the position, and before that, I was heavily involved with PyData, and I'm also taking care of PyData Delhi, and also chaired a couple of PyData conferences. And I worked with startups, forensics, and organization in the past. And when I'm not doing anything on my computer, I tend to play violin. And if you like this talk, you can follow me on Twitter or just give a cheers and thumbs up. So this is what I'm about to show you, like what is ZAR and how ZAR works, why use ZAR, and what is ZAR specification, and the implementations. Like there are like various implementations of ZAR in different languages, and how does ZAR basically ties up with the PyData ecosystem, like all the other libraries like Xarray, Dask, and everything that you've seen in the tutorial, and what is basically the ZAR community, and there are future goals, and last but not the least, geospatial data in ZAR. So yeah, ZAR was basically created by Alistair. Alistair is Oxford genetist, and it was founded back in 2015. And he was basically looking at data format at the time to to work with quite large data sets that could read and write across multiple threads and support parallelism. And it was like nothing that was basically solves this problem. So he went on and created ZAR. And ZAR is basically industry ready, and people are using it into production a lot. And currently it has 21 core devs, and we are fiscally sponsored by NumFocus. So yeah, all our legal operations and everything is taken care by NumFocus. And we have also been funded by CZI. CZI is basically Chan Zuckerberg initiative to support essential open source software. And yeah, you can follow us on Twitter and GitHub, and or this is our website zar.dev. So all of the updates and everything basically goes around these channels. And we recently also got a LinkedIn profile. So if you're on LinkedIn, you can also follow that. So yeah, so we basically missed like a couple of plottings in the notebook, but yeah, here is what different kind of images, different kind of data looks in ZAR. So the left side is the oceanography data format, which is basically for the geospatial environment, and on the right side you can see the image from the microscopy environment. So I'm not really sure what it is, but yeah, it looks beautiful. So yeah. So yeah, before ZAR, let's have a look like what an array or tensor is. So I just want to start from the ground up and address audience of all the levels. So yeah. Basically array or a tensor is a container of items. So array could be like a single dimension, two dimension, or multiple dimensions. And all the containers of the items are of same data type and size in bits. So if there's an 8-bit, there's an 16-bit, 32-bit, 64 bits, and so on and on. And the number of dimensions and the items in the container are described by the shape. So if you define the shape as a single digit, that is going to be a single dimension. If you go with 2D, it's going to be like 2 dimensions, and 3D, and so on and on. So yeah, like what is ZAR basically? So ZAR is like an open source specification format for storing chunked, compressed, and n-dimensional array. And when I say specification, I would emphasize on that, and I would explain it later, like what does a specification means basically. So yeah, basically how does ZAR work? So let's just say you have a small array and small data you want to store, and you can easily store it on your memory or on your disk. Like, but what if a data is too big to fit in a memory? Like, I don't know, maybe around 100 million or 1,000 rows or something like that. How would you fit that? So what basically ZAR does is like it divides your array into small chunks, into evenly distributed chunks. And then each chunk is basically compressed using a wide range of prominent compressors. Like we by default we use BLOSK, but there are all other compressors that are prominent, like ZST, ZLib, and they're all available in a numcodex library. So you can just go over to this link and you can see the available compressors, and you can just
as you would create your ZAR, ZAR array using ZAR store, you can just specify your compressor over there. And only the chunks which corresponds to your selection desired are being read back into memory. So you need to basically specify like which chunk you want to read back into memory, and only those will be read back, and all of the other chunks would be stored into memory. So it will not take your disk space. And yeah, so multiple arrays are basically organized into hierarchies of groups. So it's like Z arrays. And so the green part, which you can see on your screen, is basically the metadata, which contains the format, and which contains the information about the data. And the purple or pink, whatever color it is, it's the data in binary format. And .z array basically describes how those binary blobs are encoded, and each binary blob is basically given a unique key, and they are basically referenced using that key. So you can see that there's 0.0, 0.0, 1.0, 0.1, 1.1, and so on and on like that. And so yeah, how does the basically the whole compression thing happens in ZAR, and how does everything happen? So you basically take those so ZAR basically take those contiguous binary chunks and pass it through any optional compressor you can find in the numcodecs library, and that gives basically a sequence of bytes, which you can see right here, which is basically 011110. And that sequence of byte is basically gets stored as a mapping with the key, which is basically 0.1 for the image and for the depiction in the image. And so conceptually, all the storage is basically happening is like a key value store, and where key are basically strings and values are basically sequence of bytes. And any system which can expose the key value system type interface, they can use ZAR store. So that's the I would say the interoperability or the diversity, or like how ZAR works. And so for the Python implementation, we basically use mutable mapping to interface to set and retrieve ZAR data. So basically set item to set keys and get item to get the keys and its value. Yeah, and so there was one thing that Ryan mentioned in his tutorial about writing concurrent data to your different chunks. And so I'm sure like a couple of you might have thought about like, is there a write lock which could happen during ZAR? So yeah, so if each writer is writing to a different region of an array, and all the writes are basically aligned with the different chunk boundaries and not overlapping each other, then writing lock would not happen. But if writers are not aligned with the chunk boundaries, with the different chunk boundaries, then the write locks could happen. So this is just a very small thing you can keep as a footnote while you are concurrently writing data to your ZAR in a cloud format or in a local storage. So yeah. Yeah, so as you can see in the tutorial, and as you have seen in the my explanation, like why use are there are different formats out there. So yeah, the first and the foremost important thing is like arrays can be read and written concurrently from multiple threads and processes, and that basically gives a edge to ZAR, and you can basically speed up your operations and your workflows like many times. And it's like very easy to append and extend and append data to your ZAR store. And you just saw that how we did that in using the S3 bucket and just writing data to it. And you can chunk arrays along any dimensions, like you can chunk arrays along so if you define 3 dimensions in your 3-dimension data, you can chunk array along any dimension. So it's not restricted to any dimension, like 1 dimension. And as I've also mentioned earlier, like there's an extensive support for compression. So we are basically always in pursuit of like adding new compressions to our numcodecs library, but there's also a list of a large list of compressions, so you can choose any compression according to your use. And so as I've said earlier, that any key values interface system can use ZAR store. So it basically supports both the local and cloud storage system. And about the specific, and so yeah, it's basically based on a specification, and which allows it to be hackable. And I would be talking a bit about specification in the next slides. Yeah, so what is basically ZAR specification? So ZAR specification is kind of like a technical specification or a set of rules or protocol which are basically written, which are basically used for storing ZAR arrays. And we basically use current version 2 right now. And it is basically us, you can, so if you follow the specification and you can write the implementation of ZAR in any language. And there have been a lot of development recently in different languages like C++, C, Julia, JavaScript, and all of that. So specification is kind of something I would say like a Bible for ZAR when you are basically writing the implementations. And it basically tells you how the hierarchies are organized and arrays are chunked and grouped and how the metadata should look like. And so V2 has been going on for some time, and we are basically kicked off the development of V3, and there's a PR number 898 on the ZAR Python. I would share the slide so you can just look at the PR, and it's currently in the progress, and we basically hope to see that happening very soon. Yeah, as for the implementations, I have mentioned earlier, like we have the Python implementation, which is the most prominent and most used, but we also have like Unidata folks have developed Java and C++ implementations, which you can find under their GitHub repositories, and C++ implementation, Julia, and JavaScript. And it's like I mentioned earlier, like if you read the ZAR specification protocol, it's relatively easy to implement ZAR from scratch. Like if you have I'm not sure if there's implementation in Fortran or any low-level languages, but if you want to do that, you can definitely do that. And I'm sure there would be a massive increase in your write and read time speeds using some low-level languages. So yeah, I would talk about the ZAR community and future, and after that Ryan would emphasize on the cloud importance of ZAR. So yeah, what is ZAR community and how you can join us? So ZAR community is essentially the users, the developers, or anyone who is interested in ZAR and wants to contribute to ZAR. And it's like an open community, and everyone can just start contributing to it. And if you're interested in ZAR in any way, you can just join us, and there is like no hard and fast rules to join ZAR. You can just head over to our Gitter channel and just drop a message to I'm interested in ZAR and I want to I want to contribute in the development, and I'm more than happy to point you to some issues. Or if you're basically using ZAR and you want to I don't know, maybe get some help, like get some helps or get to know some tips and tricks from the users or the community, yeah, just drop into our Gitter channel, and I'll be more than happy to direct you over them. So this is what ZAR community is, and let me talk a bit about future. So since I've joined the ZAR, I have been working on the ZEP. So ZEP is basically ZEP stands for ZAR Enhancement Proposal. The naming is quite similar to the NumPy proposal, which is NEP, and Python Enhancement Proposal PEP. And which is basically a community process to implement changes to the ZAR spec. And it's something like a structured way or a process to include the changes in the spec. So previously we used to do like used to follow the GitHub workflow to include changes, but now we are basically finalizing the ZEP. The discussion has been going on for like a month, like quite a month, and we are basically in the stages of like final confirmation for the ZEP. And if there are any changes that needed to be added to ZAR, or more importantly the ZAR spec, it would follow the ZEP protocol or the ZEP process. And if I talk about like V3, like what does V3 look like and what are the features? So like in terms of spec, the bigger change the V3 is moving towards is like separating the metadata from the file structure and the arrays. And also we have ask around community and taken community consensus in effect, and seems like everyone in the community wants to have that, like separating the metadata from the main data. And there's a very interesting I would say spec change that we are looking for is like a extension protocol. So currently the spec doesn't allow you to have extension protocols. Currently the spec is Currently, the spec only has the core protocol. So if there are any changes that are done into the spec, that needs to be implemented over all the other implementations of ZAR. But we are basically looking towards an idea of having a protocol extension, which would basically allows you to have a optional change in ZAR, which could be used by other implementations or implementation which you will develop by you or not. So it's kind of like a mechanism which basically gives ZAR a very personalized feel. So if you're working with ZAR and you want to have like a small support from for some variable or some feature or something like that, and you're not sure that it should be in the main core protocol, you could add it as an extension protocol, and it would work, and you don't basically need to follow the ZIP process or all the community process for the extension protocol. So this is what the V3 V3 in general looks like, and it's still in development. So if you have any, I would say, suggestions or some recommendations for us, so feel free to join our Gitter and drop our suggestions over there. We are more than happy to take them away. And the most interesting thing that we are working on right now is the sharding support. So I'm not gonna go deep into sharding, but you can see this PR, and there's a lot of discussion about that. So yeah, this is what the future of ZAR looks like, and the community is great, and a lot of things are happening. Like sharding and V3 are basically the main thing, but also we are having a ZEP to basically cover everything which has been going into ZAR community, and it's like a very wonderful time to join ZAR and get involved in the developments and give your suggestions and stuff. So yeah, seems like Brian, would you like to?
We're out of time, so I'll just go real quick. ZAR is often used in the geospatial context as part of this sort of Pangeo cloud-native software stack that interoperates with Dask and Xarray. And this software stack, allows us to take advantage of cloud object storage on every cloud provider. It allows us to scale out using Kubernetes or other distributed computing low-level primitives that are provided by the clouds. And for geospatial data, most end users are really interacting with ZAR through Xarray, as I showed in my tutorial. That allows us to then have a lot of domain-specific packages on top of that really can just focus on one specific application rather than having to reinvent sort of I/O and the core data model. And of course, using Jupyter Lab is a very common way to interact with those tools in the cloud. Next slide. So as for geospatial data in ZAR, basically, if you take ZAR and then you store the netCDF data model in it with CF conventions, you have a cloud-native geospatial data format. And that's what we've done sort of to get things started. ZAR V2 is currently up for vote as an OGC community standard. And the community standard really just covers the actual core ZAR V2 spec. Doesn't address geospatial data. There is another spec that is it's sort of a set of conventions on top of the core ZAR spec called GeoZAR, which have been proposed by Christophe Noël of SpaceSpell. And right now, I believe that is also working its way through OGC as a more formalized way to encode geo-specific information like CRS, labeled dimensions, etc., within ZAR. And so this is certainly a place where alignment is needed. Yeah, and I mentioned the Pangeo stack. So next slide. So I know this is a big topic, ZAR versus COG, when to use each. This is my attempt to lay this out. So COG is really limited to 2 dimensions plus bands. It really comes from the GIS raster data model. It's great for satellite imagery with a single scene per cog. And it really needs stack to extend to higher dimensions, time series, data cubes, stuff like that. ZAR, in contrast, is n-dimensional. You can store any number of dimensions in it. Could you please go back?
Yeah, sorry.
For geospatial, we're really using the NetCDF data model. ZAR is great for L3 and above satellite data, stuff that's been gridded, harmonized data cubes, simulation data that's run on a fixed grid. And because of its ability to incorporate so many dimensions, it doesn't strictly need Stack in order to store a very large, complex, data structure. However, we would like ZAR to integrate better with Stack so that we can expose ZAR data through Stack. Next slide. These are two examples of ZAR datasets in the cloud. These are also in the tutorial. One is the CMIP6 public dataset that's in AWS and Google Cloud Storage. It's over a petabyte of data, split up into 500,000 individual ZAR stores. In contrast, we have the MER sea surface temperature dataset that was produced by Amy and Shell Gentleman. And this is a level 4 sea surface temperature product. It's 54 terabytes in total, and the entire thing is one big ZAR store. So that's a sort of two very different ways to sort of organize ZAR data in the cloud. Next slide, and I think that's the end. Yeah, so that's where you can learn more. We really welcome everyone's input. We're working hard on a V3 spec and would love to engage the OGC community there. And sorry for going long.
Yeah, and just a small note, we have our community call tonight for me and evening for European folks. So if you have any time, or if you feel like joining our community meetings today, you can join us. It's on our web. You can find the link on our website. And yeah, everyone is welcome. Thank you. Yeah, so seems like I'm also your moderator for the next sessions around ZAR. So let me see. Do we have Nestor with us?
Yes, here.
Hello.
Hey, ciao.
How are you?
Fine, you? Thanks a lot for the great introduction, Ren and Sanket.
Thank you. So yeah, Nestor. Yeah, sorry. Sorry?
Yeah, it will just make my life easier now when I introduce what we did, because then I have to skip a lot of introductory topics, and it's actually very nice.
Yeah, that was the idea.
Yeah, perfect.
Yeah, so Nestor, take it away.
Okay, perfect. So you tell me if, so you see my screen, right?
I can.
So, well, first of all, my name is Nestor. I am a software engineer. I've been working in different areas. I live in Switzerland, in Zurich, and I work for the Federal Office of Meteorology here in climatology in Switzerland. And I would like to show you how we use ZAR, and especially how we integrate the ZAR with Postgres so that we can query the metadata catalog using the database. So first of all, why? So that's our use case. So we have created a product called GridFX, where we actually have a bunch of endpoints to make gridded data available for production systems in order to provide real-time or near real-time data available, and also for development, so all the projects can train their models for post-processing and so on. So that's the main idea behind our product or our project. This is a big overview of all the components that are involved in such journey. So we are event-based, so we have a broker that notifies our system in order to import the data. Then we store the chunks in a ZAR group, in ZAR groups, or in ZAR arrays. In Cloud-Native, everything runs in OpenShift, and we have a bunch of services like to fetch the data and to query the data. To query would be the catalog. And in this small talk, I would like to focus myself or to show you how we configure the data store in order to use Postgres together with tar. So what is motivation? Why do we need that? So we wanted to in the catalog service, we want to have fast queries, and the most important is to have data consistency, so that the metadata or the catalog data is actually on sync with the chunk store. So this is our the tar metadata store data model. So in the middle here you see the tar nodes. That's the table that tar uses to load the metadata from the database. And then we have two tables that they link to each tar node. And in that tar node, in those tables, sorry, is where the catalog looks up. For example, in order to find arrays that with a specific coordinates, or with a specific variables, or with a specific tags. So we have a bunch of queries in order to find the nodes that we want to load. This is more how the tar node table looks like. So here you see that we have different levels of groups. So we have the root level, which is our source ID. Then we have the UUID to identify the arrays. Then for each array we have coordinates, and we can also have timestamps, and for each timestamp a variable. And the leaves are the tar arrays. So that those would be for example, the vertical coordinate as highlighted here, or the air temperature. Those are tar arrays. And then we have tar as a tar group. We have for example, the arrays that they are also highlighted. Also, the Cosmo 1A, for example, is a root path. Is also a tar group. Here a bit of glue code. So this is mainly the code that makes possible to use tar with the Postgres database. We implement a store extending the mutable mapping object, and in the get item and set item, we implement the queries in order to fetch data or store data. And we have the main or the root group, and there we configure the store, the metadata store and the chunk store here. And then how to load, for example, using a Dask array from tar, using our Postgres SQL store as a metadata store, will be as simple as the following. So given an array path, so we know already, so we have used our catalog to find the variable and the timestamp and which array ID or which path we want to load. And then we can actually create what we call grid-fix database, which it wraps the tar root node, and then we can just, with this command here, gdb point root, then we pass the path, and then this is actually a tar array. Then we can load such tar array using Dask from tar method, and then we have, so we just show here that we get the same shape, so it's the same array. Okay, so I also posted here, or I actually printed out some Jupyter notebook screenshots. Here I use our service, so we have a bunch of API services or REST services to query our database or our metadata. And here, for example, for a given source, I fetch the first variable, actually one of the variables. In this case, is the mass content of water in soil, and then I fetch the tags. So we tag each array in order to for example, if we are going to use that array for a specific thing, then it comes with a tag. So we can tag it, and then we can query for such tags. And then, given that variable and that tags, the list of tags, I just fetch the first one of the available timestamps. That will be this query here. Then here is how we load the arrays. So we use Xarray, that was also previously mentioned. We open dataset and we use OpenDAP protocol in order to stream the data. So behind our service, we use Dask to load the tar array and then stream the blocks to the client. In this case, this open dataset will then call the endpoint. So Xarray also supports the OpenDAP protocol, and then at the end we get such data set. This is that will be also the outcome, and we can also plot it. Also using so yeah, now that the data set is loaded, then we can actually plot it, and we can do anything we want in such case. And as a summary, using Postgres speeds up the query for the catalog and also any other metadata. Then something that actually that was our origin is that we had some corrupted data because we wanted to, so we had the catalog, let's say, aside of the tar chunk store, and we weren't using transactions at the beginning, and that kind of corrupted the data. So with such transaction management, we can actually mitigate that problem. And then we also have a housekeeping service. We clean up some data eventually. And the good thing is that we only need, so the housekeeping only needs to know SQL and the S3 API in order to clean such arrays. So we don't even use Thar or Dask to clean the data up. So we just know, okay, here, those nodes, they have to disappear. So it's actually very simple. And that could be the end of it. Thanks a lot. I guess questions for later.
Yeah, thank you, Nestor. And I think you can head over to Gitter. Sorry, questions will be over there.
Yeah, thanks.
Thank you. So next up we have Keda Martin, visualizing ZAR data in web maps.
All right, hello, my name is Keda Martin and I work at Carbon Plan, and I'm here to give you a very quick talk on visualizing ZAR data in web maps. So actually, let's get you oriented thinking about web maps by looking at Google Maps. Really fundamental part of web maps is the interactivity and how I can pan and zoom through a map and get different views in space. And the thing that accommodates this is that the map is fetching new information, more detailed information as I zoom out, information about different areas as I pan. And this is the pattern that's formalized around this is using map tiles. So square, in our case, chunks of data that are fetched and stitched together and rendered within the map. So this is supported and standardized through tools like GLJS, which renders and customizes vector tiles in the client, which we've used in the past. And some limitations we run into using Mapbox and looking at other tools out there is that vector tiles creating vector tiles was something we uniquely had to do for rendering in web maps. And it was also just an inefficient format for representing gridded raster data, which is what we work with in climate. There's not tooling that's designed to accommodate data with many dimensions. And in general, there's just limited flexibility around styling and computation. So we wanted to do more, and we decided to turn to a format we're familiar with, which is ZAR. So here's a very quick demo to give you the idea. We're replicating the panning and zooming and map tiling pattern that we saw on Google Maps, but we're using raster data, which is coming from ZAR chunks as the map tile. So we'll come back to this demo in a bit, but Under the hood, what does this look like? Well, we're using multi-dimensional data pyramids in ZAR format. And we created a small library, ND pyramid, to standardize certain processing steps. So we're using the Web Mercator projection for our map tiles. We're using the multi-scale specification, and we're using zlib compression, and we've standardized on a 128 by 128 pixel chunk, which that chunk becomes our map tile that we're fetching as we pan through the world. On the right, we have an example data set where, or it's an example pyramid where we're looking at monthly temperature data. And at the 0 group, we can see that there's just, the data just spans 128 by 128 pixels. There's only a single chunk or a single map tile, which is representing this, a very coarse view of this global data set. And then as we move down the pyramid or down to the first group, we have a bit higher resolution, 256 by 256 pixels, which means that there are going to be 4 map tiles to represent the globe at this view. And so on, as we move down the groups, there'll be more and more higher resolution tiles or chunks, and this is where the idea of the pyramid comes in. And then on the front end, what we have is a system of React components, which we've exported from a new library that we created called Carbon Plan Maps. Here we have a raster component, which is pointing to a ZAR store, and then is rendered within a map component. So what's happening here is that the raster component is responsible for figuring out, given the web map interface and where the user is in the map, figuring out which chunks to fetch from ZAR, and then rendering those using WebGL. And yeah, so going back to our demo, what does this look like? So we can see the, the higher resolution, lower levels of the pyramid coming in as I zoom in the map. And yeah, this is really just the ZAR version of what we saw on Google Maps. Another thing that's really nicely accommodated by ZAR is we were looking at chunks that also contain 12 time steps. So I can pan through time. And what we're doing is just indexing into different parts of the chunk along the time dimension. And same for variable. It's the 4th dimension we're dealing with in this pyramid. Looking at a slightly more complicated example, this is a web map we created to map the potential climate benefits and the cost of growing seaweed, scaling up seaweed farming. So what's happening in this map is that each chunk contains a bunch of input data. So potential for growing seaweed at each location, the depth of the ocean, wave height, distance to port, a bunch of information. And then on the fly in the map, we're calculating the estimated removal cost. And we're also, because this is on the fly happening client side, able to take into account different user specified parameters. And so here, because we're just able to do whatever computation we want to on top of the data that's coming through in the ZAR chunks, this opens up a whole range of possibilities for what our web maps can do, including doing things like taking in user inputs. And also, I earlier mentioned the flexibility around styling. We can very easily adjust the color map, things like that. So it's a complicated map, but really this pattern of using ZAR as the data source and the components built around the React components we built to kind of standardize on that pattern has made this pretty ergonomic, making tools like this much easier on our end. So thank you. That was a very quick tour through our world of web mapping. I left our contact information here. Please reach out if you have any questions or want to contribute to our mapping library. Really, whatever. All right. Well, thank you so much. Bye.
Yeah, so that was the recorded talk from Kera. So next up we have Ethan with us. So Ethan would be talking about CM-IP6 ZAR example and calculation across hundreds of CPU core using Dask on AWS.
So I actually have a video as well. Should I play it from my computer?
Yes. Can you share your screen first?
Let me give it a try.
Sure.
Unsurprisingly, I'm having the same I must restart in order to share issue that others have had. Apologies.
Yeah. No worries.
Okay, I'm having issues with his video as well, so let me keep trying.
Yeah, sure. So I think Shane, are you here?
Hey, I'm here.
Yeah. So can you start? All right.
Okay, can everyone see my screen? Okay.
Yep. Yes, I can.
Perfect. Okay, I'm Shane Mill. I'm from the National Weather Service. I'm here presenting with Steve Olson. We're exploring cloud backends for the new OGC API environmental data retrieval. So skipping ahead, the OGC EDR API background. In general, OGC API standards define modular API building blocks to spatially enable web APIs in a consistent way. They're all based on the Open API specification, and they're organized by resource type. The EDR API standard, it defines two goals. One, to allow clients to retrieve a subset of data created by the API in response to a standardized coordinate-oriented query pattern, and then to provide building blocks allowing for construction of more complex applications. This is just a quick overview. Basically, the EDR API acts as an abstraction layer between disparate data formats and systems. We homogenize the data together. The EDR API handles that and then describes the data in self-describing URLs, structured URLs. We have schema support for different formats, CRSs, interpolations, etc. Ultimately, we're getting to the means to the end for a feature extraction from a sample coverage. So what do we mean by that? In this situation, we're focusing a lot on meteorological shapes. So we want users to be able to query data by a position, radius, area, cube, trajectory, and corridor. Meteorological data is multi-dimensional data, so that lends well to using the Pangeo. Can you guys still see my screen?
I think it just vanished. Can you reshare again?
Yeah, yep. Okay, are we okay now?
Looks good.
Okay, good. So the Pangeo stack is used on the backend for the multi-dimensional data. Ryan did a great job going through this, so I'll go ahead and skip ahead. So a lot of our meteorological data will come in netcdf or GRIB. So this is just an example of, for the GFS model, we have a bunch of GRIB files that come in. We concatenate that into X-ray dataset. That's where we do a lot of our manipulation of the data. We choose to organize our data in a certain way. For the GFS, we're organizing the data by common dimensionality. And then we're storing that in S3 or Lustre or on disk using ZAR. And we're chunking data in the process based on how we expect our users to query the data. So with that ingest process in place, we have these different ZAR data stores in place in S3, and the EDR API on the fly, based on user query, will select that specific collection from ZAR, load that back into X-Ray. We'll do our trimming and slicing, and then we have some modules that connect to X-Ray to output in netcdf, GRIB, JSON, and so on. The EDR API specification, it provides complete versatility in how you construct your collections. So we tend to base it on use case of how we expect our users to query the data. This first use case is basically a point and click map for selecting weather parameters. So it's basically just a position query. So we know our X and Y chunks will be very, very small to limit how much data that you're loading. So we want to keep the chunks small for optimized performance. But with the GFS, the queries vary quite a bit with like area queries, corridor queries, and so on. So as Ryan explained before, you just have to find the right trade-off for how you organize your data on the back end to optimize performance on the front end. I have a quick demo. I want to hit 3 main points. The EDR API accessing the National Water Model River Stream archive. That's in Big Data Program S3 bucket. It's terabytes of data, and I want to show how, and it's in SAR, I want to show how Dask can load that data asynchronously in a pretty optimized way. We have a GFS collection stored on Lustre file system. That's also chunked in SAR. I want to show the effective trimming and slicing of that. And then basically bring 2 OGC APIs together, the process API and the EDR API, and show how they can integrate with the ZAR backend. So on to the next slide. Here's basically a screenshot of the Dask dashboard in action. This is basically hitting the S3 bucket that I mentioned. This is 6 months of hourly data being loaded in 6 seconds. Without Dask and the ZAR chunking, we just simply could not have that type of performance before. So this is pretty impressive to hit a time series for a petition query and get this type of performance. Now I'm going to back out and load my browser just to show a couple more things. If I zoom in a little bit here, this is the EDR API endpoint for the GFS model. So here are the sampling geometry types we talked about: position, area, radius, cube, trajectory, and corridor. I'm just going to do a quick radius query here. Let me zoom out just a little bit. You can use this leaflet map, just select a radius on the map. Based on the metadata, we have choices loaded here for the user. So I'll select a temperature for a time series. We have the opportunity to output in coverage JSON, grid, NetCF, and Cloud-Optimized Geotiff. So I'll select coverage JSON there. These are multiple isobaric levels that I can select here, and then click Show Data. So what that did is that accessed the ZAR backend data store. It, through X-ray, did the trimming and slicing. Through the user interface, we could just add like a quick palette so you can actually see the data for the different vertical levels and the different times there. And then the different output formats. As I said, you could download Grid, NetCF, and Cloud-Optimized Geotiff. And then bringing it all together, here's basically a client that we've developed different computational and derived processes for the process API. The client will basically access that process API for this specific computational class. So I'm going to demonstrate a threshold here. This is a dropdown for the EDR API available collections. So I'm going to select the GFS surface level collection. I'll select an area for temperature, for a model runtime, and then for a time series. And then on the map, I could just select an area.
Shane, we lost your screen again.
Yep. Yeah, it keeps.
Shane, can you please reshare?
For some reason. Yep. So then there's the area on the map. What happened was the EDR API went and found the min and max of the data there, and now the client is creating threshold values. So if I select 280 Kelvin, this is now hitting the OGC API processes and just giving you the data that meets the threshold. So I'll just quickly add a palette there. So you can see the data on the map there that meets the threshold. We can add basically a contour for the polygon that meets the threshold. And what we're able to do here, you can see the outline there. We could download the data in coverage JSON, NetCF, PNG, Cloud-Optimized Geotiff, which will hit the process API. But then we have a GeoJSON output too. And then to end this here, you can see that using the GeoJSON playground, you could just load, and let me zoom out a little bit. You can load that polygon that met the threshold. So this is basically just integrating the EDR API and process API together to add a few more insights to the user and a little bit more capability, treating the OGC APIs as building blocks, and all of this with a Pangeo stack type of backend. So with that, I'll end the presentation, and any questions or comments, please hit me up on Gitter.
Yeah, thank you, Shane. And yeah, everyone, please head to Gitter for the questions. And so we have Ethan's video. I think it should be playing next.
Hello, my name is Ethan Fay, and I'm a Senior Solutions Architect at Amazon Web Services, or AWS. Today, I'm going to show you an example calculation run from a Jupyter notebook.
I think we can't see the video.
Yeah. Going to Ethan's.
Organizers, yeah, can you like?
Hello, my name is Ethan Fay, and I'm a Senior Solutions Architect at Amazon Web Services, or AWS. Today, I'm going to show you an example calculation run from a Jupyter notebook using the CMIP6 dataset. And this calculation will be parallelized across a Dask compute cluster to make it go faster. So CMIP6 stands for Coupled Model Intercomparison Project version 6, and it contains the model output from a number of climate models with the intent of allowing researchers to compare the results between these models. The CMIP6 data is hosted on AWS as part of the AWS Open Data Program, and anyone is free to access this data, along with many other geospatial and climate datasets that may be of interest. The CMIP6 data that we'll look at today is in ZAR file format, and it's hosted on Amazon's S3 object storage service. To make my calculations run faster, I will be using a combination of Xarray and Dask to distribute my computations across many CPU cores spread out across a number of underlying Amazon EC2 compute instances. To save on cost, I will show you how my setup automatically instantiates new EC2 compute instances when I request a compute cluster from my Jupyter notebook, and automatically terminates those instances when I'm done. I only pay for the compute resources that I need when I need them. Because I only have a few minutes today, I'll show you everything very quickly, but note that you can recreate everything I show you today on your own AWS account using the detailed instructions that I have on GitHub, and I'll have that URL for you at the end of the presentation. Here is the Jupyter notebook that we'll use to run our calculations. After importing the required Python libraries, the first step is to create what's called a Dask cluster. Right from my Jupyter notebook, I can select how many CPU cores I would like for my cluster, and then run this code block to create my cluster. Under the hood, a number of Dask Worker Docker containers have been scheduled onto my Amazon EKS Kubernetes cluster. I have an EKS cluster autoscaler configured, which in turn automatically instantiates additional EC2 instances if there are not enough available for the scheduled containers to fit on. If you do have enough EC2 instances already, the cluster creation takes only a few seconds. To save on cost, I typically do not have these EC2 instances on all the time, so it can take a few minutes for everything to spin up and become available. Now that some EC2 instances have been created, I have a Dask compute cluster with 52 cores and 171 gigabytes of RAM so far. Note that I also opened the Dask web interface, which we'll look at soon. In these next few code blocks, I'm using the Python library Xarray to create a dataset object that points to ZAR data from the CMIP6 S3 bucket. If we inspect this section of the dataset, we can see that it's around 6.5 gigabytes in size. It has 31,390 time steps worth of 180 by 288 grids of air temperature at 2 meters and air pressure at mean sea level. After converting the air temperature from Kelvin to Fahrenheit, let's do an example calculation by taking the mean air temperature across all 31,390 time steps of this dataset. Because we're using Xarray and Dask, this calculation can be parallelized and run across all of our Dask worker nodes in our cluster. We can see how Dask created and executes its task graph by looking at the Dask web interface. Each colored block you see here represents a piece of the overall calculation performed on an individual worker node. As the mean calculations progress, the results are aggregated back together to create the final grid of mean values. This calculation ended up taking 27 seconds, and it takes significantly longer when run on only a single CPU core. For even larger computations against larger datasets, it becomes increasingly important to leverage this type of system to parallelize the computations. With the calculations complete, we can now shut down the cluster, which in turn terminates all of the underlying EC2 compute instances, saving on cost. That's it for our demonstration today. The key takeaways are, First, AWS's Open Data Program hosts many geospatial and climate data sets that you can access, including CMIP6. Second, using Xarray and Dask running on cloud infrastructure like Amazon EKS allows you to scale out to get your research questions and calculations completed quickly, but it also scales back in to save on costs because you only pay for what you use on the cloud. Third, ZAR is an n-dimensional cloud streamable file format ideally suited for large n-dimensional climate datasets, and you can find examples of ZAR datasets on the AWS Open Data Program, along with example blogs and notebooks to help you get started. If you're interested in a detailed walkthrough on how to recreate what you saw today, please check out this URL on GitHub. And with that, thanks everyone for your time and attention. Please don't hesitate to reach out if you have any questions or feedback.
All right. Thank you, Ethan, for the talk. And Ethan, you can ask questions to Ethan on the Gitter channel. He's already over there. So yeah, next up, do we have Charles and Rachel with us? Hello, Charles. Hey, Rachel, how are you? I can't hear you.
Doing well.
Great.
Can you hear me, Sanket?
Yeah, I can hear you.
Oh, great.
So yeah, just a quick intro. Charles and Rachel would be delivering a tutorial on PanGeoForge, an ETL platform for cloud optimized analysis ready for data.
Great. I'm going to begin by giving a few overview slides, and then we'll get into the tutorial portion. So let's just see about sharing those. One moment. This is apparently what I had heard might happen, which is that I need to restart in order to share my screen. I apologize. I'll be back momentarily.
Sure.
I'm going to explain quick what will happen while Charles is logging off and logging back on. So Charles will spend about 20 minutes. We're going to talk about PanGeoForge, which he'll explain in more detail as a tool for kind of creating cloud optimized data sets. And then I'll take about 20-ish minutes and go through a tutorial on using PanGeoForge. So we'll take some data that's OISST sea surface temperature and we'll convert it to ZAR. In the last 2 minutes, we'll then talk about kind of two pieces. There's the PanGeoForge recipes and PanGeoForge cloud. So then we'll talk about the cloud piece and how you can run that processing on the cloud. And hopefully have some time for questions. We'll see how things shake out here.
Yeah, that sounds interesting.
We will be using or kind of doing with this for folks who are earlier on for the ZAR tutorial, some of the same compute the binder resources. So we'll have to kind of see how we go there as we get to that point, folks starting that, or if they want to install things locally. So we'll hit that bump when we get there.
And you are also on Gitter, right?
Yep. So we'll be watching that chat as well.
Great.
Do we want to share the binder link now, just so people can start spinning things up and getting those errors out of the way while Charles is doing the introduction?
Yeah, it sounds great. So I'll share two of them in the chat, Dan. I'll share PanGeoForge binder. I'll share the my binder, and then I'll also give a couple instructions. If folks want to install locally, they can do that as well. So folks can go ahead. There's 3 different ways you posted to either start a binder link or install locally. And so you're welcome to kind of, in theory, we're all sort of spread evenly between those two or between those different options. So folks can start clicking the link. And if you haven't done one of these tutorials with a binder link before, what'll happen is a page will pop up in your browser and it will start building an environment. And you can, it'll take a few minutes for that to start up while it builds the environment, and eventually should launch like a workspace with a Python notebook in it. If it isn't working, there's a lot of, typically it's sort of refresh is kind of the thing to go to, but if it can also post in the Gitter and we can do our best to help.
Seems like Charles has joined again.
I think someone needs to promote him to
yep. Panelist.
There he is.
Hey, Charles.
Yay.
Hey.
Okay, great. I think this is progress. I'm so sorry for the technical difficulties. Great. So I think you can see my Gitter. So let's make it show the right thing and make up for some lost time. Okay. Okay, hi everybody. My name is Charles Stern, and I'll introduce my co-presenters momentarily. We're going to be speaking about PanGeoForge, which is a cloud-native data library and a data ingestion transformation tool for ocean weather and climate science. So I'm here today with Rachel Wegner from the University of Maryland, and also you've heard Ryan Abernathy earlier in the session, and he's also here to support the project. He's the creator of the project. So you've already heard a lot, so I just have one slide about this right now, that analysis-ready cloud-optimized data is very fast. You've already heard about tools like Xarray and even the ZAR format, and the incredibly high throughputs that can be achieved when using these tools together on the cloud. Here's a reference if you're interested. It may have been mentioned in some of the other presentations discussing some of those performance characteristics. But what we want to discuss today is the problem of how to make analysis-ready cloud-optimized data, and particularly how difficult that is. There's a lot of interlocking, very difficult skills, hard to achieve skills required to create analysis-ready cloud-optimized data. There is the domain expertise of the scientific domain to which the data relates itself. There's technological knowledge about how to efficiently produce cloud-optimized formats. There are compute infrastructure concerns related to producing cloud-optimized data, and obviously there's also this slide may have been clipped a little bit, but there's also the communication aspect of creating a platform to disseminate and distribute the data that's been communicated in a clear way. So this is a very difficult challenge. PanGeoForge, I see we're getting a little clipped here. PanGeoForge aims to provide a platform that allows more people to participate in this data curation process. Let's talk about our inspiration for that. Our inspiration for PanGeoForge is the platform CondaForge, which many may be familiar with. CondaForge is a community repository and community curated repository of precompiled software binaries for a lot of very well-loved and well-used packages in the scientific Python ecosystem. This is too small to perhaps see in the slide, but CondaForge now hosts well over 14,000, perhaps over 15,000 community contributed recipes for building these binaries. And we think it's a very successful model of crowdsourcing this type of resource for the community. So PanGeoForge has two main components. It has a PanGeoForge recipes, which is a Python package for building up pipelines for data transformation from archival formats into cloud optimized formats. And we also have PanGeoForge Cloud, which is our cloud platform for executing those recipes. The recipes themselves, as we'll see today, can be executed on their own on your own local infrastructure. But by using PanGeoForge Cloud, we have the advantage of taking advantage of a much larger cloud compute infrastructure, as well as contributing to a community catalog. So just briefly about the recipes, let's see if a slightly larger zoom will be useful to us here. Just briefly about the recipes. Recipes are Python objects, and Rachel will talk to you about those momentarily, which have sensible defaults and are really quite easy to compose if you're familiar with some basic Python concepts. The cloud, again, just to recap, is composed of a few different modular components and is the infrastructure and execution environment for those recipes to execute them at scale. So a feed stock, just to cover a few key vocab words, is a concept borrowed from CondaForge, and a feedstock is a GitHub repository where these Python recipes live. The bakery is a cloud compute cluster that actually executes those recipes, and a storage location could be on storage providers such as Amazon S3 or Google Cloud Storage, is where the bakery, which has executed the recipe living in the feedstock, deposits that output data. So our vision is really to have a collaborative data curation process that by hosting these feedstocks, which are GitHub repositories on GitHub, we provide a place for all of these nice data users, data managers, data producers to have a conversation around the quality of that data over time. Once the data has been created, the recipe that was used to create it lives in one of these feedstock repositories. And as you can see on this slide, all of these folks are participating in a conversation around improving the quality of that data. So this really gets at one of our core values, which I'll just mention as we wrap up these slides, that we're trying to help the community realize through PanGeoForge, which is transparency and reproducibility of the data pipelines, which is something that we see as missing from alternative ways of methods of ARCO data production today. And just building on that theme, PanGeoForge is a 100% open project. We're just showing some screenshots here of some of the repositories and project boards that are involved in producing this platform. So we certainly welcome everyone to take a look and even participate, and hope you will participate in the project at github.com/pangeo-forge. So this gets into our tutorial section, and I'll conclude the screen share of these slides just by saying that, you know, all of us today are guinea pigs. This is a brand new platform, and we're really grateful for your interest in it. And with your feedback, we hope to make it a much, very robust and useful tool for all of us to use, to produce ARCO data in the months and years to come. And so with that, I will stop my screen share and hand it over to Rachel to begin the tutorial portion.
Lovely. So let me just look for the share screen here.
Works.
Okay, are we all looking at the tutorial here on my screen?
Yep.
Lovely. Okay, so what we'll go through in the next bit of time is the tutorial. This is the tutorial that is on the PanGeoForge documentation. So if we don't get to the end, or if you get lost or you're unsure kind of what the next step is, all the information about the share is in the documentation. So over the course of the tutorial, what we do is we take some data that is available through NOAA. It's sea surface temperature data, and it's originally stored in NetCDF format. And throughout the tutorial, by the end, what we end up with is that same data set, but it's been converted to ZAR. So if you've gotten what I'm going to do throughout the tutorial is keep the original tutorial on one side of my screen so that you can see what the source tutorial information or source tutorial information is, and then on the other side of my screen I'm going to put up the binder link that should come up for folks who have run the binder. Just checking in on the getter, it sounds like Ryan is kindly promoting some of the binder link, putting those back at the bottom of the screen, and installation instructions. Has anyone gotten those to work? Thumbs up in the chat if you have gotten that to go.
Rachel, I am seeing a note from one user in the chat that it looks like the PanGeoForge binder link. I'm sorry, the Pangeo, the PanGeoForge binder link is perhaps doing better than my binder.
Okay.
I would say, Rachel, carry on with the tutorial, and I'll monitor the chat and help people get going. There are at least a few people who have the binder up and running and will be able to follow along.
Okay, sounds good. Okay, so that being said, then what we'll be doing is creating. So PanGeoForge has a number of objects that it uses to create what's called a recipe. So a recipe is this definition, this thing that defines how we're going to transform our NetCDF into ZAR. So I like using the markdown cells to kind of give myself an outline. So our high level goal is to create a recipe. That's like the biggest thing that we're trying to do. In order to do that, we have a couple of sub-steps. So one of them is to create a file pattern. So part of the idea of the recipe object is that it's leaning on the fact that a lot of data stored online has a sort of a directory or a folder file type structure. So you can move through different folders in a directory and find a data set located in that. And it's leaning on the fact that those data sets are typically named in a predictable way. So that idea of predictably named data organized by file name is called a file pattern. So we'll want to create one of those. Within that, what we'll do is we'll create what's called a format function, which I'll explain in a bit. And then we're also going to create a concat dimension. So these are the things that we're going to be doing, and they're sort of nested here. I'll make this that the format function, the concat dimension, is going to go into the file pattern, and the file pattern is going to go into the recipe. So there's all those steps that we're going towards in the end. So what we'll start with is creating a file pattern, and what we'll want to do is when we first start making a recipe in PanGeoForge, the first step that you always want to do is get very familiar with the file structure of the data set that you're trying to convert. So in the case of OISST, which is the data set we're converting here, this is a diagram that shows what we have, which is a URL, noaa.gov/data/sea surface temperature, on and on. And then within that, there's folder for each month and month of each of the years that it's present. So we're noticing that our files have a single file, and each file represents one day. And the days of a particular month and year are then grouped together into a directory. So those are the big takeaways that we would get from exploring the file structure of the source data set. we would take that. What we want to do is take that then, a URL that represents our data set, and we want to make that into a template. So something that can be generalized to then pull out the URL of any data in our data set. So what I'm going to do first is copy and paste this string from the tutorial, which is, I forgot. So I'll actually take this URL, which is a single URL of a data format that you can see when I clicked it, it actually downloaded. I'm gonna put it into Python. And then what I'm gonna do is go through and replace any place where the URL changes. For example, here, where it changes by the year and the month. And I'm gonna put in curly brackets. So year, month, that's what goes there. And the other place where the URL changes is at the end, and that was shown as year, month, day. So this is a string that is a template that we could use to generate all of the files. So what we're going to do then with that is use that and take that to create the file pattern. So with our file pattern, I mentioned that we have two pieces of that. We have what's called a format function and what's called a concat dimension. So the format function is the thing that is going to take that this general template URL that we just made, and it's going to, given a day, it's going to give us back the actual URL for that date. The concat dimension is going to define how we want all those files to live with relation to each other. So we're going to tell Zar that we want each of the days to sit on top of each other, stacked up in a big pile, and that information about how we want the files to stack is the concat dimension, or the combined dimension. Well, yeah, the combined dimension, which in this case we're gonna use concat. So let's start by getting a list of all of the dates that we have data for. So one way that you can create your list of dates however you'd like in Python. One way that I find particularly useful is to use pandas. So I'm going to import pandas as PD, and then create a list of dates using the date range function. If you were to go back and look at the data set, you would see that we have data from 1981 through, we'll just go with sometime in February. This tutorial uses the February 1st. You could go to whenever there's data. And there's data every day. So that frequency equals D is telling us that piece there. So what comes back here then is this list-like thing that has a date for every day in our data set. So I'm going to assign this to a variable called dates. In order to take that those dates and tell PanGeoForge how we want them to get stacked together, we're going to use PanGeoForge recipes dot patterns, and we're going to use this concat dim object. So the concat dim takes 3 arguments. We're going to tell it what dimension it's concatenating over. So in this case, it's time, because every day is the thing that's getting stacked together. We are also going to tell it the dates that we want it to stack. So in this case, that nice list of dates we've already made. And we're going to tell it how many items there are in every file. For us, since one file corresponds to a single day, we have 1 item per file. So we'll say concat time concat dim equals concat dim time. We're going to use our dates, and n items per file is 1. So this concat dim is a PanGeoForge object. Okay, so that's one of our, we're halfway then to our file pattern in that step. The other half of the way to our file pattern is called the format function. So that's the thing that will take our date and it will give us back, ooh, interesting. Well,
don't worry about that. It's just a weird thing that happens sometimes with the Dask Lab extension. It doesn't mean anything.
Okay, it means nothing. Continue. All right, great. So what we're going to do is make this format function. So we're going to make that, that's just a function in Python. And so we will we're going to make a function in Python that's going to leverage the strf time aspect of Python to do the formatting for our dates. So we will define a function. We'll call it make URL, and it's going to take as an input one of our time arguments, so a single date. We're then going to we're going to want to use our format URL that we use, our template URL from earlier, which is the thing that we'll want to give back. We'll return from our function, I guess I could say. And we'll want to substitute these places where we defined year month and year month day. We'll want to substitute them with the formatted version of our date. So year month can be made in Python by taking our time and doing strf time %y %m. And our year month day can be done with strf time %y %m %d. It does look like it's hanging a little bit. Let's see if I can stop the pandas import and keep going.
Looks like your kernel may have disconnected. So you might want to refresh that notebook.
Yeah, that sounds good. Do you see?
Just hit
do you
refresh on your browser. Like just.
Thanks. Uh-oh.
Oh, all right, Binder.
Yeah.
It's giving us problems again.
Indeed. I can pull this up locally rather quickly.
Lesson learned today that Binder is not super reliable these days for doing these types of tutorials.
Yeah. All right. Okay, backup plan to the backup plans. Let's see if we can get this. So here what I have, just to, I think for the, whoa. So to keep going with the tutorial to kind of get to the part where we'll get to see this kind of all go, I'm gonna walk through this then on my local computer. So I'm using, right now what I have pulled up is the notebook that actually is the one that gets made into the tutorial. And so let's just rerun quick to get back to where we were previously. So I'm rerunning now to create that list of dates. I'm rerunning to create our time concat dim. I am running to make our format function. So this is where we just were with make URL. And what we see when we have make URL is that if we put in here, remember what our dates list looked like, is this long list of dates. And if we pick any one of them, the fourth one, for example, we can stick that into our make URL function. What we get back is the URL of that particular file. So this is a lot of, there's sort of a bunch of little steps that build up to making the individual pieces, but we're now at the place where we can make a file pattern. And in order to make a file pattern, what we're doing is giving it our function, and we're also giving it our time concat dimension. So to remember what those were, that make URL was that function, and time concat dim was this concat dimension object. And what we get back from that is a file pattern. So we can see what's happened is that there are 14,764 individual days in that data set, and that those are all going to get stacked over time. Each one is changes by time, and that will go together to make our recipe. So if we want to interact with this a bit more, to kind of, I guess, give it a little more, kind of maybe understand a bit more what is in there, we can iterate through it. And what's in it is an index and a URL in the pattern. And if we print them out, you can see what's inside the file pattern. And let me also do copy this little bit of code here, which is going to not print all 14,000 files. So just to look at this, we're seeing that we have this thing that's an index, and we're seeing that we have our URL. So the index is defining the relationship between files, and the URL is telling PanGeoForge where to go and get that file. Okay, so relationship between files and where to go get the file. And that's what's inside of that file pattern. So in the end, it's fairly concise. So that's all of the first part of that tutorial, is creating the file pattern object. That's our first really big step. I'll pause for a sec. Have any questions come up in the chat that we want to address before moving to the second part? Looks pretty good. So I'll pause for another couple seconds in case folks want to add questions, and if not, I'll keep rolling to the second part. Okay, so in part two, what we're doing, this is part two of the 3 parts of the tutorial, and what we're doing here is that we're going to take our recipe or our file pattern, and we're going to make it into a recipe. And once it's a recipe, what we can do is actually start creating the ZAR. So up here, what I just ran was a big cell that had everything that we wrote in the first part of the tutorial. Now that we've made our recipe object, or our file pattern object, creating a recipe is actually fairly quick. So we're going to import from PanGeoForge recipes this xarray ZAR recipe, and then using that that class, we are going to give it the pattern, and we're going to tell it how many inputs we want to go into a single chunk. So we've been talking about chunks all morning, and we're going to tell it we want 10 files to go into an individual chunk. That number was chosen because we're kind of targeting about 100 megabytes per chunk is usually a good starting place or good size. So we are picking 10 based on the file size of the original objects. So we have back as this recipe thing, and it's got a lot of I guess parameters you can look through, but really what this is now it's the definition of how to convert our data. So let's go ahead and actually do that. Before we convert data, do actually run the recipe. It's nice to set up logging, which prints out some outputs, which are good for debugging and understanding what's going on. And in this case, because we're testing a recipe, we don't necessarily want to convert all 14,000 files of data right now. So we just want to do a small subset. So PanGeoForge has a function for that, or a method called copy pruned. And what that does is it takes just a subset of the data. So we can see, looking at the recipe output, that now we have only 2 time steps in here. If we were to look at the original recipe, we would have that 14,000 time steps, but in our pruned version, we have just 2. So we're going to run our pruned version to just do 2 files instead of doing 14,000, which likely wouldn't work on my computer. And we can see that also in the file pattern would be another way to check that out. So in order to run this, we're going to do this thing where we convert our recipe to a function. This might be a little odd if you haven't seen this before, where you are actually having the output of a function is another function. But when we take recipe pruned and run to function, we're getting back something that is a Python function. So we run that like any other Python function, which is with the parentheses. So as we do that, we're seeing in the output that the various files are being cached and downloaded. They're opening them up in xarray. They're creating the chunks, consolidating the metadata, and converting to ZAR. So I tell you it's run, but if we want to check for ourselves and really see it, we can import xarray, as we were doing earlier, as a great way to read ZAR data. So we'll use xarray's OpenZAR. We will take the target mapper of our recipe, which tells us where that this file was stored to, and we will open up our data set to see that we have some data in here. So it has lat long, it has 2 time steps, which is the amount that we tested, and if we plot it, we can see our sea surface temperature here in the end. So we've now gotten to the point where we have our ZAR version of OASST, which in our Python script, in basically these number of lines, a couple of lines, we've converted from netcdf to ZAR. So that is, I think, where I'm going to pause and check for kind of questions, and we'll talk about that What we'll do is we'll have a bit of questions, and then Charles will talk about the cloud side of PanGeoForge. One of the things to highlight here, I think, is we have kind of two parts. We have PanGeoForge recipes and PanGeoForge Cloud, which are sort of independent units. So I've been running this tutorials with PanGeoForge recipes, which you could use and run completely on your computer and not do anything necessarily related to the cloud. But as we've been talking about, there's a lot of benefits of using the cloud and to really take that czar and kind of make the most of it. Running and hosting the data on the cloud is a great benefit of the czar, or is kind of most optimizes, I guess, the PanGeoForge recipes tool. So the two independent pieces, but also very highly related.
Yeah, good. Thanks for pointing that out, Rachel. I think that it's really important to clarify that. Just to like zoom out and say a few words about what we just did, because we really kind of raced through this this detailed technical example. Really, what this PanGeoForge recipes library does is it gives us a very concise and hopefully easy to use syntax to represent a rather large data transformation pipeline where we're taking nearly 10,000 netcdf files and combining them into a single ZAR store, and it allows us to encapsulate that entire workflow in about 10 lines of code. So just kind of zooming up and explaining again why we created that library is to make it easier to do that type of workflow. Without PanGeoForge recipes, you may be writing hundreds of lines of code to do this type of conversion and transformation. So I think now, yeah, Charles is going to talk a little bit about how you can. We're trying to make it easy also to run those in the cloud.
Yeah, thanks that's a helpful context, Rachel and Ryan. And I will open up another sharing window, and we'll look at how you would submit these recipes on the cloud. And I guess I'm feeling a little embarrassed that I now, even though I just shared my screen, oh, okay, maybe because I wasn't a presenter. Okay, great, show my screen. I was a little confused. Okay, so here we are. So I'm just going to actually talk you through this process as you would experience it as a user with the user-facing documentation. So before we looked at some slides just to summarize this, but this is all the user-facing documentation at PanGeoForge-forge.readthedocs.io. Just as a recap, the introduction tutorial that Rachel just talked us through is, as you probably have already found, all located here under Introduction Tutorial. See if I can zoom in on this a bit more under Introduction Tutorial. All of the components of PanGeoForge recipes that Rachel just presented to us are discussed in greater depth under the PanGeoForge recipes tab of the documentation here, and there's in-depth discussion of a lot of everything that she just discussed there, including more in-depth tutorials for specific use cases. But what I want to talk about right now is the PanGeoForge Cloud. So I'll just talk you through some of these concepts, and then we'll look in a moment at GitHub where you would submit your recipes to be run on the cloud. So just recapping from our intro slides, a few core concepts. Catalog shouldn't be any mystery what that might be. That's our catalog of data sets, which is certainly in an evolving state as this has just been launched within the last number of weeks, essentially. But data that's built on PanGeoForge Cloud will be reflected in the catalog. And sort of a trend I want to highlight here is that for each of these core concepts, we have the PanGeoForge documentation page here, but also our PanGeoForge website sort of dashboard representation. So this is just pangeoforge.org, and we have a dashboard here that keeps track of kind of the state of the system. So I'll be talking about each of these concepts in the documentation, And there's also a link here that will bring you to the dashboard representation of those things. So as we talked about before, feedstock is as it is in CondaForge, a feedstock is a GitHub repository that's the container for recipes. A recipe run is an individual execution of a given recipe within a feedstock. For these, it might be easy to page over and look at what a recipe run looks like. So if we looked at a feedstock, for example, this was a demonstration feedstock. I'm not sure, maybe it doesn't have any recipe runs on it. Let's look at one of these other feedstocks. So on this feedstock, for example, we have a number of different recipe runs. And for a given recipe run, when we click through, I think we will actually see some logs. These are the logs, the execution logs for that given run. So the actual run itself is tracked here. I'm making a mental note, which I think we have already here, that we should be listing the output destination of the data set there. And as we talked about before, a bakery is the cloud compute infrastructure that we use to execute recipes. There are, as shown by these repositories here, implementations available for all 3 major cloud providers to establish bakeries for PangeoForge. Currently, if you look at the dashboard, we have just a single bakery, which is called Pangeo-Lamont Doherty Earth Observatory, LDEO-NSF EarthCube. So this is our Lamont Doherty Earth Observatory NSF funded bakery. So these are just some core concepts, but the important concept thing to think about here is how would I like to kind of participate in PangeoForge? And that's discussed in the recipe contribution section of the documentation. The first thing to note is that there is a great way to participate in PangeoForge with writing no code at all, and that's to just open a new issue on this issue tracker of the staged recipes repository. So this is also something we've borrowed from CondaForge. Those of you that have used CondaForge as contributors, recipe contributors may know this. We have a repository within the PangeoForge organization called Staged Recipes. And this is essentially the entry point for all contributions to PangeoForge Cloud. A very great way to participate in PangeoForge as someone who's familiar with a particular data set that you'd like to see in cloud optimized form is to just open an issue and add the proposed recipe tag or label rather, and you can see there's quite a number of these here. If we click on any one of them, what we see is a description of the data set, where it's located, some thoughts about how it might be transformed. Here we see Ryan chiming in with some suggestions. There's a number of these, obviously, and you could take your time after this presentation to look through them. But this is a great place to start ideating, to start brainstorming with others about how you would design a recipe for a particular data set and without having to write any code. So this is a great entry point. When you're ready, perhaps you've already done that, or perhaps you want to jump into just writing your own recipe. Essentially, there are 2 required files to contribute a recipe to PangeoForge Cloud. The first is the recipe module, and that's the Python file that contains the components that Rachel just described to us. There's a lot of links in here that in the documentation that can point you back to the recipe docs to figure out how you might write your recipe module. And again, an issue is a great place to discuss ideas about that. The next one is a YAML configuration file called meta.yaml. And the meta.yaml configuration file, we have links here as to what that looks like, and I'll show you an example in a moment, essentially defines the configuration for your recipe, what bakery it will be run on, which for now will always be the PangeoForge NSF, excuse me, the Pangeo-LDEO-NSF Earthcube bakery that we looked at a moment ago. What bakery will be run on, the license of the original data, your name, your GitHub username, your ORCID ID if you have one, etc. So these are sort of just configuration, a configuration for your recipe. And once you have those two files, or a draft of those two files, that's a recipe module and a meta.yaml, you will make a pull request to staged recipes. There's a few sequential steps here for making a pull request, which are maybe familiar to anyone who's done that before. But if we take a look at some pull requests here, just take a look at the first one. We can see that this contributor has added the meta.yaml. So this is, kind of an example of what a meta.yaml looks like when it's contributed as a PR. We have a title for the recipe, a description, a listing of what version of PangeoForge was used to write the recipe, some information about the data provider and the contributor and the bakery again that should be used to run the recipe. And then here is the recipe file itself for an actual recipe for a real data set out in the world. Well, the one that Rachel just showed was also a real data set, but for some data sets are a bit messier to handle. So this one is a few more lines than the one that Rachel demonstrated for us, but still only less than 50 lines. And we have some white space in here too. So this is what that pull request would look like. You have two files contributed. And as described in the documentation, when you've submitted a pull request, there's a series of pull request checks that will be performed. So if we go back to the conversation, you'll see a series of comments by our helpful PangeoForge bot, which is this little smiley anvil character. And the PangeoForge bot is essentially just watching the staged recipes repository for any pull requests that come in and making assessments of their formatting and their structure, and if they meet the expected criteria, the PangeoForge bot will make essentially a test recipe run for your data set so we can start into the testing process. So if you're interested, it's a bit beyond the scope of the few minutes we have left to go into all of those checks, but we have a reference page. It's linked here, and I'll show you also in the navigation tree or the table of contents. There's also the reference page here. So this reference page in the documentation talks in exhaustive detail, step-by-step detail, but very clear. You can look through everything if you're curious that the PangeoForge bot will be examining about your recipe. But if you're not interested in that, all you have to do is just open a PR and the PangeoForge bot will tell you what you have to do next. So in this case, actually, there weren't any points of feedback for a kind of on a structural level. I think this one, for example, if we looked at this, we'll see that, for example, right here, so the PangeoForge bot chimed in immediately and said, I don't see a meta.yaml in this pull request. I only see these files. In this case, it says, sorry, I only want to look for the .yaml extension, not the .yml. So in this case, we had a .yml extension for the meta.yaml, and the PangeoForge bot just said, this is what I see. And then the contributor made a correction there, updated the file name. The PangeoForge bot found another issue, which is that there was a missing field in the meta.yaml, and eventually we moved on from there. So I'll wrap up the PR discussion section here with just the thought that you don't need to know what the PangeoForge bot is going to do before opening a pull request. If you're curious, you can review the documentation here, but the PangeoForge bot should tell you what is needed. And if it doesn't, one of us will chime in and correct it. So I'll just wrap up, and we're about 12 minutes to the hour now, and so I'll just wrap up with another 2 or 3 minutes discussing what happens after the pull request, and then we'll have time for some more questions. And of course, you can put those in Gitter now if you've already thought of them. So what happens? How do we get from a pull request to a feedstock? Again, this is discussed in the documentation. After making a pull request and the pull request checks being performed, we go to creating a new feedstock. So to create a new feedstock, one of the maintainers, it might be one of the people presenting today or someone else, will have made an assessment in addition to the feedback of the PanGeoForge bot that the pull request is ready to merge. Here's an example of a pull request Rachel made. We had a long discussion, you can see here. Once the PanGeoForge bot ran a test of the recipe in the prune form, like you saw Rachel do in the tutorial, and reported back with representation of the X-array data set of that pruned recipe. And we discussed whether or not we thought that was what is how we expected to look. And ultimately, we merged this pull request. So once that pull request was merged, it's automatically created into a new feedstock repository. So you can see that pull request became automatically this repository. And this repository was given a feedstock directory in which the recipe was deposited. Here's the recipe. This recipe is 42 lines. And the meta.yaml configuration was also put in this repository. And from here, the production deployment of the feedstock begins. In this particular case, we're actually debugging that this week. So this deployment has actually failed. But this feedstock can be deployed, and that will bring you to one of these recipe run pages that we looked before. And this is essentially tracking the logs of the full recipe deployment. When one of these succeeds, it would be added to the catalog, which right now is just a very simple plain text list of URLs, and very shortly will be a much more engaging user interface. The last thing I'll say is that, just as I had said in my initial slides, these feedstocks provide a place to discuss the quality of the pipeline, discuss the quality of the recipe, and a venue for improving that collaboratively over time. So it's a very transparent process. And as you can see here, I mentioned we're debugging this deployment. Here is just such an issue discussion. I had posted this here. We're discussing why did this deployment fail, and this is a very long thread, but this is on public GitHub, so you're welcome to chime in if you have thoughts on this today or soon. So that brings us, when we refer back to the documentation, to the end of the contribution cycle, which is maintaining the feedstock. This feedstock can be run once, but perhaps if you have data that has evolved or updated, you can make pull requests to these feedstocks and then rerun deployments of them in response to pull requests to these feedstocks. And hopefully then when you or your colleagues or other members of the community create publications based on these data, you can link back to these feedstocks in that publication and say, and this is the reproducible pipeline that we used to move the data from, let's say in this case, a NOAA server from a known archival endpoint of a particular data set into the cloud optimized format for the data, for the paper, which is a step in the process that's often obscured. So I will pause there. We're a few minutes before the hour, and Rachel and Ryan may have other things they want to share. And we're open to questions at this point.
So we had one question in the chat, either Ryan or Charles, if you want to jump at that one. It's about, is there a way to deal with data sets that aren't directly accessible in archived netcdfs, but are instead by data request through an API?
Right. I'm
Right
reading that
now,
question.
that's not capable supported, but very soon it will be. Right now, we can basically open any data set that Xarray can open through a URL. So that could be an OpenDAP link, a GRIB file, a NetCDF file. But if it is something that needs some special processing to massage into that format, a custom opening hook is required, and that's under development right now. Maybe another thing worth mentioning is yesterday there was a lot of discussion of Kerchunk, which is a tool that makes it possible to access, these binary file formats like netcdf or HDF or GRIB using ZAR semantics without actually converting the data to ZAR. But it requires building up an index of all those files. So PanGeoForge Recipes includes workflows that allow you to build up these indexes using Kerchunk to then build one big virtual ZAR data set out of your netcdf files without actually having to copy the netcdf data to a new format, which I think is something people are very interested in.
Yeah, I've just highlighted, that's a great point, Ryan, and I've just brought up on screen again the location in the docs where you can read a notebook tutorial about how to do that. Our recipe class for Kerchunk is actually called the HDF reference recipe, but that uses Kerchunk for the actual implementation. This shows you how to go through the steps, starting from the file pattern, which Rachel introduced, and beyond to use that recipe class. And there's also a more detailed description of that in the API documentation, if I can navigate to it. Right, the HDF reference recipe is described in more detail here.
So Leaf is asking, we have quite a large intake catalog for a field campaign which uses netcdf files, but none of them in ZAR. It would be really nice to be able to convert everything in the entire catalog to ZAR. Is there something like that which would traverse an entire intake catalog to create a ZAR back mirror? That's a great idea, Leaf. It would be very easy to implement here. But it doesn't work today, but we would love to support that. Another one is from a Threads server. Like if there's a catalog exposed by a Threads catalog, it would be nice to be able to walk that, or a stack catalog for that matter. That's actually much easier than what Rachel showed today of manually putting together this file pattern. If there's a catalog and you want to operate on a specific sort of branch of a tree of a catalog, it should be very straightforward to automatically generate the file pattern inputs from that. So great suggestion.
Just to clarify that, Ryan, I think what you're suggesting is that the intake catalog could be used just in the existing PanGeoForge recipes within a file pattern to extract the URLs?
Either that or have a specific, or we broaden the idea of the inputs such that you can essentially take an intake catalog and that will automatically generate the inputs without having, you could do this, you could code this today inside a file pattern function, but I think there's a more direct path.
Right, that makes sense.
All right. Thank you, Charles. Thank you, Rachel, and obviously thank you, Ryan, for delivering the tutorial. So that also marks my shift, the end of my moderation shift, and I would hand over to Chris Holmes. It's nice meeting. Hey, Chris, how are you?
Thanks so much for all the awesome moderation. I missed most of it because I was asleep, but I heard great things. And
yeah, the sessions over there in my afternoon, which would be night for you, they were also great.
Awesome.
I gotta go now, and thank you for the opportunity, and I hope to see everyone in NuGetUp. Bye.
Thanks so much. Cool, and I'm gonna hand it over to Joanna to be the moderator for this next session, and I think she'll introduce Javier de la Torre.
All right, thank you. So welcome everyone to this session about Cloud Native Vector. I think it's a very promising session with packed of lightning talks. And we are going to start with Javier de la Torre. He's going to have a 10-minute talk to kick us off, and he will tell us about the race towards a fully native geospatial cloud. So over to you, Javier. I think we cannot hear you. I'm not sure if you are talking.
Can you say something, Javi?
Sorry, yeah, just trying to figure out in GoToMeeting. Can you hear me now?
Yeah.
Yes, we can hear you. Yeah.
All right. Well, then give me a second because I'm still also new to this GoToMeeting, so trying to find my way to share the slides. But can you guys see my slides now?
Nice.
Yes, we can. Yeah.
All right, great, 10 minutes. Great. Well, hi everybody, and thank you, Joanna. Very glad to be here. Thank you, Chris, and everybody for organizing the session. My name is Javier de la Torre. I'm the founder of Carto. My talk today is going to be on the spatial cloud data warehouses, something that I'm very passionate about. As you will see, also for some reasons of what we do at Carto, but also because I believe this represents a huge opportunity to rethink how we do geo on the cloud, and it opens a ton of opportunities to bring many more users to our community, which I think in the long term is what excites me the most, is to see our community of people that get to understand the power of geo and use it on a day-to-day. So, but let's get started. I was asked, because I might not be familiar to everybody, in our industry and for others, start by talking a little bit about what is the concept behind cloud data warehouses. There's many terms that you can find on the web around cloud data warehouses.
Sorry, Javier, I don't know if you want to put it in presentation mode, or is it intended like this?
I just don't think I can.
Okay.
Because
okay.
of
no worries.
is it
Don't
more or less?
We can see it. We can see it. Yeah.
Sorry about it. It's the GoToMeeting privacy settings on a Mac and the nightmare of permissions. So if this works, that's great. So let's start, with a little bit of, what are these cloud data warehouses? I'm sure that most of you are familiar with at least a few of the logos that I'm putting in here of some of the commercial products. But I mean, you will find the cloud data warehouse defined in many terms on the web, from data warehouses to data clouds to databases to data lakes to many different ways. But in essence, I mean, they are think of them, like databases or data warehouses that are optimized for analytical purposes, right? And there has been, over the last, I would say, probably 6 years, a huge revolution on this space, where now we're starting to see more and more products coming that heavily benefit from cloud technology. The same thing that we've been talking over these 2 days around cloud capabilities. Well, so these products are the next generation of data warehouses that really liberates the cloud capabilities. As a reference, there's a few leaders on the market. Obviously, the cloud vendors themselves are very strong players there. Each of them have one or more cloud data warehouses products that they offer on their own. AWS has Redshift, but it also offers Athena and a number of other products that could be categorized in the same space. Google Cloud has a very big proposition around BigQuery. Azure has also multiple products, but Synapse Analytics seems to be also what they are like surrounding around themselves. And then there's two products on the, again, on the commercial landscape that are really kind of growing very fast, which is Snowflake. You probably heard, one of the fastest growing enterprise software companies recently, and Databricks, which you probably are very familiar around the Spark ecosystem. And those two, Snowflake and Databricks, work on multiple cloud. So they're cloud agnostic or cloud independent, right? So this is the thesis. Then there is a lot of other open source projects that I can mention, that also fall within this space. But I think it's fair to say that the rise of the data warehouses is mainly driven right now by the commercial providers attached very much to the cloud vendors and the relations they have with them. And this market is growing now like crazy. It's probably like one of the fastest growing segments on enterprise software that you can find. I mean, like you've probably heard of like a Snowflake IPO and the valuations and so on. But so it is, like on any kind of company that is kind of pushing on this segment is benefiting a lot. And the reason for it is that they're seeing massive adoption from users. These products are really attracting a lot of users to rethink the way that they do analytics on their organization. From my point of view, they are really responsible for, in a way, democratizing or making accessible the power of cloud, scalable cloud computing to many more to many more people than it's been previously before done. So just for you to get an idea, this is how they look like. They look like databases. So this is BigQuery on the top left, Snowflake right, Redshift, and Databricks. They're essentially kind of like they now there's a very clear trend towards like exposing, as we would talk, a SQL interface where you essentially operate with them in SQL. Some of them, like Databricks, come more from also like supporting Python, Scala, as within the Spark ecosystem. But now also Snowflake is adding Python support to interact with them, and so the others. And these products are competing now like crazy, and they're like doing feature matching all the time. So what you see on one is coming to the others, etc. Now, why they are so popular and why it's so important? The first is that they provide huge benefits to users because of the usage of the cloud. So a lot of them, you're probably familiar with them. The scalability is obvious. These products allows you to essentially they can parallelize and utilize depending on the product, but most of them, like in a serverless kind of capacity, they can open up servers and and increase the capacity for analytical workflows. And you get the scalability in some cases running thousands of machines at once, right? To run your queries or to run your analysis, right? That's one. So scalability is very big, and it's a scalability, accessible scalability. You don't need to create a map reduce work. You just write SQL and it will take care of all that. So that's a massive advantage. The second one, they're pretty cost effective. And this is a very, very important factor when we're talking is storage computing separation. The fact that you run SQL, but the data is not in memory, it's not in your RAM or your it's not like a PostgreSQL database, if you want to say. It actually, the storage is in the cloud storage, S3, Google Cloud Storage, Blob Storage, etc. And we will talk a little bit more about it. But that essentially means that when you are not using the data, when the data is only just sitting there, without being used, you're paying only a storage cost at cloud storage prices that is very, very competitive, right? So that's a huge, huge cost-effective benefit, but also it has other implications. I'll talk about data multi-tenancy. These first two, I think, are pretty well known. Data multi-tenancy might be less known, but it's a huge benefit that they provide you. I'll go over it. But essentially, they provide data sharing between different users in a very, very effective way. And then finally, they are essentially becoming very kind of like central points to a lot of data workflows, so they enable a lot of interoperability. And I'd like to talk a little bit about them. But I will do it on the context of Geo, because this is really what is exciting. Over the last 4 years, we've seen like many of those products starting to add more and more spatial capabilities to them, right? So BigQuery was the first kind of main next generation data warehouse that added the spatial support. Then came Redshift, the Snowflake, and pretty much now all of them have some support of a spatial capability in the form of a spatial functions, right? And one of the things that this enables, it's going back to, to the point around data multi-tenancy, is that this computer storage separation is enabling what we call the world of data serves. It's like we all live in a single database. I have my database on one of these cloud data warehouses. Let's think about saying something like a Snowflake, and I can share a table with another user in the concept of something called data serves. And of course, since my data and the other user are also on the cloud, we essentially, it's a logical serve. There's no data transfers. And that's a huge change on the way that we think about distributing data. So I like to put this concept of, like, I really like this, it's very pseudo SQL. But think about, like, you have your own data and you need to do a SQL where you're joining your data with 3 providers and you want that data to be always updated and you don't want to do ETLs. This is possible in this kind of like ecosystem with the concept of the data source. And this is what we call I put in here, and this is very nice connected to later. Joris is going to be talking, but one of the issues that we had with this is that these data sets and this concept of storing the data on cloud storage and then using it from these computing engines, from these data warehouses at the top, was already possible, but was not possible on Geo. And for that, we needed another piece of interoperability that we've been working now for quite a bit of time, which is GeoParquet. Chris, Joris, and a number of people in many organizations have been working on this, which is how we can make geospatial support in the Parquet format, which is a very well-known format supported by all these data warehouses, so that providers like Carto, Foursquare, Planet could potentially publish their data sets on these GeoParquets, and then you can use them directly without necessarily moving into your place, directly in your same SQL as I'm describing. This is one of the core advantages of having interoperability at this level. That I believe alone, it will be a huge game changer in the way that we think on Geo. But that's not only the only one. I was talking about also SQL, right? SQL being, like this power for interoperability. SQL is really becoming the lingua franca between on the world of data analytics, and probably it's because of the rise of these type of data warehouses. So now you have like products that do ingestion, preparation, transformations, enrichments, all of those, all the steps that you can think of almost on data analytics. Now there's products that do that through the use of SQL. And what this means that now suddenly you have a lot of interoperability because of products, because they're just using that as the same like language for passing from one place to another. And now going back to the spatial, well, the capabilities when it comes to Geo are growing really fast. So PostGIS obviously is the most mature kind of like database system, if you want to say, with spatial support. But Redshift, BigQuery, Snowflake, they are all like competing a lot to try to add more and more spatial capabilities. So it's just becoming better and better every day. In fact, actually part of that, one of the things that's just gonna wrap up in there, we do create an open source product that has also a commercial component, but like it's called the Analytics Toolbox, where we're trying to advance actually the capabilities of these data warehouses into.
Sorry, we are coming to the end of the time. I mean, if you could just wrap up.
That's the last thing I wanted to say. So
okay,
it's actually
excellent.
open source. You can go to the Space Station finding. Thank you very much.
Oh, that was great. Thank you very much, Javier, for this presentation. And I think we can take some questions in the end. Chris just posted the link for the Gitter shot. So now we're going to move to our next speaker, and it's going to be Joris van den Bosch from Voltron Data GeoPandas. And he's going to tell us about the GeoParquet, which is something that Javier mentioned just now. A columnar format for geospatial vector data using Apache Parquet. So over to you, Joris.
Yeah. Can you hear me?
Yes, we can hear you.
And do you see my screen?
Yes, we can. Yeah.
Because I don't see it myself, whether you see it. Okay, so that's great. So I'm Joris van den Bosch. I'm working at Voltron Data on the Apache Arrow project. But for the geospatial part, I'm also one of the maintainers of GeoPandas. So for time, I'm going to skip this and get to the actual topic about Apache Parquet. So to know what GeoParquet is, we need to know what Apache Parquet, the file format, is. I pasted here the explanation from their own website, and let's go through it part by part. So to start, it's maybe not super clear, I'm highlighting something, but it's an open source file format, so it's an open specification, and a language agnostic file format. So there are implementations in multiple languages. In Apache Arrow, on which I'm working, we have a C++ implementation with Python and R bindings, but there are also Java implementation, there is a Rust implementation. It's a column-oriented file format. Maybe also to mention it's a binary file format, and column-oriented, meaning that the data are stored by column, or at least by chunks of a column, and are therefore also well suited for heavy analytical workflows. It has some very advanced data compression and encoding features, with the result that it can produce very small files, which can be beneficial to reduce I/O and data transfer, but still efficient to read those data. It also handles complex data, so it has support for various data types, but not only the standard data types, but also nested data types. I think lists, maps, structs. So if you have a nested JSON structure, that's something you could also convert and store in Parquet data. In summary, it's a widely used file format. It's originally from the Hadoop ecosystem, but nowadays it's used outside of that as well. It's widely used to store large amounts of data. I think the typical data lakes, typically for as the starting data for analytical workflows. And it's also a format that is well suited for the cloud. So that's where GeoParquet comes into the picture. We have a useful and widely used file format for tabular data. Vector data often comes in a tabular format, so we can match those two and try to store geospatial data in Parquet. And that's what the goal is of GeoParquet. So we want to standardize how we store such geospatial data in Parquet to ensure that the different tools that would use Parquet, that we ensure that there is interoperability between the different packages, cloud data systems, and that we can also push such a column-oriented file format into the geospatial world. In the end, GeoParquet is just a specification how we are going to store geospatial data in Parquet files. Parquet is an existing file format, an existing specification. So what our own GeoParquet specification adds on top of that is we specify how we are going to store the geometry data, which data type to use. Currently, we store the data as well-known binary, so as a binary column. But in the future, we can expand on that. And in addition, we store a bunch of metadata. I will directly show an example of that. Some of the features of GeoParquet. The first few are related to the actual, to the geospatial part. So in the metadata we store. So we store information about spatial reference systems. So you can have multiple spatial reference systems that can be used. So it's not limited to a single coordinate reference system. You can have multiple geometric columns. We can specify whether you have planar or spherical coordinates. And there are some additional features, I already mentioned them before, I think, that are more specific to Parquet. So you have very good compression, good at really heavy analytical processing, And Parquet files are often used in partition data sets, so where you have many Parquet files in a certain layout. It can also be helpful for when reading subsets of the data. So some things that make Parquet very suitable for such analytical workflows. So you can have partitioning, but in addition, Parquet file format has a lot of statistics at different levels, which make it very efficient to read only part of the data. That's for standard columns. That isn't yet working for geospatial columns, but that's something we want to do in the future. And there is also a talk, I think, just after next to me. Here's a small example of how the metadata looks like. So for a certain column in the file, we store a bunch of metadata, so about the bounding box, the coordinate reference system, which encoding is used, the number of geometry types. I'll go a bit quickly. So I'm personally myself already using GeoParquet, or at least Parquet, for a while in GeoPandas. Afterwards, there was also an initiative started in the OGC repo. So with, amongst others, Chris Holmes and Tom Augsburger worked on an initial version. But recently, with some help from a lot of people, so I listed here some of the project and companies involved. We released an initial release last month, and yesterday a second release with some additional features. But very important to note is that this is work in progress, so feedback is very welcome. Some future work that we want to do on this is that, yeah, expand the support for the format so that more tools are be able to work with it. GDAL in the master branch, there is actually already an implementation which will come in, so the next version of GDAL. There are some Python and R tools that I already mentioned before, but there are also some other talks after me that will tell some more about other tools or software systems that start to support this format. We certainly want to work on spatial indexing. Another talk is coming. There is an option to go beyond the well-known binary to have more efficient storage of the vector geometries using the GeoArrow specification. And of course, we need to stabilize the specification. Maybe just as a small last part, so very small benchmark, just to give you some idea. Every benchmark is flawed, so you can do this in many ways. I use Python here, so you get a lot of overhead from using Python, so it takes some caution with those numbers, but small comparison of the example data set that is linked from the README from the GeoParquet repo. So it's a polygon data set. So there's a small comparison of the file size compared to GeoPackage. I just compared to GeoPackage here. So you see that GeoParquet gives a much smaller file, which can also be read faster. Now, again, this is using Python, so you have the overhead from the conversion from GDAL to Python in case of GeoPackage. While for GeoParquet, I'm directly using the Arrow project that will efficiently read the Parquet format without going through the row-oriented internals of GDAL. And especially if you select a single column, you see even a bigger difference, and that's where the column-oriented nature of Parquet especially shines. Voilà. That's my presentation.
Okay, thank you. Thank you very much, Boris, for this presentation. And remember, you can post questions in the Gitter. So we are going to move to another presentation about spatial indexing in GeoParquet format from Eugene Saipish from Azavea. I have no idea if I pronounce your name correctly. Eugene? Okay, not too bad. You're very kind. So over
Give
to
me
you,
a second as I enable permissions. I will be right back.
Okay. So in the meantime, Joris, while we have you there, when you converted from GeoPackage to GeoParquet, did you manage to preserve everything, or did you actually miss some of the features, some information?
Yeah, for this specific data set, I'm not super aware of possible limitations regarding data types for GeoPackage, but the data set included some strings, some integers, and a geometry column, and that's features that both support. So in this case, both files are equivalent.
Yeah, it was a very impressive benchmark.
Okay. Is everything hunky-dory?
Yep, we are good.
Awesome.
Yeah.
All right, let's try to keep this lightning. So this is a talk on spatial indexing in GeoParquet. Big disclaimer is that this is very much a discussion in progress. Hopefully this will be a nice on-ramp. If I say something that is untrue or I miss something, it's probably because I don't know better. So that's the issue number. Yeah, okay, so let's recenter ourselves. The problem we have is that we have this nice cloud-native data format. We want to store vectors in it. This is very much like write once, query often type situation. The reason shapefiles aren't good enough is because you can have hundreds of gigabytes of data. And really, the focus here is to make something that's portable across languages, ecosystems, so kind of like the least weird. And the implication is if we're going to be publishing hundreds of gigabytes of data, it probably would be good to be able to efficiently select it spatially. And that just means by bounding box of geometry. In practice, this always ends up being a filter in two steps. The first filter is just a filter by bounding box that discards a majority of your data set. And then there is a refinement after the geometries have been read in memory to do the actual geometric intersect, use spatial predicates, fancy stuff, expensive. So in order to support that, we kind of have to have a couple of components in place, right? We have to have our data in chunk format so we can discard large parts of it. The data that's spatially located has to be written together. That's kind of not what I'm talking about here, but it's a major assumption that this has happened. So it would be legitimate to discard large chunk of the data set. And there has to be spatial metadata that we can use to discard chunks without looking at them correctly. So our model is super simple. We are storing features in a table. There's a geometry and attributes, simple features if you like. GeoParquet supports storing more than one geometry column, but for purposes of this discussion, we don't care because we can only index on a single geometry. So let's just go with this model. So yeah, a lot of what we need is already just in the Parquet format themselves. So this is slightly simplified version of the Parquet layout on disk. And let's just talk through it for a minute. So we have chunking on 2 dimensions. Rows are chunked in row groups. That's the purple box. And these things we assume are going to be spatially collocated. And then the attributes are chunked by columns. This is what we mean when we say that this is a columnar format. So all the geometries are written together, then all the GUIDs and names that you don't see, and so forth and so on. And at the bottom of the file, we have a footer. This is actually how we route when reading the file to the part that we need. We have the schema, we have a place to shove extra key value metadata, and we actually have the offsets, right? So that's nice. We're focusing here on WKB, well-known binary, because this is the most portable format. And I guess like this is one file, but one file will typically be between 32 to 128 megabytes. So actually there could be, you know, a dozen or hundreds of these things somewhere. So GeoParquet, how did we make this geo? The same way that we did with the GeoTIFF. We just added some geo metadata that qualifies the geometry. We know what projection it is. We know what kind of encoding it's using, whether it's planar sphere or planar or spherical geometry. And we can actually put the bounding box right there in the metadata. Is that our way to spatially filter this? Well, unfortunately not, because that's just nowhere near selective enough. Even like a 32 megabyte file, which would be a single Parquet file, can have tens of thousands of geometries, depending upon how big it is. I made that number up, but the point is that in order to read them, decode them, and do the intersection is still prohibitively expensive, experiment shows. So we have a couple of options to actually implement a spatial index. One is using space filling curves. This is like very popular. This is what GeoMesa, GeoWave, lots of databases do. Space filling curves are things like Hilbert, Z2, S2, lots of others, I guess even H3. I'm going to argue that this is kind of inappropriate for use cases, because what you do here is you intersect your geometries with some kind of recursive grid, and you use the IDs of the grid to do your indexing. So the point is that unless you're storing points, you're inevitably going to end up in the situation where your geometry is associated with two cells that often ends up being data duplication. And the math of actually trying to use these indices is like super weird and does not like requires its own support library. So this flies in the face of keep it simple requirement. So I'm going to say we don't want this. It's wildly inappropriate. Second option that we have is let's use the key value metadata that we have per column chunk, you know, kind of like the row division of our data. This would work, but this would require us actually changing the way that the filtering happens, actually changing all the Parquet clients. That's a lot of work across a lot of projects, probably not a great first start. So now we're down to either adding a column, basically now we're down to adding a column or using some sort of native geometry format. So adding a column that simplifies the geometry in a way that Parquet can understand, in a way that Parquet filters are able to understand is what we're talking about here. So in our mental model, we just say, great, there's the geometry, it's complex, it's bytes. We cannot express any kind of predicate on it using the existing Parquet libraries. But if we express a bounding box as an X and the Y column, these are primitive values and we can filter on these. And the story actually gets much better with this approach because the Parquet format already has the support for storing stats for the minimum and the maximum value for primitive columns in the footer. This is the part that is read first. So your predicates are now being evaluated before the column chunks are being read, and that's filtering, right? That's kind of like your actual mechanism. It actually gets a little bit better as of 1.1. It also stores stats for pages. So there's kind of two levels of filtering. That seems good. Yeah, I guess you only have to do this once during write. It's like a little bit unfortunate that you're introducing data into the data set, but what you get is quite powerful. And this works, and we'll talk about that in a second. But the really neat thing about it is this data structure maps very neatly onto the idea of an R tree. So in the data layout, the column chunks are composed of pages, files are composed of column chunks. And of course, spatially, the bounding box of a column chunk is the bounding box of a page, and the bounding box of a file is the bounding box of all of the column chunks.
Eugene, we are coming to the end of the time, so if you could.
Oh, okay. Yeah. Great. So this works. Actually, Grigory Pomachan implemented this and ran with this in Cartospatial extensions, testing this on 10 million polygons versus reading this on the CSV that ran for 60 minutes. The same kind of full scan for Parquet runs for 4 minutes. And using this bounding box filter with the push down predicates takes the query down to 1.5 seconds. I'll say one thing is that you can do this. This isn't great for points, and perhaps you can do even better if there was a Parquet native way of encoding geometries. Which is already being discussed in GeoArrow and kind of requires on splitting the X and the Y column in order to be able to do the same filter on X and the Y. So I guess with that, I will stop.
Thank you so much for your presentation, Eugene. And we'll give the floor to our next speaker, Kyle Barron from Foursquare. And he's going to tell us about the potential of GeoParquet and GeoArrow on the web. So looking forward to hear this.
Can you hear me now?
Yes, we can. Yeah.
Cool. How do I share my screen? Which button is that again?
You'll get some buttons magically appearing.
Oh, it is magically appearing.
Yeah, you're sharing your screen now.
Okay, cool. So I decided, or thanks for having me. I want to talk a little bit about GeoParquet on the web because I think that Parquet is a really great file format for bringing analytical vector data onto the web. So today I wanted to try something new instead of having slides, trying to do something in an observable notebook to have a little demo at the end of the same notebook. And I posted the link in the Gitter as well. So I believe that the web is really the future of geospatial because unlike historically when applications had to be installed on a desktop, it's a lot easier to install a web application. You just go to the website and it's possible to get really good performance using modern tools like WebAssembly and WebGL. But in order to use a lot of, like for geospatial web apps, you want to support a large amount of data. And pretty much any time on the web, because the browser can't access files outside of the browser sandbox directly, you need to download the data from a server to the front end. But this is almost always going to be the limiting factor for large data because the bandwidth speed is much slower than the CPU, than the memory. So anything that reduces how much you're downloading is going to make the web application more responsive. And I think there's really 3 techniques here that are really valuable. And the first is better compression techniques, that if you can spend a little extra time on the server and a little extra time on the client, packing and unpacking your data, if you're able to save a lot of time by downloading less data, then that's worth that extra cost to pack and unpack the data. The second is if you just need less data. So that's one way of solving that has been tiling, like vector tiling. But when you vector tile, you essentially take a snapshot of your data. That's a lossy way to compress your data, and it's hard to do analytics across neighboring tiles. It gets a little messy. You're only loading the data in your viewport, so it's harder to do global analytics using your data. Spatial indexing, however, is a really great way to require less data if you only want data within a certain bounding box. A third way to make the map more responsive is to stream the download so that you can start rendering the data before it's finished downloading so that the user makes it seems more responsive to the user. They don't have to wait until the entire, let's say, 100 megabyte file has downloaded before you see something. Now, I think Parquet really is a great fit for each of these 3 points. So Parquet supports not just compressions, but it supports encodings, essentially rearranging the data so that it compresses even better. And you see that in most Parquet benchmarks, that the Parquet file will be smaller than almost any other file format you can test. Requiring less data, Parquet is also has the potential for, because Parquet supports partitioning, as you've heard in the last talk. So if we can store the metadata in this way, then the client doesn't need to download the entire data set. And similarly, because there's Parquets in a block format, you can stream the download and potentially render the data before all the data has finished downloading. Now, some formats recently have achieved similar similar features. I think especially flat GeoBuff is a brilliant specification, but we've seen that cloud-optimized GeoTIFF has really succeeded in the raster world, and I think part of that is that it's been able to build on top of all the existing tools that supported GeoTIFF and TIFF images. And so I think that Parquet has an advantage because, as we heard from Javier, the entire ecosystem is already built around Parquet. So if we don't have to work upstream against the current to build all these tools for Parquet, as long as we just have to update them to support geospatial data. So I'm really excited about bringing this to the web. Parquet is a difficult format, so historically JavaScript implementations have been abandoned, but I was able to use WebAssembly to create a JavaScript library to read and write Parquet using the Rust implementation of Parquet. So here, this is a quick demo. First, a disclaimer that the loading has been optimized. So here, this GeoParquet file is only 13 megabytes compared to an uncompressed 210 megabyte GeoJSON. However, I procrastinated till last night, didn't make this until last night. And so it currently unpacks to GeoJSON for rendering. So this is a slow way to render the data, but it at least shows the potential that if you're able to load the data in GeoParquet, you're really working on the performance of loading the data. And then the next step is keeping the data in a binary format on memory and rendering the data faster. So this is a 13 megabyte GeoParquet data set compared to a 210 megabyte GeoJSON that renders here onto a DecGL map. I think I'm close to time, so I will end my talk there.
Yes, you are. Thank you very much for your presentation, Kyle. So we're gonna move to our next speaker. It's going to be Mo Sarwat from Where Robots, and he's going to tell us about GeoParquet support in Apache Sedona. So over to you, Mo.
I think it's a video.
Maybe he's not here.
I think there's a video to play.
Ah, okay. So here is the video. If you want, maybe we can move to the other talks while we sort this out to not miss more time.
Yeah, sounds good.
Okay, so I think, so if we can go to the next talk, which is cloud-native formats for planet-scale vector tilesets from Marcus Tremmel. Marcus, I see you're here online. Are you able to share your screen?
Yeah.
Excellent.
Just a moment. Okay, can you see my screen?
Yes, we can. We see a terminal.
Okay, just a minute. Okay. So now you should see my presentation. Huh?
We see it. We see the presenter screen with the notes. So I don't know if you want to share.
With the note, then I change. Okay, so now it should be fine. Now.
Yeah, no, it's fine. Perfect.
Okay, so yeah, hello everybody. My name is Markus Strömmel, and I work at a company called Rohde & Schwarz. And today I want to talk about why, in general, there's a need for a cloud-optimized tile archive for global scale tile set. And I also want to give you a short overview of how such a tile set archive basically could look like, based on a case study I worked during the last few months, and I already successfully used in some projects with significantly reducing the storing process. Okay, so if you want to deploy a global scale tile set in a cloud-native environment with current technologies or tools without the use of a cloud-optimized tile archive format, you probably have two major options. The first option is you could use a backend with a database where the tiles are stored, and also then you can use a tile server for providing the tiles to a map client. Then there's also a second option. You could also directly host the map tiles on an object storage. The problem is that both options have major drawbacks. In my opinion, in general, they are both unnecessarily expensive, especially if you're hosting large amounts of tiles. So if you're hosting global scale tile sets. So we have faced these problems in our projects and in our products, and because of this, I started to work on a solution which I call a cloud-optimized tile archive for planet-scale tile sets. And so I would call it something like an MB tiles or a geo package for the cloud. And the archive format is very similar to other cloud-native formats. So there is a data section where the actual tiles are stored. For example, there can be raster or vector tiles with focus especially on vector tiles. And then there, in addition to the data section, there is a metadata document which describes the structure and the layout of the archive format. And then there's also an index which is referencing the tiles or the position or the offset of the tiles in the data section. For describing the content and the structure of the tile archive, there's already a good standard in work, which is called the two-dimensional tile matrix set and tile set metadata specification of the OGC, which is currently a draft, but which also fits very well for describing cloud-native tile archives. And this standard has to be extended with additional properties about the index layout. For example, if they on which space filling curves they are, or which space filling curves is used. And then the most time I spent on designing the index, and I ended up with a workflow like the following. So if you open up the map and then there a compressed tile pyramid is loaded with the initial fetch along with the header. At global scale tile set, we are talking about zoom level 0 to 7. And then when the user zooms more into the map, it turns out that compressed tile pyramids are not that effective for lazy loading portions of the index. So I switched to a different approach, which I call index fragments. And index fragments are simply an aggregation of index records with a default of 4096 index records aggregated together. And then for efficiency, these index fragments are ordered on a space filling curve, for example, Hilbert or in set order. And with this approach, most of the time, only one additional prefetch per zoom level is needed before accessing the actual map tiles for the current viewport of the map. And I would say this is clearly, or even not all, noticeable for regarding the user experience. So if you're hosting a ComTiles archive on a CDN, we're talking about in a medium internet connection about 20 to 30 milliseconds for fetching that fragment. And because of why the tiles are ordered on a space filling curve, you could also then batch together the tile request to, on the one hand, to improve the performance. This works for HTTP1 requests, but in particular to reduce the storage cost, or to more precise, the transfer cost. And this can reduce the number of tile requests by about 90% if you use that batching feature. Okay, and then one final thought. I think there are a lot of standards out there in the OGC which are standardizing stuff like with tiles. For example, there's WMTS or GeoPackage, which evolved from MB tiles. And there is also the new API standard, which is called the OGC tiles API standard out. But I think there is still missing a standard for cloud optimized tile archives. There are a lot of cloud optimized formats out there. I think the most used is probably PM tiles and also ComTiles, which I showed you today. Both show that this is working and can reduce the cost of hosting tiles in the cloud. And because of this, I hope there will be some future work on, or a working group on working on this stuff for having a standard in the future. Yeah, thanks.
Thank you, Marcus, for your presentation and also for keeping the time. So I think our next speaker is, or our previous speaker is here now, Mo. So I think we can give you the screen. We cannot hear you. I don't know if you're trying to say something. No, we cannot hear you.
Hello?
Hi, yes.
Okay, good. Thank you. So let me just share the screen real quick. Again, I was in the beginning. I was here in the beginning of the session, since the beginning of the session, but I was not added as a presenter, so I apologize for this.
Not your fault. It's our fault. Sorry about that.
Yeah, no worries, no worries. The problem is that
you got to restart.
To share the screen, I have to.
Yeah.
To share the screen, I have to quit the application.
So maybe we can. I mean, we have Norman. We have Norman online. So maybe we could, in the interest of time, we could go to the last presentation. Norman, would that be okay with you?
Or we'll at least test his.
Sounds good. I'll do
yeah, that works for me.
Yeah, I think that's right.
Okay, so we'll have Norman Barker from TileDB. He's going to tell us about cloud-native vector data with TileDB.
Great, thank you. I'm just going to share my screen. Thank you for having me. So you should be able to see my presentation now.
Yes,
I'm going to make it. Yeah, I'm going to make it full screen.
Cool. And we need to keep things to 5 minutes to not get.
Yeah, I'm going to be exactly 5 minutes. So okay. Yeah, let's get started in the interest of time. Thanks, Chris. So I'm going to talk about a little bit about who TileDB is, because I don't think many people in this audience know. So we were originally spun out from MIT and Intel Labs in 2017. We've raised over 20 million from world-class investors. And we're currently about 45 people strong in the company. We have a lot of traction in geospatial, telecoms, and farmers and hospitals and other scientific organizations. What is the actual problem? Well, organizations are drowning in a data infrastructure mess. They just have too much data, too many different data sources. You know, SQL, we talked a little bit about Parquet, shapefile, geotiff is just too much to handle. And there's too many domain-specific file formats. Everyone's recreating the file format. And so we want to focus more on APIs and having a universal data engine. What does this result? This mess results in low productivity for data analysts and scientists and a huge total cost of ownership for organizations. So what's the secret sauce? Well, with TileDB, you can model everything as a dense or a sparse array. So dense is raster, sparse is like geometries and point clouds. So we're going to go into more detail in a second. So we have data frames. We have a column store. TileDB is a column store. Sorry, someone just took over control. There we go. So we have TileDB as a column store. You can see that at the top, and that maps down into a sparse array and a dense array. So what are the examples? Well, table, LiDAR, SAR, 2D and 3D, so spatial temporal data, time series, and weather and video. TileDB embedded is completely open source. It's built in C++. It's fully parallelized, so very, very fast for read and writes. It's a column format, supports multiple compressions, so you can compress each column differently. And we also already have spatial indexing built in, so we have R trees for sparse arrays. We have many, many APIs in like R and Java, C#, C++, and Python. And we also support updating and versioning, so we have multiple writes with lock-free, and we have parallel readers and writers. We also allow you to go back in time, so once you write to an array, you go back to a previous timestamp. So master data is stored as to a 3D sparse array, so temporal data. I gave a webinar last week on how we work with SAR data, which is complex data, which is spatial temporal. We allow cloud natives to read and write directly from cloud storage, so Google Cloud, Amazon, or Azure, for example, and versioning and time tracking. Let's move on, because we're in the interest of time, onto the actual sparse implementation. So point data, we've long had support for point data, so like LiDAR data, for example, in TileDB. And we allow native float indexing. We have visual indexing with R trees and Hilbert curves, so space filling curves. We have cloud native, so rapid reads and write, versioning and time tracking, and we also support schema evolution. So you can evolve the schema over time, so you can add attributes to your data. You can add columns to your data if you need to. We also have integration with both PDAL and the point cloud library PCL. So how do we do geometry data? So we saw that GeoArrow added a random binary geometry type to their schema. You can do the same thing in TileDB. So you can see that we have an initial implementation already in GDAL. So I went through Evan's merge yesterday, and I was made to copy that into TileDB. We have the same benefits as the raster driver that already exists in GDAL. So you can read both geometries and points and rasters through one API. We're cloud native, we have versioning and time tracking, and we have spatial indexing already built in. And more importantly, the metadata is maintained, so you have a direct one-to-one from the source to the destination. Sorry for the slightly out of sync here on the bullets. So how do we do the spatial indexing? So we have the concept of envelopes and centroids and storing the XYZ. So we already know to store the XYZ directly in the TileDB array. So we already index directly on native coordinates. And the way that we do spatial indexing for geometry as opposed to points is that we store the maximum distance from the geometry centroid to the boundary of the geometry. And we store that as metadata. And that's one fixed value in X, Y, and Z, or X, Y, Z, and T if you wanted to. It's computationally faster just to store the center point of the geometry bounding box. And then we already buffer the bounding box query that we make, the rectangular query, by half the bounding box every query we make. And then when you get the results, we filter on every geometry. And we maintain an interoperability with PDAL and also like AIS, so vector location data for point clouds. So you can see down here on the bottom right, we have a diagram. We're going to make an ellipse query here as a geometry query that we buffered from a point. We see all the geometries inside. We actually query on the bounding box, and then we buffer that bounding box by slight amount. And then on the result, we filter it. And this is very, very fast. We already archive like 10 years of AIS data, and we query that data within a couple of seconds. So what's next? Well, what are our results? We initially tried to be interoperable with the Apache Arrow layer in GDAL because we already have an Arrow adapter inside TileDB, so you can go from Arrow to TileDB and back again. But actually, it was just easier just to go directly with TileDB code. So we have an invitation within GDAL. I'll be issuing the PI this week.
Norman, excuse me, we are coming to the end of our time, so we'll just wrap up.
Yeah.
Thank you.
Yeah, thank you. So geometry specifying stores WKB. We support schema evolution, time tracking, and versioning. And we also allow spatial filtering and indexing. And more importantly, we have one API for rasters and geometries. So the future, we're going to have benchmarks for cog and vector. And then we're going to have a 3D geometry library built into CloudDB, which will be open source. So right now, mesh geometry queries are 2D. We want to extend this to 3-dimensional. And we're going to have enhanced browser visualizations. And yeah, with that, thank you for your time.
Thank you very much, Norman, for this presentation. And we are coming to our last presentation. So I don't know if Mo is already back here. Maybe he's not as a panel speaker.
Yeah, can you make him a panel speaker? He probably has a new. Hey, Tom. Sorry, we're going a bit over on the previous session. So.
Can you guys hear me?
Yes.
And see me? No.
Yes.
Can you see me? All right. Cool.
Yes, we
you
can
see the
it.
screen.
Yes.
Perfect. That's cool.
We ask you to be really brief with the presentation because we are.
Yeah, absolutely.
So,
my name is Mo Sarwat. Yes. Can I keep? Yeah. My name is Mo Sarwat. I'm associate professor of computer science at Arizona State University. I'm also founder of Wherebots. So without further ado, let me just tell you just a little bit about Wherebots. So Wherebots, like in our vision, is to enable every organization to be geospatial driven. And our mission is to democratize geospatial analytics by becoming the OS standard for scalable geospatial infrastructure. As you see on the right-hand side, we use that using our open source software, Apache Sedona, which is again software for open source software for processing geospatial data at scale in modern data infrastructure. Again, this is the wrong forum to motivate geospatial data, so I'm not going to talk much about that. But the idea here is that geospatial data is not a specific data type. Geospatial data, any kind of data can be related to space and time, and hence geospatial analytics apply to any kind of data type. The geospatial data market is to reach $300 billion, which is actually huge by 2030, and we have a lot of opportunity here. There are so many use cases beyond the traditional use cases from the past. So many tech companies, so many transportation companies, and the government sector also is really interested in geospatial data and is already doing geospatial analytics. The main theme we've seen with users is that they do a lot of extract, transform, load operations on big geospatial data. They run a lot of geospatial operations like spatial geometry. Also, the geospatial pipeline is a complex pipeline deployed on the cloud or on premise, but in a cluster setting for scalability. So to show here in the stack, if you look at the stack here, can you still see us?
Yes, we cannot see your presentation though. We see a browser, I think.
You see a browser?
We see your desktop, and there is a.
Okay.
Okay, now we can see it. We can see it. Yeah.
Okay, perfect. If you look at the stack from the left-hand side, you have the geospatial data. The very right-hand side, these are the data usage applications, and there are so many of the beloved applications we have, or the tools we have, like Esri, Carto on the end, Tableau, and also the consumer maps. There are so many formats for geospatial data. GeoParquet, for example, is one of them, but there are so many other formats that exist out there. And this data needs to be applied ETL on it, and you need then store the data, and then you run some. Again, sorry about that. Every time I move something around the screen, it moves. So, and then you do data processing for analysis. So, Apache Sedona exists actually in these three layers: the ETL, the data storage, and the data processing and analysis. And it makes these tools geospatial aware and makes them work with geospatial data. So to summarize, the benefits of Apache Sedona is that an open source software for processing geospatial data at scale. You get usability, so it's a turnkey geospatial data API using the standard spatial language. Like again, the OGC standard, it's GTS compatible, GeoTools compatible, and also GeoPandas friendly if you're using Python. It's also adaptability, so it adapts to your stack, whether you use Spark, you use Flink in your data stack, you use Python, Scala, SQL, it will work. Also integrability, so it's natural cloud integrability because again, it uses SQL, so and this is most Databricks and Snowflake, AWS, Azure, and most of the cloud service provider use that. And it also uses the traditional geospatial formats, like again from Parquet and other formats as well that the cloud is familiar with. Most importantly, it's also achieves scalability, so it's fast and efficient processing, so 100x faster than geospatial tools. and 10x faster than big data system implementation. I'm talking like about for Spark, for example, and 50% better resource utilization. So if you're doing this in the cloud, it will save you a lot in the cloud. For the sake of this, for this presentation, so we heard about GeoParquet and the effort, and we actually support that because this feeds into our vision as well. So what we did is that the first thing we started, we said like we want to have a prototype of how can we load data into Parquet. So as of now, we actually implemented a function that can load the GeoParquet format as it is right now into Sedona, and then Sedona spatial data frame. You can run SQL, you can run Python. This is just an example of the code. We also implemented like a SQL function. Like it's not in the standard, but potentially it will be in the standard in the future. It's called st geom from GeoParquet and st load from GeoParquet. You can load that into also a spatial data frame and run SQL on top of this. And we also implemented like the write format, so you can actually process things in Sedona and do your analysis, build a new data frame, and then write things back into the GeoParquet format. So in other words, we were trying to support this effort. We were trying to be able to load things, write it back, especially for users who are already using Sedona. So this is our effort when it comes to GeoParquet. I tried to make this brief because of for the sake of time, but I'm happy to take any questions.
You did. Thank you very much, Moa. And I think we can continue the discussion on Gitter. I will thank all the I will thank all the speakers here for an excellent session. Really interesting talks. And I think we are 5 minutes over, so we should start straight away with the next session, which is going to be lightning talks.
Yeah, I think
we have all are here. Okay, yeah, I can see the first speaker is here. So we'll yeah, go ahead.
I can take over moderating if you want, although I'm happy for you to continue this session if you want.
Okay. So I'll continue. So we start with Tom McWright from Placemark, and he's going to tell us about how real-time geospatial data can work. So.
Yeah, you'll get some magic buttons that appear.
All right. I'm muted.
There we go. Nice. It's all good. We see your screen. We hear you.
We can see.
Do this. All right, and full screen.
Yes, we can see it.
Excellent. All right, I'll keep this to 5 exactly. All right, hello, thank you for having me. I'm Tom, I'm working on Placemark. And so, yeah, this talk is about real-time collaboration, which is very common across a lot of other software categories. I'm sure that you've used it if you've ever used Google Docs and seen other people editing. And this talk is basically about in application to Placemark.io. So it's kind of the successor to GeoJSON.io and a new map editor that is focused on collaboration. So if this was just slapping real-time technology on geospatial, I would have finished the project 6 months ago and wouldn't have much to talk about. So this talk is kind of from the perspective of the geospatial world and like, what are the problems here? All right, so the first problem is going to be addressability, which is a different concept of addressability than what the geospatial world probably would think that is. It's essentially how do you communicate small changes about data? Because collaboration is all kind of about just like people on the same document communicating changes back and forth. So in this case, addressability would be like the index of a character in the string, and it has a position. The state of the art for this in geospatial is muddled and kind of bad. We usually have arbitrary IDs that are numeric that always overlap between different data sets. I think one really interesting example of a project that focuses on addressability is OpenStreetMap, in which not only do things like a building polygon have identity, the individual vertexes of that building polygon have their own IDs. So you can just move one vertex. So what Placemark is doing is using UUIDs which are longer IDs with 128 bits of entropy instead of what a number would be, which is usually around 52 in JavaScript. And then using JSON path to refer to coordinates. So in this example, you would have a point, and the point's ID would be this long string of random characters. And then we would have a way of representing one coordinate in that point. So if you're dragging just that coordinate, we can communicate that coordinate being dragged. So the second topic, conflicts. So what if two people edit the same data set at the same time? So a lot of the geospatial world is still at the point of naming files and hoping that nobody else edits the same file at the same time that you're working on it. OpenStreetMap moves past this a little bit in sort of a way that you can check data out, edit it, push it back, and then hope that nobody's edited in the meantime. But the real-time norm is that nobody ever sees a conflict. So the technology that I recommend just diving into is called CRDTs, which are conflict-free replicated data set types. And so what this basically does is that if there is a conflict, you create a set of rules in which it defines which edit wins, or if multiple edits happen at the same time, how those edits combine. So if somebody changes a property of a geometry at the same time as somebody else is changing the geometry, a coordinate of the geometry, it's able to merge those two things. All right, so the topic 3, which kind of pulls out of the CRDT thing, is speed. Geospatial is one of the most challenging problem areas, I think, for speed, because we work with gigantic data sets. We want to see all of it at the same time. It could be a lot of stuff. I think the most crazy part about it is stuff like the coastline paradox, in which a sufficiently detailed coastline can be so large that even just somebody moving one point of the coastline is something that's actually really hard to communicate. In real life, you can see this in the OpenStreetMap project. And unfortunately, CRDTs at their current state are still slow. They're working out of a state of being slow. Thankfully, they're getting a lot faster. So during the time that I've worked on Placemark, the tools that I've been building this on have gotten about 2x faster. But this is kind of part of the whole living on the bleeding edge here. So in situ, Placemark is the product that I'm building. And in this, you can drag one point in a large data set, and everyone can see that point moved and synced. And that's because every feature has IDs, because it's using a CRDT under the hood. And then, yeah, so I think the questions that come up are versioning, difficult, big data, difficult, decentralization is almost not possible at this point. But that's for a future talk. So thank you.
Awesome. Thank you so much, Tom. And thank you for sticking within time. Appreciate it. So, hey, Jeff, if you're on, you might need to go next. I know it's skipping too, but I think Samuele was having trouble with getting the application.
I can go now. Just give me 1 minute, pull up the slides.
Oh no, there's Samuele. Hey, made
Okay.
it. Okay. You'll go next.
Nice.
Awesome. Got you just in time.
Perfect.
You want to try to share your screen? I think you'll get.
Yeah, I'm just looking at the button to share the screen.
And just a reminder for everybody, any Q&A for Tom, just drop it on the Gitter, and in general, we're using Gitter for questions. And if we have time, we'll do some Q&A at the end, but that's a problem likely as we've been slow on our speaker transfer times.
Yeah. Just let me know if you can see my screen.
Yeah, we see a screen with the browser.
Okay.
And it's loading. Okay, cool.
Okay, can you see my slide?
Yep.
Yeah.
Die Folge gleich los. Aber ich brauche noch eine halbe Stunde.
I see somebody else who is talking. Is it possible we can mute him or something?
Yeah, it looks like it's Marcus. Marcus, if you're on, could you mute? If not,
Ja, ich glaube.
Yeah, so my name is Samuel Mwakisambo, and I'm a software developer at Katoza. So for those who don't know Katoza, Katoza is a free software and open source software company based in South Africa. It's a service provider for the free and open source software, and also to provide training, development and maintenance of GIS systems. And today I'm going to talk about, I'm going to introduce you to the plugin, newly developed plugin called QGIS Stack Browser. So Katoza partnered with Microsoft to develop this plugin. The main aim for development of this plugin is to provide a convenient way of exploring and browsing the stack catalog resources inside QGIS application. So it's kind of like setting up a way for providing an access to user, because up to now I don't think there is a way of browsing stack items or catalog inside GIS desktop computer, GIS desktop applications. So there have been past plugins that were developed. One of them was developed by Kevin Booth, but it didn't have enough maintenance, and so we end up overriding it, and right now we started a new development of the plugin. So we can download and install the plugin in the QGIS application. So we have published the plugin inside the QGIS plugin repository. So for those who would want to use it, we just go inside QGIS plugin manager and install it. Apart from that, there are other ways that you could also install the application. You could use the plugin custom repository. So during development or during updates of the features, we usually update this repository before publishing it into the QGIS plugin repository. So if you want more latest changes on the plugin, you could use the plugin custom repository, or you could just download from the plugin release page and you can store it as a zip file. So the plugin has a section that enables user to explore the stack catalog. And so the way we have developed this is a pretty standard way and convenient way for the QGIS users. So for those who are familiar in using QGIS, it's pretty easy to adopt and use the plugin because we have designed it in a way that the way QGIS define and store connections. So a stack catalog can be defined as a connection, and it can be edited and removed just as a normal QGIS connection. As you can see on the slide there, that's the view of the search tab of the plugin. The plugin also provides a way of searching collections, so you can filter all the available collection on a certain catalog, and then you can search inside in the selected collection. The plugin also exposes the filters, filter by date, extent, and the advanced filter. So users can use custom stack query in searching the stack catalog straight from the plugin. So the way we have developed the plugin is we have used the PyStack client library instead of accessing directly the catalog. So we're just using the PyStack client API to achieve most of the functionality. So the available features I've mentioned. So it's possible to search the stack catalog inside QGIS using the plugin. We have exposed the number of filters I've just mentioned, and we are in process of adding another couple of filters. So user can download and view assets inside QGIS. So for example, if you look at the current slide, there's a shot of the of the result page of the plugin, which user can click the view asset button and then can load assets inside QGIS. The current supported asset by the plugin are GeoTips, Cobb, GeoPackage, and GeoJSON.
Could you wrap up in 1 minute?
Yeah. So we will have to get a feedback on the plugin, and for developer, you can go on to the repository for the plugin and fork it and make contribution. For users, you can use the plugin and you can submit ticket on the plugin issue tracker. Yeah, for more details about the plugin, you can just go inside the plugin documentation side, and then we will have to get your feedback after going through the site. So that's all for now. Thank you, and enjoy the rest of the talks.
Awesome. Thank you so much for the plugin. I've been using it,
Nice.
and it's awesome. And yeah, I had it in my talk, and it's like to see it continue to evolve. It looks like we got Andrea. Can we see you? Just in the nick of time. And you should get a magic presenter button. Hey, I see you. Do not yet hear you. See your screen though.
Getting there.
Sorry for the.
Can you hear me now?
Yeah.
Right,
Thanks
sorry.
for rolling with it.
Install the
No worries.
application in the last couple of minutes. All right, all good.
Cool. Overview.
Okay, so all right, let's see if this starts. Okay, yep. Can you see my slides?
Yep, see it full screen.
Yep.
All right, good, great. So 5 minutes about Cloud-Ready GeoServer. So my name is Andrea Jaime, I work for GeoSolutions. We provide services around various open source projects, including GeoServer. We are a part of OSGeo, we are part of OGC, and we support GeoInt. This presentation is about how GeoServer is evolving to keep up with the cloud. So the overall trajectory of GeoServer and its support for the cloud has been, well, pretty much user-driven, like any other development happening in GeoServer. So customers with support contracts and, generally speaking, people interested in contributing to GeoServer start adding bits and pieces to GeoServer that help supporting with the cloud, leveraging the GeoServer modular architecture, typically one module at a time in an organic, sometimes a bit chaotic way. We get more and more functionality. So the first thing that happened was, well, just deploy it. GeoServer does not need to be modified to actually work on the cloud, and so we got a ton of deployments as AMI, with Docker, with Kubernetes. Of course, we can integrate with the existing cloud DBMSs because they talk the same protocols as their desktop equivalents or their server equivalents. We can leverage elastic scaling and so on. So GeoServer is happily sitting there in the cloud without making taking advantage of the cloud characteristics, the cloud unique characteristics. Next step has been the obvious cost cutting, blob storage for tile caches. So we got early in the process support for storing tile caches in S3, Azure Blob, Swift. At the moment, we don't have Google storage, but again, it's just another plugin that needs to be written. And then GeoWave and GeoMesa started piggybacking on GeoServer to get OGC protocol support. GeoWave and GeoMesa both supported distributing data over a computational grid and distributing calculation, and they are typically deployed on the cloud. So basically, GeoServer was acting as front end, as an OGC front end for these two systems, for both the, well, for most of the protocols, but typically WMS, WMTS, and WFS, with possibly some WPS support. Then we got COG support. We had 2 iterations of COG support. The first module was called S3 GeoTIFF. It was specific for S3, it didn't work with any other blob storage, and it did not leverage the COG structure, which, well, we have been talking about it for a couple of days now, allows for efficient data transfer out of the blob storage. Comes the COG module. The COG module reads only proper COGs. It leverages their internal structure for efficiency. It supports generic HTTP servers, S3, and Google Storage. We hope to have Azure blobs support soon. And there is good integration with the image mosaic, so we can support large collections and time series. I don't have it in the slides, but there is a plugin floating around that allows to use a stack server as an index for the image mosaic, so that you can literally just query the stack API in this case, not a stack catalog, but a stack API to power the image mosaic on the fly. We got Flat GeoBuff support, courtesy of the author of Flat GeoBuff, which did develop a data store so that we can read Flat GeoBuff and deliver it through OGC protocols. But also we can produce Flat GeoBuff again with an output format which plugs into WFS and also OGC API features. And I think it's an interesting opportunity because, well, we have been talking all day about how efficient it is to access data through the space aspect of it, so bounding box searches and so on. But sometimes you really wanted to just do efficient SQL filtering, so alphanumeric or time-based filtering, and you can do that against your, I don't know, whatever data source you are using, and then generating a Flat GeoBuff in output, which is an efficient way to stream out the information you filtered down to your client. Then there are OGC APIs. GeoServer supports a bunch of them: features, styles, map coverages, also DGGSs. OGC APIs per se are not cloud specific. There's nothing cloud specific about them, but having the support for OGC APIs in general enabled support for the creation of a stack module in GeoServer. We already had an OGC OpenSearch for EO module in GeoServer that more or less had the same concepts. You have the collections, you have the products instead of items. And we basically built a stack API support on top of it with full search with the new SQL2. And the current database is a PostGIS database with fully customizable database structure, so you can go and add and destroy columns as you please, and the module will adapt it to the new structure. We have a full templating for both JSON and HTML representation. Here in the slides, you can see DLR, the German space agency, customizing it for the Luz project. And of course, it will be possible, again, to plug in other storages if you don't like the PostGIS one. Another interesting integration that is growing, we don't have it open source right now just because it's an early prototype. We have a connection to Azure Databricks, which ends up leveraging the Databricks SQL API so that GeoServer can pick data stored in the data lakes. In this use case, we have the position of vessels, ships around Europe, with several years of history. We are talking about billions of positions, which are getting published. Sorry?
1 more minute.
Yeah, we are getting published through WMS and WFS, but not just that. We are using Spark to aggregate and enrich them into trajectories and correlate the trajectories of multiple ships and so on. And that is it.
Awesome. Thanks so much.
Actually, wait. I skipped one slide. Sorry, my bad. One final thing. On GitHub at GeoServer/GeoServer-Cloud, you can find this Cloud-Native GeoServer, which is a repackaging of GeoServer as microservices. So single jar Spring Boot applications. Each jar serves a single protocol. So we have one microservice for WFS, one for WFS, one for WMS, and so on. Another microservice for the catalog, another one for the tiles, and so on, with distributed updates via message passing. So this is just, it's interesting to see how a 20 years old application can be modified to become a bunch of microservices just because it has been architected as a set of standalone modules which can be plugged in and off. And this allowed us, well, actually allowed Camp to Camp to repackage everything as a bunch of microservices.
Awesome. Thanks, Andrea. Let's switch presenter over to Jeff. But yeah, that was awesome, Andrea. I think you definitely just made me feel old with the 20-year-old application, since GeoServer was the first thing I worked on, and Andrea and I worked together for many years. And yeah, super psyched to see all the cloud native standards come into GeoServer, and kind of two major parts of my life come together. So super psyched to see this work, Andrea. And then over to Jeff. Jeff did an amazing tutorial yesterday. We'll get that posted soon. So check out that. But now he's talking about Arturo and Cloud Native Geo. Over to you, Jeff.
Yeah, hello, can you hear me and see my screen?
Yep. You're
cool.
All good.
Let's go into presentation mode, we'll get started. Start my timer too. Start a slideshow. Cool. My name's Jeff. I work on the engineering team. Jeff Albrecht. I work on the engineering team at Arturo, and I'm going to be talking to y'all about how we're using cloud-native geospatial technologies at Arturo. First, to describe a little bit about what Arturo does, it's relatively straightforward. We take unstructured, typically raster data from multiple sources. We label all of that data. We have an entire other side of the company that builds machine learning models. And then we run these models and we get these structured property characteristics that we then can sell to our customers, typically insurance carriers, to help them make better data-driven decisions. The really cool part about Arturo is I started working here 3 years ago, and this is what basically our entire product looked like. Is you had this little dashboard, you could go and type in an address, you could hit submit, and you'd come back with some model results. And then you could do that for another address and another address and another address. And you could submit as many addresses as you want, but you could only ever really look at one address at a time. As the company has matured, we've realized that actually our customers want to look at entire portfolios. Looking at one address is nice, but they really care a lot more about, for example, looking at average solar panel damage across potentially tens of millions of addresses across entire countries. And that was a big pivot technologically. This is because they typically want to do book monitoring, looking over big areas. They also typically don't just want to look at the latest image. They want to look at how did my portfolio change over 6 months, a year, 2 years, 5 years. And this was a huge technological shift. 3 years ago, we didn't really have a lot of geo going on in our tech stack. And the super fun part working at Arturo since then is we've been basically pivoting a lot of our tech stack to work in this new method of operating, where we're thinking about where the problem we're trying to solve is how can we extract property characteristics over entire countries instead of individual addresses back to back. Cloud Native Geo has been really, really important to this sort of technological pivot, especially in the way we do data engineering. The first important piece is the multi-source imagery. We take imagery from a lot of different sources: satellite, aerial, stratospheric balloons is my favorite one, super cool data source, drones and ground level imagery. And when we're trying to build consistent and deployable analytic pipelines on top of multiple imagery sources, it's really difficult because every single imagery provider, of course, has a slightly different way of exposing their coverage data and how you access the imagery. This is where Stack comes in. We love Stack. We love Stack so much. We open sourced our internal Stack API that we wrote a while back called Stack Fast API. We use a bunch of other other libraries in the Stack utils repo. And Stack helps us build reliable data pipelines that run across multiple imagery providers without having to build and write custom code every single time we want to integrate with a new imagery provider. which has been a pretty big game changer especially as we expand into other parts of the country in the world. Stack ultimately answers this question. This question is super important, not just to Arturo, but any analytics company. If you are trying to do analytics in this space and you can't answer this question well, I don't care what company you work for, I don't care how good your team is, I don't care how good your analytics are, you will not be successful unless you can answer this question very well. And that's why Stack is such a great asset for the geospatial community, is because it does a really good job answering this question, especially when you're working with multi-source imagery across multiple timescales. The other big change we've made is to how we do data sources and syncs. So we use mostly cloud-optimized GeoTIFF for data sources. COGs, if you can structure them internally in a way that matches your use case, they're just about the best way to store and serve massive raster tile sets in the cloud. You can serve them back out into a data pipeline at ludicrous speeds if the structure of the COG matches your use case. And you can get really good economies of scale because you can just push imagery into these pipelines so fast. ZAR also makes for a great data sync. Out of all the tile-based formats that were discussed over the past 2 days, it's one of the only ones that's optimized for both read and write, which makes it a great sync. You can also get incredible compressions with num codecs, so it's very cheap to store a lot of intermediary data for these data pipelines. And there's a great ecosystem of ZAR tooling that just makes it super interoperable and super easy to look at. It's like 4 lines of Python code, to open a ZAR array and start looking at it in a Jupyter notebook. It's pretty incredible. That was the talk. Pretty short and quick. We've basically pivoted again the way we think about our tech stack from individual addresses to entire countries, and Stack, COG, and ZAR in particular have been very, very important to making that switch successful. Honorable mention is Dask. We're not quite using Dask yet, but we're playing around with it just to do some post-processing on some of the ZAR arrays we create. And I'm hoping it's a bigger part of our tech stack eventually because we're seeing some pretty promising results there. Yeah.
Awesome. Thanks so much, Jeff. Let's get the screen switched over to Daniel. But yeah, super psyched to see all you've built at Arturo. I think Jeff, I think, was the first person, at least that I knew, that got a job out of embracing cloud-native geospatial. He came to one of the earliest sprints when we were very small. And yeah, it's super cool to see the last.
The spec was 04 was
nice.
Yeah, 0.4.
It was early, but Jeff had built a tool for it and then got swooped up by Arturo. And now, yesterday, a number of people said how they were hiring in this space, and it's cool just to see that, yeah, working with this stuff now can get you a job. All right, I see Daniel up. Daniel gave a great talk yesterday on GeoBlaze. That's very closely linked to GeoRaster layer, but this is more about, I think, one level up. So yeah, over to you, Daniel. Do we hear you? We don't hear you.
Make sure you're buckled up. This is going to be fast.
Nice.
Oh. So GeoRaster Layer is a Leaflet.js plugin for visualizing GeoTIFF files. This couldn't be possible without GeoTIFF.js library by Fabian Schindler. It has a lot of features, including a lot of projection support, fast rendering. It doesn't require WebGL, and there's a new feature which is masking data based on a geometry. Who uses GeoRaster Layer? A lot of people use it. Some of the ones that I want to highlight are the COG Viewer app by Nicola from Up42. It's really cool. And Leafem, which is in the sort of RStats, RSpatial community, they use it. And a lot of great sort of small to medium to large businesses and organizations and individuals. Okay, how is it cloud optimized? We are going to show that. It's cloud optimized because it only requests part of the data that it needs. So we're going to look at some analysis ready data from Maxar here. And to verify that it is cloud optimized, we're going to go to our network tab. Let's reload the page so to track these requests. And you can see that it's a partial content request. And then in the request headers, the range is, I only want these bytes in the file. I don't want the whole file. I just want part of the file. Okay, so now we're going to do a quick demo. I got 3 minutes left on adding, how do you add GeoRaster layer to a map app? Let's say that we have an app running. It's a simple sort of leaflet web app. We're clicking on a neighborhood and we're getting which neighborhood it is. This is some great data from the Cambridge GIS people. Okay, so we want to add our geotiff to this leaflet map. It's pretty simple here. So the first thing we're going to want to do is we're going to want to make the scripts available that are required. So we'll use GeoRaster. GeoRaster layer for leaflet is built on top of GeoRaster, which is a JavaScript library for simplifying access to geotiff data, and we'll also import GeoRaster layer for leaflet. And then we're going to go back to our app and check and make sure that it loads. So we'll see, we'll have a parse GeoRaster function now, and we can give that a URL. Okay, 1 minute, 30 seconds left. Now we're going to add our geotiff data. So we'll first create the GeoRaster. And we'll give it, I kind of copied these URLs. So we have a URL to some population data. We'll parse that. And then we'll create a new layer. And we'll pass it the GeoRaster. And then we'll add that to the map, and hopefully in 50 seconds, we'll get this to work. The population data is pretty big. So it looks like we're missing something. Oh, we're missing some leaflet.js scripts here. Let's refresh this page. It might just be a race condition. Huh. Wow. Darn. Okay. Well, I'll give a quick example of it working here. Let's see the population example. I'll give it a second to load. Yeah, so you can load data and stuff like that. Okay, that's all.
Awesome. Thanks, Daniel. Very impressive and bold with the live demo and coding, but way to roll with it when it didn't quite work. Great to have it, to see it happen. And yeah, I was going to say, I think you were the only speaker yesterday who was under time, so you could use your extra 30 seconds or time that you built back. And everyone's been going way over, so super appreciate you keeping things short. And yeah, and reminder for everybody, Q&A, I think we're mostly just doing in the Gitter, so I know Daniel's on there, so feel free to drop questions and share links there. And now it's over to Pete, who gave an awesome talk on Stack Tools yesterday, but now he's going to be talking about some Rust implementations of Stack. Over to you, Pete.
Yeah, Daniel, I commend you. That was bold. I love it. Yeah, so my name is Pete Konopsky. I'm a geospatial software engineer for Element 84. I've been working with Stack Tools, PyStack, and kind of the Python ecosystem for a while. But as a hobby project over the last couple of months, I've been working on a Rust implementation of the Stack specification. That work? It's available on GitHub. It's open source licensed, all that nice stuff. The current release is 0.0.4. I'd like to get to a 0.1.0 soon enough, but it's a hobby project, so you know how that goes. The motivation is kind of this. A lot of the geo problems that we run into from a software side aren't really geo problems. People at my company say this all the time. I've heard it in other places as well. A lot of it are just software problems. And I find that Stack in particular has a lot of things associated with it that aren't specifically geo, right? So there's a lot of IO required to read all of the links and assets. You know, you might be using it to do database access, things like that. Because it's a tree structure, it obviously lends itself very well to software engineering sort of solutions. And it's just big. There's a lot of Stack things. So if you can be a little bit more efficient, that can be a big win for people. I think Rust is well suited for it. I'm generally not a language purist. I think programming languages are tools for jobs, but I think Rust is a good language for this sort of job. First, because it's a focused on performance. It's a compiled language. There's no runtime, no garbage collection, and it really makes you think about memory management and ownership and data layout in a really kind of, in my opinion, understandable way that really encouraged you to write performant code. One of the taglines of Rust is fearless concurrency. The compiler itself helps you make concurrent code, whether that's kind of in an async await sort of environment or in an explicitly threaded one. And so because it's such kind of a first class thing in the language and it doesn't force you into a certain concurrency model, you have a lot of flexibility with if you want to do parallelization with a Rust library. Finally, it's aware that it's kind of a new language, and so it plays really nice with others. It has really strong FFI support. It doesn't ask you to rewrite all your stuff in Rust. It's really made for writing like microservices. And as discussed previously, it integrates well with WebAssembly as well. So a quick overview of the library and what it's what it has right now. So if you wanted to use it, what you would be opting into. First of all, it has just the basic Stack data structures for Rust. It doesn't have any of the other things on the data structures. So one thing I learned from PyStack, PyStack kind of has a lot of the IO stuff kind of baked into the data structures, and that gets pretty complicated pretty quickly. In the Rust library, we just keep it simple. So if somebody wanted to just use the basic Stack data structures and do something else with it in their Rust library, they could do that without having to worry about IO stuff at all. IO is a pretty tricky thing in the Stack ecosystem because you're working with various cloud providers. You know, we see people using FSspec and Python and all these other things to kind of work around this. In Rust, I use traits to basically abstract out the idea of reading. I provide a very simple reader and writer, but if you wanted to write your own that can deal with S3 buckets or that sort of thing, the library is generic over readers. And so you can kind of bring your own IO to the party and still use the library. Finally, I put a lot of work into like kind of the tree stuff because walking trees in Rust is pretty squirrely. At least I've found that when I've been building a lot of stuff for the planetary computer and things like that. And so there's kind of some ergonomics that I won't go into here around walking tree structures with iterables. Rust is very good at this sort of thing. It has what's called zero cost abstractions, where you can kind of use native iterator interfaces without taking a runtime hit for how they execute. So that's just a quick overview of what the library is. Again, because it's a hobby project right now, I have a pretty, whatever I want to do it sort of roadmap, but I'd like to start specking out some of the async stuff and maybe making an API client. Of course, if other folks wanted to come to the party, they're more than welcome to. And there are the relevant links, and happy to take questions in Gitter or elsewhere.
Awesome. Thanks so much. Super cool to see. Yeah, I love seeing Stack have just representations in more and more and more languages. Yeah, and I think it seems like we're hitting the fun ones like Go and Rust and yeah, out of just the core Python and Java. Awesome. Are we ready to play? I think Kushing wasn't quite able to make the session, but I think we've got a pre-recorded video ready to go. So I'll pause and hopefully it starts. No, yeah, he's not able to make it. It says waiting for his screen. He said, so maybe Mikola, you ready to go? I think we'll switch to you and oh wait, here it's coming.
Yeah. Oh, okay.
see what shows up. Oh yeah, this the okay. I think the video is coming. All right, I'll pause and see. Oh no, it's your screen. Wait.
Yeah, let me unmute myself. Okay, I hope that works, right?
We hear you, we see you, we see a dark mode screen.
Yeah. Okay. Yeah. Hey everyone, my name is Mikola. I'm product manager at Opera2, and yeah, it's been a tradition already, but I would present my own project. So it's not really connected to Opera2, but overall, in any way, that's about the discoverability of data. To start with that, I would refer to some of my tweets. So basically, I would be speaking about the data discovery tool based on Stack. And the main idea here is that with this tool, yeah, I suggest to actually be able to browse the entire Stack collection of data and not just look at some specific area of interest and for a given temporal extent. And these visualizations are actually made based on this tool, and during this presentation, I believe I would share some motivation of building that, as well as make a quick demo of how it works and what's the point and which values it can bring. So just to start with that, I would refer to like very common way of browsing geospatial data, and across like multiple products, what is expected usually is that customers, users are coming to the product and they have already in mind the area of interest where they want to search over specific data, and as well as some temporal extent. And so usually we have some limitations based on that, and it includes that, yeah, you can browse for the whole world, but you would have a limited number of responses returned to you, and you will not be able to see like the whole coverage in most cases. And it includes, by the way, also like this Stack plugin for QGIS, which is awesome, and it definitely exactly what is needed for such use cases. But I would share like a couple of use cases that are slightly different, and I had a chance to actually work on. So the first use case is based on the fact that customers wants to find where is the most covered data by high resolution imagery. So they didn't care that much about one specific location that they had like hundreds of them. And what they wanted to achieve is to find the data that was covered by high resolution imagery the most number of times, and therefore they can learn models and basically build analytics on top of that. And yeah, the second example is even a bit more straightforward, is that for some assets monitoring, also like companies trying to find which data is available right now in archive before committing to make task requests, because task requests in most cases are much more expensive. And therefore, if they can refer to archive data to do the analysis, it's much more cheaper than actually, trying to task the entire grid system in this use case. And it comes to the case that there are not that many tools that enable you to actually browse the entire collection of archive data. And with that in mind, there was an idea born to build some Stack discovery tool that would help cover exactly that. So I would just show you a couple of examples right here. So the one that is loaded right now is basically based on Kepler GL. Streamlit is powered by Stack client and GeoPandas. So overall, what it does is that given the Stack catalog and selected the collection of data, you can kind of like query all the available data in this collection, and then you can see it on a map, and therefore you can make a decision if this data is something that you want to use or something like that, or you want to order, even if we speak about like any high resolution data. And it works pretty well with some limitations, of course. So it's definitely not the best tool to browse for like Sentinel or Landsat data, as you imagine. So this definitely would be the case for other tools. But if you imagine that you would just need to double check what is available on some specific collections of data, you can also run and use this tool, which is, I believe, pretty simple to use with its own limitations. And it's very nice to be used together with some other tools like LeafMap or let's say even yeah, others that enables them to browse and discover this data and to visualize it somewhere else. Yeah, hopefully it will end up running before I finish the talk. But overall, that's pretty much it from my side. Let's see if it handles this specific collection. But overall, I believe I would just share it on Gitter, so feel free to test it out and see how it works on your given collection. Yeah, okay, it worked out. So that's perfect timing, I guess. And yeah, I imagine that you can browse over available data, then make a decision which data you want to use, and then move on. Yeah, that's it from my side. Thanks.
Awesome. Yeah, that's super cool. I love the Kepler GL responsiveness, and it's really cool to see that combined with stack results and yeah, just be able to kind of play with it instantly. Cool. So next up, we've got a pre-recorded video from Qxing on LeafMap that Nicola just mentioned as a great tool once you get your stack stuff to dive into it. So let's see what, yeah, I'm excited to see this one. Let's get started.
Hello, my name is Qxing Wu, assistant professor at the University of Tennessee. In this presentation, I'm going to show you how to use LeafMap to visualize code and stack with minimum coding. You can scan the QR code at the lower right corner or go to the URL gshub.org/OGC to access the PowerPoint slides. So what is LeafMap? It is a Python package for interactive mapping and geospatial analysis with minimum coding in the Jupyter environment. The source code is available on GitHub. You can check out the GitHub repo. And some of the key dependencies include, for example, IPyLeaflet and Folium for mapping, IPyWidgets for designing interactive user interface, and Whitebox for geospatial analysis. Also some vector and raster data analysis and visualization using GeoPandas and local type server. So LeafMap supports Jupyter, Colab, and also Streamlit. You can check out, for example, the LeafMap documentation, leafmap.org, and there are lots of tutorials and Jupyter Notebook examples for you to try it out, and over 50 examples. So next, I'm going to quickly go through some of the key features that how you can use LeafMap. So you can, for example, open any raster dataset on your local computer. It can be a cloud optimized GeoTIFF, or it can be any raster dataset support GDAL. And you can also change, for example, the color map. Not only the local raster, you can also visualize the data from the Microsoft planetary computer. And in this case, for example, you can change the bank combination. You can easily, for example, calculate NDVI, for example, and then you can select what level color map that you want. And so you can also change the layer opacity so that you can compare two different data layers, not just the DM. So you can search any dataset available in the planetary computer catalog, and in this case it's just 1902. In addition, you also support any cloud optimized GeoTIFF through HTTP URL. So you just need to paste an URL, and then you can change the visualization parameters to easily visualize code and stack exact item without doing any coding. Next is I'm going to show you how you can search the planetary computer catalog. So you can easily select some sample dataset to display, or you can simply draw a rectangle, for example, or polygon on the map, and then just click one button. You will be able to search the catalog and return the list of results. And after that, just select whatever is being returned and select one sample dataset. You can customize the color map if you want. So simply display the data without coding. So DEM, Sentinel, whatever dataset catalog available. So you can also filter by date. So by date, by ROI. So in that case, it's you can search the data very quickly without having to write any night code. And after that, you can load the data directly to the map interface, and then you can turn the data on and off, just like what you did in some traditional desktop GIS software. All right, and besides visualizing the data, sometimes you might want to analyze the data, or you want to inspect the data. So in this case, you can easily get pixel value. So you just need to click on the mouse. So again, this is cloud optimized geotiff in the planetary catalog or any cloud optimized geotiff. So it is not the data on your computer, and you can get the pixel values. You can also collect training samples. So if you want to do some classification, so you can assign the label to the points that you create, and then you just simply save that one as a CSV to your computer, and then you can open the data. So this is very useful if you need to collect training sample to do image classifications. So you can also load the data back into the map. So after you export as a CSV, you have the location for each point. You also have the label, so you can directly load the data into the map very easily. If you want to learn more about leaf map, check out my YouTube channel. I have a lot of video tutorials for leaf map, Gmap, and some other open source Python packages. And you feel free to reach out to me by email or Twitter if you have any questions. Thank you.
Awesome, and that takes us right to the end of the hour. So yeah, I think there won't be time for really any interactive Q&A, but yeah, I think all the speakers are on Gitter, so feel free to reach out on Gitter. And yeah, thanks everybody for giving great talks. I really enjoyed all of them, and yeah, it's been awesome to see all this great work that everybody's been up to. And with that, Phil, are you about ready to go?
Yeah, I am.
Cool. I guess I'm actually slightly before time. It's not expecting that. We were running so far behind that we managed to get back. Do you want to share your screen?
Yeah, let me, I think I'm getting.
You'll get the reset. Yeah, all tapped in. Yeah. We'll see.
All right, there we go.
Yeah.
Let's see. Which screen am I going to share? I'll share this screen. And let me get the presentation down there.
Cool, I can do a little intro while you get set up. So yeah, Phil has been a part of the Stack community for a while, and then most recently he's been leading all the charge on the 1.0.0 of the Stack API, and recently put out the RC1 release. And then with this tutorial, he's going to dive deep into SQL 2, which is kind of the biggest new feature in Stack API in the last few months. Yeah, which was probably a bigger feature than we were necessarily expecting, working with OGC on that, but super powerful. So I think he's going to give a lot of overview on what all you can do with it. So yeah, over to you, Phil.
All right, sounds good. Okay, so I'm going to be, as Chris said, I'm going to be talking some today about search using CQL2 in Stack API. And this is using the filter extension in Stack API. I'll talk a little bit about what the different elements of the Stack API are and what the extensions are. In this talk, I'm a senior geospatial software engineer at Element 84. I work with Pete, who did his lightning talk earlier about the Stack Rust tools. And as Chris said, I'm also the sort of the Stack API shepherd in getting the API polished and released. All right, so just a brief reminder of what Stack is. It's a group of composable specifications for both describing data and searching data, and it's intended so that people can use exactly the different components that they need to use without having to implement a lot of stuff that isn't relevant to their use case, and being able to put together really good sets of metadata and really good APIs that work well for their specific use cases, and extend both of those in ways that are useful to them, and possibly contribute those back to the community for other people to have those sorts of standards. So Stack is related to the OGC standards in that the Stack API extends the behavior of OGC API features
And a stack item extends a GeoJSON feature. They add things to both while also being conformant to those specs. And that allows us a lot of flexibility to work with existing tooling and just add additional features on top of that. The main thing I'm gonna be focusing on today with the CQL2 support is a specific conformance class in Stack API called item search. This adds a new endpoint / search that allows a cross collection search within a catalog. By default, the OGC API features endpoints only search within a single catalog, although they're also working on a cross collection mechanism now that's I think it's either in development or in draft. And Stack API is specifically thinking of like all these items in one place together, and you're searching over a lot of different items from different collections, different satellites, different everything. The core Stack API item search has a few parameters that you can search on. You've got datetime, where you can search on a single instant or an interval. You've got a bounding box that you can search spatially. Both datetime and bounding box are also supported by the OGC API features endpoints to search items on. The search endpoint additionally adds an IDs parameter that you can restrict the query if you know the exact ID of the item you're looking for, or restrict it to a single collection. Additionally adds a spatial parameter intersects that takes a GeoJSON geometry instead of just a bbox, which allows a lot more precision for searching over an area that you're interested in. The big limitation here is that stacked items provide a huge amount of metadata in their properties, but there's no way in this core item search behavior to search for it. And that was intentional, because one of the principles of all of the stack specs is that they're composable. And so it was sort of intentionally not included in the item search specification, because we knew there were probably going to be a large number of different ways that people could possibly search over items using different languages, and we weren't exactly sure what the best way to that would be. So it's in another Stack API conformance class. The most common thing people want to search over is cloud cover. That's by far the most common use for this. And for simple things like that, we added the Stack API query extension, which included a proprietary JSON-based language that we sort of refer to as StackQL. It was explicit to, it's intentionally for Stack, and it's intentionally very simple. But that also means that it's not a standardized language like SQL, or as we're talking about now, CQL is. It was really just a very fast way to get some basic metadata attribute query going. And that's actually been implemented several times. I was watching Tom Osberger's presentation yesterday, and he had some query extension queries as part of his notebook queries to his Stack API in Planetary Computer, and it works fairly well. We're going to continue to support that, but the future going forward is using the filter extension, and the filter extension supports CQL2. So I'm going to start off with a little bit of explanation about what CQL2 actually is. And I'm going to start by saying what CQL2 is not. I want to make this really clear because I a couple of years ago I did an implementation of CQL2 or of CQL for a Stack API that I was working on, and I actually misunderstood which CQL we were talking about and implemented a totally different CQL support in my Stack API. So what it is not is the classic OGC CQL as defined in the general model. Although that CQL did serve as a significant influence on this CQL's CQL2 text mode. It's also not the search and retrieve via URL contextual query language, also known as the common query language, and it's not the Cassandra query language. It's the OGC common query language, and we try to be pretty consistent about calling it CQL2 now so that it's really clear exactly which query language this is. This was originally part of the OGC API features part 3, filtering and the common query language CQL specification. It was realized that CQL2 actually has more applicability to various use cases outside of just the OGC API features part 3 implementation. So it's been broken out into its own standalone specification that will then be used by part 3. But it also means that it can be used by other specifications going forward. And it's turned out to be a really, really nice language. I want to speak a little bit to the process that CQL2 went through in its development too, that we in the Stack API community were very involved with the OGC folks, Peter and Clements specifically when they were developing the CQL2 language. And it was a really great collaboration of our focusing on like very, very practical concerns about what we wanted to do queries on, and then wanting to define a very well-defined, generally applicable language to be reused within many, many different features. And we ended up going through several iterations in Stack API in different betas. And what's come out of it is really, really great language for doing these types of spatial queries. Just to give you a brief flavor of what these sort of queries look like, there's 2 different flavors. There's CQL2 text and CQL2 JSON. The text format looks similar to SQL. As many of these languages end up looking, and the JSON format uses a series of op and args parameters with lists of arguments to recursively construct these queries. I'll go into more of this later, but this is just an idea, just to give you an idea of like what these type of queries look like. Okay, so the Stack API filter extension, most of the behavior in Stack, both Core Stack and Stack API, are done through extensions. This allows a lot more decoupling of the behaviors and allows them to be versioned independently. Currently, the Stack API spec is in 1.0.0 RC1 version. We'll probably split out the filter version and version that independently because the CQL2 spec is currently still in draft. We'll probably split that out. So if any changes do occur, we can version it independently and people can implement whatever version is available at the time that they're doing their implementation. And then that gives more flexibility going forward in updating Stack API independently of the Stack API filter extension. We introduced this in beta.2, which came out, I think, a little over a year ago. And it's migrated, migrated as we've released versions and the CQL2 spec has evolved into the current form, which is thought to be very, very stable. is starting to have some implementations. Okay, I'm going to start. One of the key aspects that I keep, I've said several times, is that a lot of these specs are intended to be composable and modular, so that you can choose what to implement depending on what your use cases are, and that is both for clients and servers, that you can implement whatever behaviors you need to. You can do it in an incremental fashion, and you can advertise what you actually support through conformance classes. And likewise, clients can look at these conformance classes and know what features an API implements, and then only surface those features to the API user. Probably the three conformance classes that are part of CQL2 and therefore filter extension that are getting the most, will probably get the most use, are the basic CQL2, the advanced comparison operators, and the basic spatial operators. There's 10 classes overall, and the other 7 definitely have their uses, but they're more complex to implement. And I'll talk a little bit more about these later. Okay, so basic CQL2 conformance class has logical operators in it, so you can do and, ors, or nots. It has the basic comparison operators and an is null operator that works against all the primitive types, string, numeric, Boolean, date, and datetime within an expression. This is the example that I showed earlier. With this, I can match collection to a string. I can match cloud cover to be less than a number. Likewise, I could, if I have mixed data, some that has cloud cover and some that does not, I could say the cloud cover either has to be less than 10, but if there's no cloud cover mentioned, then I also want that returned. That's useful for cases like Nate, that doesn't have cloud cover as a value, but is generally cloud free. So this is, this even if you could filter on properties within an item in the core item search, just being able to add these together and say, I want this property or this property is really, really useful. And same thing with collection. You could filter different attributes based on the collections by just oring and anding them together. Likewise, most of those parameters that I showed earlier that are supported directly with the item search endpoint, like date time, those can also be pushed down into CQL2 filter expressions. And here we have an example of filtering by date time, where the date time has to be less than a timestamp with an ISO 86 or a RFC 3339 date time indicating that timestamp. Likewise, these are kind of hard to fit on a single screen because the JSON is so verbose. But here's an example of the first query we had above, where we're just saying it has to be the Sentinel-2 L2A collection, and the cloud cover has to be less than 10. And likewise, here's a couple of the other predicates that we could say. We can say that the date time has to be greater. Well, I think I said greater than here, but the date time is compared to a single timestamp. And likewise, the is null operator allows us to check that in a certain property. Okay, so those are the basic operators. The next conformance class is the advanced comparison operators, like between and in. between and in can always be expressed by using a conjunction or a disjunction, and an or, with a series of greater than or less than comparisons. But there's no other way to express an SQL style like expression where you're doing a glob like match on a string. So here's an example of those. Between takes an argument of the property and then two values that it needs to be between. Like we'll take a property and then an expression with percent signs that express the match on either side of it. And then in we'll take a property name and a list of values that it could possibly have. And then the basic spatial operators, it's plural, but there's only one, spatial intersects. And this has the same semantics as the intersect parameter that item search has. But because the OGC API features endpoints don't already have an intersects parameter, it's important to have this as part of CQL2. It's also important because you may want to just push everything down into the filter expression and not have to mix and match the item search parameters and CQL2 expressions in that filter. You can just put them all in the filter. And this is what the spatial intersects parameter would look like. You choose the property that you're filtering on, and then a GeoJSON geometry that you want that to intersect. Yeah, and so the question is why S intersects instead of ST intersects like other common applications. I don't actually know that. That may go back to some of the other OGC specifications. And Peter says that he knows, but can't speak right now. Peter, if you wanna put that in the chat, I'll read it to everyone.
We can also probably promote him. Jonathan, could you find Peter Vertanis on the attendees and promote him? You can say a few words. Or maybe not.
Yeah, I'll just go on. Well, Peter says that they're all just a single, just for consistency's sake, they're all just a single prefix letter. So S for spatial, T for temporal, A for array. So yeah. Then I'll just briefly talk about some of the other conformance classes. I'm not going to give examples of these, although the Stack API filter extension definition and the CQL2 definitions have a lot of examples for these that you can go find if you're interested. The spatial operators extension adds an additional, on top of the basic spatial operators class, adds the other DEM 9IM spatial operators that define adjoining and within and all the other spatial operators that exist. The temporal operators also define a number of different ranges of different instance and interval operations. Custom functions defines functions that you can actually use within the CQL2 expressions. These are these are useful if there's some transformation that the values need to go through in order to compare them properly. Arithmetic expressions in the operations, array operators, equals, contains, contained by, and overlaps. Those can be useful. I'm actually talk a little bit about one of the array operator use cases later on. And then the property to property comparisons. By default, I didn't mention this, but I sort of implied it. By default, the basic CQL2 class only allows you to compare a property on the left-hand side of the comparison and a literal value on the right-hand side of the comparison. The property to property comparisons class allows you to compare one property to another property. And that's a separate class because there are a number of data stores in which it's actually really hard to do property to property comparisons in. And so this allows a little bit easier of initial implementation. And then finally, the accent and case insensitive comparison operators for working with languages that have more than just ASCII characters in them. Okay. So I've been talking a lot about how to actually construct the queries, construct the expressions that are in the queries. But one of the biggest problems with many of these query languages is that you don't actually know what terms and property values you can use in the expressions. When we're talking about something like SQL, you can look at the table column names, or look at an out of band set of documentation that says here's all the different terms that you can use, here's all the different property names. But that's not great when you have a general purpose API that you're allowing people to do queries over and they don't know what they can actually query on. And so queryable is this really great mechanism that explicitly defines what terms, what properties can be used in a query. So for example here, I use collection and I use a property called EO cloud_cover. Well, if you know Stackwell, collection is usually a top level field in the item JSON, but EO cloud cover is actually in the properties object in an item, whereas I've just used it raw here. How do I know that this API isn't expecting that to be properties.EO cloud cover? And the way I do that is I can actually look at the queryables definition. So this is a endpoint that's either at the root of a Stack API at the queryables path, or they can also be within a collection, so that individual collections can advertise that they support a certain set of properties that can be used in CQL2 queries. And this is great because it decouples the actual stack item representation from the way that they can be queried over. And so, for example, instead of having to say properties.EO cloud_cover, I could simply say there's a queryable called cloud cover, one word, and that can be used anywhere in the property, or that can be used anywhere in the expression as a property. And then these are well defined using a JSON schema, so that there's typing information associated with that. JSON schema allows you to do even more things like define a regex that the value has to adhere to. For example, datetime is that way. I'll show an example of that in a few minutes. But in this example here, we've said that the properties.datetime value has a name of datetime, and the cloud cover has a name of cloud_cover. We've eliminated the EO colon from it because it's unlikely that it will conflict with any other property name. And then we can just use these in our expressions. And even better, we're actually referencing the schemas, the JSON schemas that are used in the definition of these properties in Stack. Datetime, we're referencing the core item spec. For cloud cover, we're referencing the EO extension. And so we don't have to redefine them. We get really, really high quality definitions automatically. And so, as I was saying here, the queryables in that previous JSON schema definition are saying, here are the names that you can use in your CQL expressions, and here's how they map to the actual fields in the item, which is completely transparent or opaque to the user. All they know is that they're querying against these names, and then the server will translate that into an appropriate query against the data store. A really great example of this of the use of this schema is the Microsoft Planetary Computer. Through Element 84, we have done some work on the Planetary Computer, although not this. I'm mostly presenting this because I think it's a really great example of what can be done dynamically with the UI with these queryables. And this UI is from the Planetary Computer's Explore interface. It uses queryables to define all of these custom filters. The acquired filter, which is a date, cloud cover, orbit state, all these other ones. There's a list of probably 25 in these filters that are dynamically driven based on what the queryable's endpoint says exists. So datetime's referencing the item's properties datetime. It's in the UI, it's simply, or in the API, it's simply referencing the item spec. And then that item spec actually defines it as either string or null. It's if it's a string, it has to use the datetime format. And even more restrictive, in Stack, the pattern has to be in UTC, either with a 0 or a Z offset. So this really, really allows a UI developer to provide an interface that restricts what users can actually put in for these filter mechanisms, so that they're more likely to create a valid query and create a query that actually has meaning with the data that exists and is what they intend. Same thing for cloud cover. It's referencing the EO cloud cover definition. It is a number, and it has a min and max of 0 to 100, so that a range slider can be displayed to the user to choose what cloud cover they want. Additionally, here's an example of an enum where the orbits, the satellite, I think it's called the SAT extension, or is it called this? It's either called the SAT extension or the satellite extension. Uses has a field called orbit state. This definition queryables directly references that, and it's defined as an enum, and then that enum is populated directly into the UI, so the user can only choose the 3 options that actually have meaning in in the query that they're trying to construct. So by default with this queryables mechanism, the only valid queryables that can be used in an expression are the ones that are defined in that schema. But there's a property called additional properties in the schema that says users can try to use other properties. They may not work, they may not have the expected behavior, but it's not going to be an immediate failure if they do try to use other properties. And this is sometimes useful for heterogeneous data sets that have that some items have certain fields and other items have other fields, and it's difficult to actually get a complete listing of all the possible fields that you might be able to query over. This is sort of an escape hatch that says, okay, you can try to do other things. They may not work, but you can try to do them. And then the software ecosystem, for this I'll talk about for a minute. We released the Stack API 1.0.0 RC1 released about 2 months ago. There were some changes to CQL2 in that, but we've been slowly having fewer and fewer changes in the betas and and now this RC as time goes on. So we've had quite a bit of implementation work that's been going on and is rapidly catching up to RC1. As for backend support, StackFast API PGStack supports the CQL2 JSON format via PGStack supporting that. GeoServer supports it via GeoTools, but only supports the CQL2 text format. PyGeoFilter supports CQL2 JSON, and the Extra Platform Spatial Library supports CQL2 text. And then several of the clients, client support in PyStack will allow you to run it with filters, but you have to explicitly say that the filter language is a CQL2 JSON, or it assumes an earlier version of the CQL spec. I'll share out these slides soon, and here's some references to the various specifications and a lot of really great examples of how to use CQL2. And yeah, thanks a lot for listening, and I'll look in the chat now for some questions and start going through those. So Robin asked about this is a great point. So he asked about it points out that the Microsoft Planetary Computer queryables are basically empty, and that's true at the root level because I think in this example here, let me open this up and look. So the currently deployed queryables in Planetary Computer, there aren't any listed at the root level, meaning which is advertising that there are no fields that you can query the entire data set on, because each collection of each type of data, whether it's Aster, Sentinel, all have very different metadata associated with them and very different properties associated with them. So the root should basically only be something that the fields that you can query every single item in that catalog for. That's generally very small. It's usually more than none, because you should generally be able to query ID, collection, geometry, date time in any of those. So that document's probably a little shorter than it actually should be, but it's good at pointing out what the differences there. Okay, let's see. Yeah, Tim asks, has there been any discussion about including stack queryable metadata in the existing collection summaries? And I'm not actually sure what that would look like. But it looks like there's a good discussion on that in the Gitter channel. Okay, so is there a way in CQL2 to get sorted outputs? Like I'd like to find the top 10 images in a year with the smallest cloud cover. Yeah, so that wouldn't actually be part of CQL2. That's part of the sort extension, as David points out. The sort extension would allow you to sort by cloud cover. Although the existing sort extension suffers from the problem that there's no way to advertise what things you can actually sort over. So that's a possible future extension to that. I know OGC is working on that with their sortable work too. These UBLs are really, they add a lot to implementation and add a lot of work to the spec work and the implementation work, but they provide such a great API-driven client interface that they're very worth it.
Hey Phil, I think I can talk now, right?
Oh yeah.
Great. Yes. So in what's happening in OGC with sortables is we adopted the sort of syntax that Stack had for specifying sortables, and we added a sortables endpoint for exactly the reason that you just said. They're very good for API-driven development. So the OGC definition will have a sortables, which is just another type of schema. So in OGC, we have a bunch of different types of schemas. So you have the presentable, or just the regular schema that you get when you do a query. You have the queryable schema, which is the sub schema that you can use for querying. You have the sortable schema, which is the sub schema that you can use for sorting. And the other thing I'd like to point out is that you could also put synthetic properties into these schemas, right? They don't have to necessarily map to some property that's in your data store. If your server knows how to handle the synthetic property, that's perfectly reasonable and legal as well. Thanks.
Oh yeah, thanks, Peter. That was one thing that I had meant to bring up. I said I was going to bring it up, and then I forgot to. The decoupling of the advertised queryables from the actual structure of the item means that you can, as Peter said, use synthetic, I guess what we call synthetic queryables, which are queryables where there's no like direct correlation to a property in the item. And so one of the examples that I use for this is in an item, assets can have the EO bands extension, which define the name of the bands that are in that asset. So you could say like, this asset has a red band, a blue band, and a green band, or this asset has this type, this collection of bands in it. And there's no easy way to search on that because it's actually a list of things, and they're all in different objects, really. So you could advertise that there is a queryable called bands, and it's just the list of all the bands sort of added to a single, as if they were added to a single array. And then a user could use the arrays extension to search that the band that they were interested was in this synthesized queryable called bands that doesn't actually exist in the item. And then the server would rewrite that in a way that made sense to query the data store with. And so those are really powerful because you can expose an easy way for a user to query data that's in a bunch of different places in your item. Matthias asked, have there been any thoughts to serve queryable with the refs resolved? If you'd like to request queryable from Stack Browser, it seems slow to have to retrieve all of them. Yeah, I think that's actually a really good point. I think in defining them, you would probably use the references, but then there's, there's tools out there that will resolve all the refs and then give you a resolved JSON schema back. And I think that's probably in implementation, what you'd want to do is reference them in your definition of them, but then generate a version that actually has all of them resolved. So there's no, you don't have to do, the client doesn't have to do multiple queries to retrieve however many stack JSON specs they need to. David Bittner said that PGStack also supports CQL2 text via converting to CQL2 JSON with PyGeoFilter. I had forgotten about that because that's a really good implementation point, that if you can support one of them, there's conversion tools to convert to the other. And so implementing CQL2 JSON means that you can easily also support CQL2 text via the PyGeoFilter, or if there are any that exist for other languages.
Yeah, just to circle back to Matthias's question quickly, Phil, if I can. Generally, servers, when they generate the queryables, they actually, resolve any kinds of references like that so that you get a full JSON schema. And one of the reasons to do that is that some servers will generate a runtime list of enumerations for the properties, so that when you're building your query, you actually have a good chance of constructing a predicate that will actually return something, as opposed to guessing what values might exist for, whatever property. So they dynamically, include the enumeration list, and it's built up at runtime sort of thing. So it queries the database and says, oh, okay, property 1 has these 5 values right now. So if you use any one of them and you do a query predicate, you have a good chance of actually finding something.
Yeah. Okay, so there's apparently a CQL2 parser in Go that I hadn't heard of. That's good to know of. PG feature serve. Okay. Are there any other questions or things of interest? I could run some queries if that's of interest. They're not terribly interesting, but let's see. Let me get this out of this. Let's see, there we go. Yeah, so Planetary Computer is the implementation right now that has the or public deployment that has the best support right now for CQL2. Here I'm going to run this this query. So this is restricting the collection to Sentinel-2 L2A collection, and then cloud cover is less than 10%. And then I'm also using the fields extension, which allows you to restrict the results so that I don't get nearly as much data back, and I can easily see my cloud cover values. You know, one thing that I think is interesting about this is that the CQL2 JSON format is nice because it's basically already it's effectively already a parsed tree of the elements in the query, but it's extremely hard to write because it's a lot of JSON to get correct. But in general, people won't be writing these queries directly. They'll be using some sort of other tool, like whether most people will be using a UI that has drop-down menus in it. And you know, as we saw earlier, the queryables allow those UIs to be constructed in a way that is really, really relevant to what is actually happening, and it's not just a free-form query. It's, you know, very restricted in what the UI elements can be. Yeah, so so Matthias points out that I can query globally for EO Cloud Cover, but it's not listed in the queryables. And I think this is a sort of an artifact of the fact that this implementation in Planetary Computer is still ongoing, and you know, we only recently came out with the final version of or not the final version, the RC1 of the filter extension, and that things haven't quite caught up with you know, what can actually be done done in that implementation. One of the things that I did notice was well, if you look in the Planetary Computer Explorer interface, the options change depending on which collection you've chosen, and so the filter options are being driven off of that collection's queryables rather than the global queryables. Even though, as I demonstrated here, I can actually search for properties that don't exist in the queryables right now. All right. Well, thanks everyone for listening, and yeah, so Alex says, are there implementations to simplify building SQL statements in code, Jupyter Notebooks, or does PyStack abstract it? Right now, I think PyStack doesn't have any specific abstractions for SQL2. It's just a JSON blob, but I think that that's something that will be, you know, will be added over time, so that those can be constructed in a more programmatic way rather than just building a, you know, sort of an arbitrary dict that hopefully is, you know, conforms to the schema. But you know, there's a lot of like builder patterns and things like that that exist for SQL and apply pretty well to SQL2 also. We're at a really exciting time right now because you know, we've just gotten these specifications sort of ironed out, and now the implementations are going forward. And yeah, so if people are interested in getting involved with some of the implementations, they're definitely ongoing and need coding and testing and just you know, even your use cases are really valuable to know, you know, what you're trying to query and what needs to be implemented to support those types of queries easily, particularly with like data scientist usage in Jupyter Notebooks.
Yeah, and following on that, we've got a little bit of funding from the Stack fundraising efforts in the past to help support some of those implementations. It's not much money, but if you happen to be working on an implementation, and yeah, like our thought is give a bit of money to try to get that sooner so we can get feedback on the spec itself. And I think that's what's going to really put us from RC1 to 1.0.0 is, yeah, when we see a number of different implementations and feel really solid about everyone working with it. So Cool. Thanks, Phil. This was super great. Yeah,
thanks.
And yeah, we got a few minutes to the next session, but I think we'll probably just pause, people in chat on the Gitter if you would like, and then yeah, looks like we got many of the presenters on, so I'll be back in 5 or 6 or 7 minutes and we'll kick that session off. Thanks, Phil.
Thanks, Chris.
Hello, Howard.
Hey, Matt.
I'll be the moderator for this last session. We'll wait another minute before we get started.
All right. Hand me the present screen share.
Yeah, just select OGC to do it. It should come your way.
There, that one.
Okay, it's 2 o'clock. Welcome, everybody. My name is Matt Hansen. I'll be the moderator for this last session. This has been a great couple days. I haven't been able to see everything, but I know that there's a bunch of talks that I'm going to go back and watch the video for, so I hope that you all have enjoyed things. This last hour, we have several talks around point clouds, but also some other miscellaneous talks. And first up is going to be Howard Butler, who is the guy to come talk to if you ever have a question about point clouds. And he'll be talking about Copic, the new point cloud optimized point cloud format, and including how to pronounce it, right? It's Copic.
Sure. Thanks, Matt.
It's undecided. I think it's undecided, right?
Yeah, I don't know. Every language will probably pronounce it their own way, just like GDAL and everything else. Yeah, thanks for the introduction. My name's Howard Butler. You can find me on Twitter. I have a company in Iowa City, Iowa called Hobu Inc., and we've been doing open source software for point cloud data and point cloud data management for more than a decade. Our latest effort here is with the Copic or Cloud Optimized Point Cloud we're talking about today, but we've also done a lot of work on point cloud organization with Entwine, and then of course the open source library called Poodle, excuse me. So what's kind of a reality of point cloud data? And I talked about this a little bit yesterday as well. Is it's data that's read many more times than it's written, right? And that might give us some opportunity to organize things in a certain way that takes advantage of that. How you use point cloud data, most of the time is finding what you're looking for. It's what I call, it certainly meets the definition of big data, but it's fluffy data, right? An extra point, loss of a point in a million point cloud really has zero meaning. And the applications don't often need all of that information to be able to make decisions with the data. Open formats like LAS and LAZ have pretty good industry interoperability, but there's closed formats that can certainly do more. And up until we developed Cloud Optimized Point Cloud, there wasn't really a single file container format for doing point cloud data in a cloud-native geospatial way, and that's what we're doing with this today. What got us here? Why did we want to develop this? We see this curve all over kind of society these days, which this is a plot of the linear mode LiDAR pulse rate, and that corresponds directly with resolution. And so as the sensors are increasing in resolution, the data volumes are following suit. And so the data storage, data organization, data transmission, data compression approaches that we had taken and just constructed in the early 2000s need to catch up to this. So what would be an ideal point cloud format? A grab bag of requirements, some of them certainly in conflict. Storage efficient, obviously, with fluffy data, we want to compress it, but we also want to be able to search and get what we care about. A single file has a lot of desirability for data federation and moving data around. This organization needs to support every possible computing challenge. Maybe we want to transact data as a database and keep track of what's been going in and out of it. In Cloud-Native Geospatial, being a usable thing over the network is super important. And then, of course, we want everyone's software to be able to read it. this thing doesn't exist, right? Like these things are all in conflict, so let's make a new one, like we tend to do. But what's missing in open formats really is this idea of spatial access and resolution selectivity. So if we drop out some of these requirements that might be in conflict, can we construct something that would meet most of these challenges? So a guy named Martin Eisenberg developed the LASZIP software and the LAZ format. It's an adaptation and compression of ASPRS LAS. Martin, released this as open source in 2011 and 12. He was instrumental in developing LAS versions as well, and with his LAS tools software, both commercial and open source software, had a great impact on the industry. He recently died this past September, but the LAZ's impact is certainly going to continue to be felt across the industry. So what's some thumbs up for LAZ? The first one is, at this point, except for one of the really large GIS vendors, it has industry-wide support. Everybody can mostly read LAZ natively and do what they need to with it. It's a very efficient lossless compression. And we recently changed the license of LASZIP to be Apache public license. And what this means is applications can embed it directly, do like a static compilation and put it in an iPhone app, which iPhone has LiDAR now if you weren't tracking. And so the ability to put LAZ and LASZIP software everywhere and do stuff with it is stronger than it ever was before. Some downsides for LAZ though is it's kind of CPU intensive, right? It's trying to make a very efficient compression, and to do that requires a very complex compression model, and it requires quite a bit of CPU to compress and decompress it. You can certainly, if you're willing to relax that, you can do quite a bit better. It also has this sort of defect or consequence of how it was of its heritage is it grew up in supporting geospatial linear mode pulse LiDAR, which is a certain kind of point cloud data that it supposes a certain model. That old Sullivan quote about form following function is absolutely true here. And formats, no matter what they are, have to make compromises about what they're going to support or how they're going to support something. But LAZ has a very strong argument for us to augment it to add what we need to make it cloud native geospatial implementation. The first is it's undeniably the storage, archive, and transmission format of large geospatial public LiDAR. There's petabytes of LAZ content out there already. It's well established. It has open source implementations. It's based on open specifications. And Cloud Optimized GeoTIFF shows us a way to essentially augment an existing container format and bootstrap it to an industry in an opt-in way. So if we go and attack the two features that are missing, which is spatial access or windowing and resolution selectivity of LAZ, how might we do that? The reason why we want to do this, of course, is to be able to take advantage of partial access, right? We want to touch this data over HTTP, and we need selectivity both for applications to be able to control how they move through the content to select the information that they need. We want to be able to do that in parallel as fast as we can, or as fast as our infrastructure supports, and not decide for applications how they're going to access the content. So how do we do that with Copic? We actually store an extra bit of metadata called an octree. It's the same octree organization as Entwine Point Tile. And then we cluster that LAZ file according to that octree. And so LAZ files support both a kind of a fixed chunking model and an adaptive chunking model. And in this case, we're storing those as adaptive chunks. It's backward compatible with LAZ 1.4. But it only supports a subset of the data record formats. And the reason for that is to limit the aperture or the window of things that developers need to support here. This LAZ 1.4 and 678 kind of is the sweet spot, certainly for LiDAR data. And it has an open specification at copic.io that you can go read and hopefully implement without too much trouble. So what can I do with this? One of the concepts that Chris was showing yesterday is We want to be able to have an application, ideally a web page, we can just drop data in and quickly visualize it. So the data format needs to be supporting visualization type access. And in this particular case, this application is using the metadata to calculate which points it needs to go select, making range requests against S3 to go fetch those, and then in some worker threads decompressing that and displaying it on your screen. This particular implementation that we developed is cesium based and supports both the Copic and EPT point cloud data structures as a single point kind of application for convenient visualization. You can pass in multiple resources, you can save your viewpoints and stuff like that. It also reads many coordinate systems. Coordinate systems in LAZ and LAS can be quite challenging, especially in JavaScript environment. Coordinate systems in general in JavaScript environment can be challenging. Right now it's a free resource, but we haven't released it as open source. Still talking about that. So what else can you do with Copic? So computing an overview with the data. The ability to select for both the resolution and the window means that software applications can traverse through the data and control their traversal through the data. You're doing that with a COG file, whether you're using GDAL to select an overview or some other application, or all the fantastic browser-based visualization we saw the last couple of days is doing the same kind of thing. The ability for an application like Poodle to be able to do that means that instead of touching this file with 360 million points and throwing most of them on the floor, we can construct a kind of a quick preview image to make sure we're located where we want to be or something like that in a few seconds, and only touch a much smaller percentage of the data, and do it over HTTP and get the convenience of the cloud-native geospatial thing. Another important concept here that we've also seen this as cloud-optimized GeoTIFF is the ability to parallelize your software moving across this data. We don't have a server in the mix other than HTTP, and the application controlling how it does that means that it can control how it parallelizes across the data as well. So what else can I do with Copic? Pretty quick here. The release that comes in June, you can go get it now in the nightlies. QGIS is going to support Copic for visualization and for analysis. And so, Martin Tobias and the Lucher team here have sent us along this movie that shows a Copic file that is Melbourne, Australia, that we made available online on the Copic.io website. This is great visualization. We can make some movies and stuff like that. But the real power is you have all of QGIS available to you, right? So all of the analysis, elevation modeling, filtering, meshing, all of the stuff you might want to do in QGIS to elevation content, you can do with Copic files. And this is a really important step for making this stuff super convenient and being able to do it, local file system, but also over HTTP. The same model that has been tread down with cloud-optimized cloud-optimized GeoTIFF. So what else can you do with Copic? So our team has been working with the Planetary Computer team as well to construct their catalog with a stack-based catalog using Copic to model and store all of USGS 3-depth LiDAR point cloud content. There's been a lot of talk about Planetary Computer here in these couple sessions, so I won't get into too much detail there. And I have a Jupyter notebook that shows how you as a programmer can essentially touch their API, go figure out which data you're going to read, and then do Poodle stuff to it. So in this particular case, I was computing height above ground model to find that the building nearest the bean in Chicago is like 380 meters high. This is really powerful for allowing applications, again, to control how they're touching the data, only access the parts they need, and that particular window there actually covers 4 tiles. All of the sort of stack access that you would do also applies for Copic files here. And so the processing compute model is essentially the same, except it's point cloud content instead of raster content. So what else can I do with Copic? Well, the same thing with COG it's just an LAZ file, right? So all of your existing workflows that are using LAZ to do stuff like LAS tools, white box tools, maybe you're doing cloud compare visualization, they don't need to know that special metadata to be able to read the content as LAZ. And that's a really important concept here in terms of making this data accessible and not having to have a discontinuity where you're trying to bootstrap, an industry with petabytes of history, essentially, of content that it can't simply convert to a new thing, not all at once. So, people have asked us, well, hey, you were doing this in 20-point tile thing. Why are you doing the Copic stuff now? And it comes down to, for us and for LiDAR point cloud, the distinction between an exploded data organization and a condensed data organization. So in an exploded organization, depending on which cloud you're in, you might have per object access cost, and that could be quite substantial for really large point clouds with millions of objects in them. But the most significant challenge with an exploded data storage is it's impractical to move them. And so if you're in the cloud and you're always in the cloud and you're never moving data, it's not really an issue. But if you ever have to federate this data or air gap it across something or put it on someone's desktop because they don't have network access, an exploded data format is very, very difficult. You have to put it into a suitcase and haul it over somewhere and then dump it back out again. This is whereas Copic has the same pitch as COG, which is it's condensed, it's all together. It might be one file. Sometimes they could be big, really big if you wanted to, or they'll be small. And it's the data provider's prerogative to control how big or small those tiles would be. Another challenge that Ryan talked about in his talk this morning is with ZAR is that data that's modeled as a exploded is kind of like a stack collection, right? It's a whole bunch of tiles. It's a whole bunch of different data that's all put together with one kind of semantic meaning. And but Stack's atomic unit is item. And so for better or worse, in LiDAR point cloud, tile and raster content too is kind of the dominant organizing principle. And so data that are exploded as a collection of tiles, we found them difficult to model in Stack, and being able to do this with cloud optimized point cloud is easier. And then finally, at least for the point cloud, geospatial point cloud industry, bootstrapping support for it for a new thing is very, very difficult, right? There's a lot of inertia you're pushing against. Even with EPT, where we have all of the EPT content available in Amazon Public Data Store, and it's available for people to compute there, and it's updated daily, and it's like 40 trillion points right now. The people doing that are doing that to compute in the cloud, and the rest of the industry hasn't really followed suit, right? Because it's kind of something special they would have to build into their software. Whereas something that's LAZ based, which they're already reading it, adding support for it is an opt-in thing. It's not a have-to thing. And so that pitch is just much easier for people to get on board with, and they don't have to do everything all at once. So what's the roadmap here? We finalized the spec in November of last year. And then this past March, we released Poodle 2.4, which provides both a readers.copic and a writer.copic stage. And this means Poodle application users can use that content, Copic content for analysis and take advantage of that spatial and resolution selectivity feature that Copic has. We have an open source software called Untwine, which is able to construct very large Copic files in a efficient way, exchanging memory for file storage. So it'll use a lot of cache to build things out, but you can throw most of that away. There's an open source library from a team called Rock Robotic, based on Python and C++, that for making Copic files and doing stuff in Python. Connor Manning from the Hobu team manages the Copic.js, which you saw in the visualizer being used. Lucha team has QGIS support for Copic available in the nightlies if you are willing to hack and slash to go get that to work, to be released here in June of 2022. And then some of these other projects all have this at least on their radar or on their queue, right? So they're certainly taking a hard look at what's available and seeing what's going to happen with industry support and who's starting to pick it up. So final take homes from my talk. Copic here is an extension of LAZ that supports spatial query, spatial windowing, spatial resolution. It's backward compatible with LAZ 1.4. The LazZip library and LazZip codebase was relicensed to Apache public license. That means you can embed this in your own commercial software, do what you need with it to provide LAZ and Copic support for your applications. There's lots of open source support that we've helped bootstrap. Commercial support hopefully coming. Ask your software vendor for it. Show them all the stuff that's available. And finally, there's no official pronunciation. We're calling it Copic at our office, but as long as everybody knows what you're talking about and you're able to communicate what's going on, good for you. So thank you very much.
Thank you so much, Howard. That was great. Great learning more about the format. I don't see any pressing questions, and to make sure that we have enough time for everybody, there's a bunch of talks to get through. We'll move on, and if any questions pop up. Oh, actually, there is a question here from Brian Hamlin. Can LazZip ship in Debian after relicense?
It should be able to, yeah. I mean, the Debian team was,
it's Apache now.
Yeah, the Debian team was actually the ones who helped work through some of the licensing issues that LazZip had originally, and so with the code base relicense, it shouldn't be any sort of issue there at all.
Awesome. Well, thanks for that, Howard. Great talk. All right, next up we have Darren Wiens. Wait, did I pronounce that right? Is it Wiens?
Yes, Wiens.
All right, I should have known that, but I guess I didn't. So Darren's going to be talking about extension for representing video in Stack. Take it away.
Yeah, okay. Thanks. I'll assume that you can see my screen. Just yell at me if you can't.
Yep, no, we're good.
Yep, so I'm Darren Wiens, a geospatial developer at Spark Geo, and I'll be talking about a new Stack extension for video assets. Yeah, so I made this animation in Blender and I'm very proud of it, so don't tease me in Gitter. But the intent of the extension is to describe all different forms of overhead video assets, whether it comes from a drone or airplane or satellite. And in addition, it should support both a moving sensor. So if the actual vehicle is moving, should support that, and also support a moving and dynamic frame area. So it can, like the actual shape of the rectangular video being collected should be able to be described in the metadata. So most of the new properties are at the item level. So you can fill in the pixel dimensions, and then things like frame rate, frame count, and then video specific properties about video codec and whether there's no data letterbox areas around your video, and then some well-known sensor identification fields. I also include some suggestions for assets to include in your items. So you should always have a video asset that points to the actual video file, but then you should also have a frame geometry asset, which would be a GeoJSON polygon feature collection indicating the four corners in geographic coordinates of the video, as well as the frame center coordinates and the sensor coordinates. And if you combine all of those geographical assets together, you should be able to make sort of an animation like you see on the right here, where there's the sensor points are sort of orbiting around the rectangular video frame coordinates. I'll just warn you now that the next slide is a little bit crazy with 3 videos all playing at the same time. So if you're prone to motion sickness, you might just want to look away or just be aware. So here's an example of full motion video that this stack extension would apply to. So on the left is a seemingly aspatial video that's taken from a helicopter that follows a truck on a highway. There is embedded geographical metadata that's stored as in-band metadata right within the video file. And if we extract that in-band metadata out into GeoJSON features, we can then make like a UI on a web map that takes advantage of those frame corner coordinates, and also in the top example, I've locked the camera to the sensor coordinates, and in the bottom, the camera is free floating, but both of them are using the same UI in Mapbox, or you can do this in MapLibra or other UI. There is a full example on the SparkGeo blog that shows how you can actually extract the in-band metadata from certain video files. So you can find that at the URL here. And thanks to Brad Hards, who's provided a lot of useful feedback on the extension so far. I'm still accepting more feedback on the extension, so please go to the GitHub repo to provide that through either issues or discussions. Thanks to the Stack community for being so welcoming and helping me make my very first Stack extension contribution. And that's it. You can find the extension repo here and find me at Twitter to talk more about it.
Awesome. Thanks a lot, Darren. I do have some questions. I'm glad that you went through this because I hadn't really looked much at the extension, but we don't have time. And so either we'll have time at the end or I will comment on issues in the repo after this. But very cool.
We can talk more about it on Gitter or GitHub, wherever.
All right. Yeah, sounds good. Sounds good. All right. So next up, we've got Kurt Schweer from Google, who's going to be talking about Stack and Google Earth Engine. And I will give you a 1-minute warning because I was looking and we have actually quite a bit of talks that will no way fit into the hour, but we can at least try and keep as close as we can. So, all right, Kurt, it's all yours.
All right, let's see if I'm sharing my screen. I don't see anything. Did I do that wrong?
Yeah.
Let's try again.
Well, I can see.
There we go. All right. So today I want to talk about Stack and the Google Earth Engine. This is going to be just a taste of it, so it's pretty quick. And let's jump into it. So Earth Engine is a computation platform that takes all of your desires in code and parallelizes them and gives you back some results. It's pretty powerful. You can do lots of stuff with it, but computation needs data. If you don't have any data, your computation is probably not very exciting. So we have a public data catalog with a bunch of data. It's 50-ish petabytes, 600 data sets or so. Lots of cool data to work with. But if you can't find it, that's also a problem. So users need a way to see what's in there, and that's a catalog. So Earth Engine's had a catalog for a while. You can search for it and group things. You can say here, find things tagged ocean. And to give a quick history of Earth Engine, it's been around since 2009. About 2018 is when we had our first catalog available for users. It was launched. And in 2019, we had our first release of a Stack catalog. It was derived from an internal proto-based catalog. So it was basically just taking the protos, turning them into Stack, and then shoving them out on a bucket on the cloud. In December of last year, we turned things around so that we now have a directory of Stack content, and that stack content drives our catalog. And when we need protos, we derive them from stack. So we are now based on stack. There's a bit of a mapping problem that we had to go through. Earth Engine has a bunch of its types. Stack has catalogs, collections, and items. We ended up with all of the Earth Engine datasets mapped directly just to collections. So we have catalog files for people to use, but we don't use them. We just focus on each Earth Engine dataset is a stack catalog, or sorry, a stack collection. And we stick those files on a GCS bucket. And what those look like is a bunch of JSON. So here we've got an example. I don't expect you to read any of this, but basically it just shows you what's going on with the contents, and it's all the stuff you'd expect with Stack. We needed to be able to scale this and be able to edit it and maintain it. And so we wanted some sort of templating system to help make our lives easier. And there are lots of ways to slice this. You can write more JSON just directly. You can glue together stack catalogs across different organizations. You can do various generic templating approaches where you blend like Python and Django and Jinja or something like that. You can use databases and drive that with templating. You can then do things like take templating languages that are designed for JSON, where it might be a little bit closer together. You can choose your own adventure. You can mix and match lots of those different options. We decided to go with something called JSONit, which is very close to JSON. It's actually, you can take a JSON file, drop it in as a JSONit file, and it actually works just as is, or you can get a lot fancier. And the nice thing about JSON is it's a complete language. It's Turing complete for those of you who care. You can write functions, do all sorts of stuff, and at the other end comes your JSON that you would like to have. So here is
1 minute, Kurt.
Yep. Okay. We have some helper files that we can build. We can have things like your stack version. You can have your Earth Engine helper functions that say like your extent, things that you generally want. You can then have a catalog entry that's got a bunch of local variables you're going to fill into your template in the same file. Then you can use those to write out what you want to have in your stack. And then you can have out the other end from that template come out the stack JSON that you'd like. There's the rest of it. And from that, you have a stack catalog and you have the original Earth Engine catalog that most of our users use up till now. You have the best of both worlds. So that's my talk, and thank you for listening. The slides are available at the link below. And feel free to talk to us. We'd like more feedback on Stack and Earth Engine. Thank you.
Awesome. Thanks so much, Kurt. Yeah, Google Earth Engine, I use it as an example whenever I'm explaining Cloud-Native Geospatial, because it really was like the first Cloud-Native Geospatial infrastructure, really, that now all these other systems are essentially trying to do, doing the same thing with open source components. So yeah, really cool to see the use of Stack in there. So thanks again. Next up, we have Serhi. And I'm sorry if I pronounced that wrong, who's going to be talking about how Stack is sometimes too flexible. And I'm really interested in hearing this because I have had those same thoughts.
So I think we didn't actually get them upgraded to be a panelist. Serhi, could you?
Should we?
Yeah, you're just on the web client.
Yeah.
So
maybe I can join a bit later, trying to join with Windows PC.
Cool, sounds good. Yeah, you should be okay on that. Or alternatively, you can send slides and we can run them, but you should be able to just.
Thank you.
Awesome. We'll get you in the next one.
All right, so we'll go on to Mike Jeffy. Jeffy, are you ready?
I think I am. Just give me a second. I was waiting my turn here. So I need to make sure system preferences. Thought I had saved that.
Permissions, you'll have to restart on a Mac.
We'll see you in a minute.
Yeah, see me in a minute. It only shows up when you're added, so just as an FYI.
All right, so Vincent on GeoCubes and multi-dataset cogs. Are you ready?
I think that one might be a video.
Okay, is somebody going to be showing the video?
Yeah, OGC should.
Yep.
Yeah,
hey everybody, I'm taking care of the video right now.
Okay, great.
Hi everyone, today I represent you a new Cloud-Native Geospatial database called the GeoCube. It's a project under development by Airbus with the support of the CNES, and it started with the question: how to efficiently handle massive spatio-temporal data on distributed environments? The answer is the GeoCube, taking advantage of a modified COG file format capable of storing multiple datasets in one file. Let's get into the detail. The core of the GeoCube is a scalable service using GDAL as image processing library, a PostGIS database to index images that are stored in an object storage such as GCS, AWS, or local file system. In the ecosystem of the GeoCube, the ingesters are responsible for the massive ingestion of images from any public, commercial, or private catalogs. The ingesters are capable of process images using predefined or custom scripts and indexed the images in the GeoCube. Finally, an API is available to search images, optimize the database, ingest new images, and deliver align time series for massive and parallel workflows in standard languages such as Python or Golang, and parallel computing libraries such as Dask. In a nutshell, the GeoCube is a cloud-native geospatial database designed to be easily deployed for a variety of Earth observation projects. The GeoCube is sensor agnostic. It can process any raster format readable by GDAL in native resolution and prediction. But it is also able to reprocess the data to be optimized for the project itself. The GeoCube was designed to efficiently work with spatiotemporal data, delivering multimodal and aligned time series. It has the ability to reproject data on the fly, and it can use a special data format based on COG, optimized to deliver time series on the cloud. Finally, the GeoCube is a scalable and distributed solution that can be hosted locally or on a distributed platform to answer multiple needs from commercial application to more local R&D services. But what makes the GeoCube so efficient to deliver time series? Actually, the GeoCube can refactor the data to store several images in an optimized version of the COG. The COG is already an optimized GeoTIFF for the cloud, thanks to its internal organizations in the file. The data is split into tiles, and the indexes are grouped together. The multi-dataset COG, the new COG, goes one step further. It interlaces the full resolution blocks of several COGs, enabling a fast access to the whole time series of a given block. As in the COG, this interlacing preserves sparsity. Overviews can be stored spatially, contiguously, or interlaced, depending on the use case. This MuCOG respects the GeoTIFF standard that makes it readable by GDAL. The MuCOG is not mandatory, but it gives very good performance when it comes to reading a time series on a cloud storage. The MuCOG minimizes the latency by drastically decreasing the number of calls to the storage, in blue in the graphic. It reduces bandwidth usage by decreasing the volume of data read, and it results in a reduction of cost with a lower computing requirement. With a MuCOG, you can retrieve a block of 100 images in less than a second, which is 10 to 20 times faster than with COGs. 5 minutes is too short to convince you of the capabilities of the GeoCube, but the GeoCube is an open source project designed to be easily adapted to various environments, and even though it's still under development, the source code is already available on the Airbus Geo GitHub, so I invite you to have a try, share your comments, and get involved in the development. Thanks for your attention.
Great. Well, thank you to Vincent for that. That's very interesting. I've always dealt with time series in COGS as separate files. So I'm going to go back and visit this and take a look. It seems very cool. It looks like some really big performance gains there. Let's see. Do we have Serhi or Mike ready to present? I don't see Serhi on the list, so let's go with Mike Jeffy. Although, wait, I don't know if I see him either on here. All right, so Scott Simmons, are you ready?
I am certainly ready, no problem whatsoever.
Okay, great, let's go with you.
All right. Get my screen shown here, folks. And everything's good. Great. Thanks, everyone. So my name is Scott Simmons. I am the Chief Standards Officer at the OGC, which means really I help look after all those standards development activities in OGC. And I want to give a little bit of almost closing context for what we've talked about the last 2 days. And that is, where are all these activities that you've been talking about fitting within other OGC activities? And so it's really twofold. One is, how are we approaching these cloud-native topics? And then what are the specific action items we're undertaking? If you look at the way OGC right now operates, we're not just a standards development operation. OGC also performs exercises, experiments, practical research against those standards we developed, as well as defining requirements that may be useful for standardization through our innovation program. So the right side of this cycle shows that traditional development of standards that we follow. And on the left side, you can see how we might research against those standards after they're published, or define requirements that may be later topics for standardization. And so use cases and requirements that are going to drive standards and best practices can intersect both in the right direction and the left direction here in the middle of this cycle. We experiment on these use cases in context, and then we solve discrete problems. And so I'm going to approach these from both perspectives. We'll start with experimentation and go to the discrete work. So it is more than just formats. We've talked a lot about formats for the last couple of days, but the formats live in the context of an entire ecosystem. There is an ecosystem in the cloud. It's really important, and we need to find the formats, the practices, and the business operations that support that cloud. And so if we look at our innovation program activities to address the cloud in general, you can look at that fundamental work necessary to design and populate your cloud. Be that looking at the engineering formats that are necessary, how we might federate the cloud, so we might build and lay these things out. And you can see test beds going back several years working on this just general approach to the cloud. We then need to federate and further secure the cloud. And so we've looked at federation amongst similar and cross-cloud environments and securing these. We then also work on development of cloud-based platform. What are those entities, those software environments, and the supporting formats necessary so that you have a platform against which to work? And then finally, you got to make a business on the cloud, be that a nonprofit, for a government operation, or something from a commercial standpoint. How do we actually provision to the cloud, and how do we make money on it? Well, part of that work is realized with Stack. So Stack right now is fully compliant OGC API features standard implementation. It's been in deep collaboration with OGC since 2018 with our first hackathon to work on what was then Web Feature Service 3. And Stack continues to coordinate with our OGC API records. And the API from Stack is being proposed as a potential future OGC community standard. And when we talk about those formats, back to that discrete work that we're doing in the standardization program, there's a number of them in work in OGC right now. So ZAR, great discussion on ZAR yesterday and furthering today, is currently in the final steps of the OGC community standard adoption process. And so if our members agree to start that vote, it'll start in the next couple of weeks, and everything should be wrapped up in June. Once ZAR has been approved, we've been approached by the GeoZAR community to bring that in as perhaps a full OGC standard on the standards track, referencing ZAR as a community standard. COG, Cloud Optimized GeoTIFF, the draft specification based on the really excellent code and drivers that have been available for COG for some time now, was developed under Testbed 17 last year, and you can see a link here to an engineering report showing that draft specification. And now our GeoTIFF standards working group is working on the candidate standard in GitHub, and here's a link to see where COG is being developed now. GeoParquet is being incubated right now in the Open Geospatial GitHub repository for GeoParquet. GeoParquet may be a really suitable cloud-native vector format for all of us to use, and so potentially, depending on how this incubation goes and whether we get adequate implementations and confidence in our community, we can move that into a standardization track in OGC as well. And Howard, just a few minutes ago, gave you a great brief on cloud-optimized point clouds, and that was presented as well to the OGC members at the December 2021 member meeting. Lots more good content today. And LAS is already an OGC community standard, and depending on what our community wants, we've got a lot of members that are very interested in COP or Coptic or whatever we want to call it, that might also be suitable for an OGC community standard. And with that, thank you very much for your time, and I appreciate everyone's time today.
Thank you so much, Scott. That was great getting some context and vision from OGC on these efforts. All right, so next we're going to go to Jeffy, who is now a panelist. So you should be able to. There we go. Can you I can see your screen. I can't hear you if you're talking.
Unmuted now. I just need to share my screen. Screen 2. Presenter view. Can you see my screen? Oh, perfect.
Yep.
Are we good to go?
We don't see you. We want to see you.
Okay. Yeah. Oh, am I not visible? Let me get my.
Oh yeah, we don't have your audio.
Yeah, there we go. Sorry, a lot of buttons pressing at the same time. We're good to go, right?
Yeah.
Excellent. Good. Thank you. Sorry for the delays, technical issues. I'm Mike. I'm on the Open Data team at AWS. I'm going to be talking about building communities, leveraging cloud-native geospatial data on AWS. Just a warning, this is not a technical talk. More of a high-level overview, kind of from the perspective of a large organization that's working with an increasingly diverse set of data providers and actors who are leveraging large amounts of publicly available geospatial data on AWS. For my talk today, I just want to focus on 3 topics here. First, how the cloud is changing how we think about community geospatial data. Second, how we define what a successful community data set might look like. And third, what are some of the ways that companies like AWS can help drive further adoption of cloud data formats and data standards in the future. In thinking about this talk, about the work that we do, none of it, of course, would be possible without dedication of data providers that we work with, many of whom have presented talks in this event. And in this session, I'd be remiss if I didn't mention that I'm really standing on the shoulders of giants who helped shape this program to what it is today. Through this capacity, we work with orgs that want to democratize access to data by making it available on AWS. One of the ways we do this is through a data sponsorship program. It covers the cost of storage and egress throughout different AWS regions. We also leverage programs like the Amazon Sustainability Data Initiative, or ASDI, and Earth on AWS, which help to offset computational costs by providing cloud credits. From decades of best practices and shared experiences, we know that these siloed approaches to data management simply don't scale across large organizations. And one of the ways that the cloud has influenced behavior and approaches towards geospatial is by flipping the flow of how organizations work with data. In this traditional model, a user might download a subset of data to their own local compute environment. But as we shift towards a more cloud-centric model, we don't need to move data around. We can simply bring compute resources adjacent to the data. And I think by migrating towards cloud-native formats like CogXR and Parquet, these become much more efficient. And we could think about adding something like GeoParquet and leveraging Redshift in a serverless environment, so that really demonstrates the power of the cloud. So one of the topics we spend a lot of time thinking about in our program is how we define a successful data set. What we've learned over the years is this can generally be summarized by 3 criteria. First, can it be treated as a product? Are the data valuable in among themselves? Second, is the data in a format or structure that facilitates downstream analysis? And third, is there a community around it? So visualizing this, we generally see this pattern where usage continues to grow in its raw form as it becomes increasingly processed. Then at a certain point, it starts to decline because the data is almost too specialized for that broad usage. what part of the fun of this work is finding that sweet spot where a data set sort of reaches an optimal state in terms of its accessibility and credibility as a trusted source. So I just wanted to provide a couple of quick examples. We're all pretty familiar with the Landsat Commercial Cloud Data Access Program. The USGS put their entire archive of Collection 2 Landsat imagery on AWS from level 1 to level 3 using cloud optimized GeoTIFF with stacked metadata. Howard, of course, talked about Copic. I just wanted to quickly acknowledge that this has been a great data source for the community. We continue to use it and explore greater visibility of this. And also Daylight, which some of you may not know, it is a complete, it's a set of, it's a distribution of OpenStreetMap data that has passed a QA and validation process to remove some of the vandalism. Anyone can download the Parquet files and load it directly into Athena to start querying Daylight data. So it's a really powerful capability. And then you could, of course, visualize the data the same way that you usually do in your own desktop environment, QGIS. And finally, I just wanted to mention that we're constantly evaluating our program to look for new approaches. These URLs are examples where we've added tags like stack, SAR, COG to specify which data sets these are relevant for. One can imagine something like GeoParquet. If you have ideas for hosting those data sets, I'm definitely all ears. Please reach out to me at my email at jeffymj@amazon.com, and I'd love to hear your thoughts on this. I think that's 5 minutes exactly.
Awesome, nice work, Mike. Open data is happy data, that's for sure. I subscribe to that. Nice talk. Great to hear what AWS is doing. Let's see. Okay, I don't see Serhi on the panelist list. So Matt Barra from Esri, are you here?
Hello. Yep, I'm here. Although I don't have a share button on my panel.
Okay, that should be taken care of shortly.
There we go. Okay. All right. You guys seeing my kind of front page for a brief?
No. There we go.
Maybe using I3S web optimized format. Great. Okay. Yep. Great. Well, good afternoon, everybody, and thanks for having me kind of as part of this session. My name is Matt Barra, and I'm a lead solution engineer at Esri. And today I want to talk for just a few minutes about index 3D scene layers. And I'd like to demonstrate how I think they can be kind of part of a larger sort of cloud native solution. If you've never heard of I3S files before, you may actually know them by their more common name, which can be the scene layer package. They've got an SLPK file extension, and they're designed really to rapidly stream and sort of distribute large amounts of 3D content, specifically while working through the web, mobile, and the cloud. Although the files can be consumed locally, everything is based on JSON, REST, and modern web standards, which makes it really easy to handle and parse and render by web and mobile clients. Esri's been working on the I3S standard since 2015, and back in 2017, it was accepted as an OGC kind of community standard at version 1.0. And this past December, OGC approved the latest release version, which is 1.2. So what kind of data can we display with I3S files? Well, initially the spec was introduced with 2 layer options, right? There's the 3D objects and 3D points. And 3D objects include things like building exteriors and GIS data, as well as 3D models in various formats, while 3D points includes GIS point data like trees and signs and other features that can be tied to a sort of a single coordinate. Since then, 3 other layer types have been added to the spec as well. The first is integrated mesh, and it was added back in 2016. And obviously it lets users display skin terrain with images from satellites and drones. Then next, the spec added point clouds, so we can work with LiDAR. And the point cloud spec supports caching attributes like RGB intensity and more, so that client applications can update the symbology as well as query the point information. And then the final type, well, building scene layers. And this was designed to be sort of part of BIM workflows. It includes architectural and structural details like walls, windows, and assets for facilities. So how do I3S files fit into a cloud native solution? And to answer that, I'd like to do a super quick demo. All right, so what I'm doing here is I'm actually running sort of a local web server on my machine. And I've got this folder that contains, a few I3S files. And by just using sort of a small bit of Python, I'm able to dynamically generate the page you see on the left side, which allows me to query, analyze, and display kind of each one of these files. Then the map on the left side of each row, I can move around, I can query and sort of work with the information that I've got inside of it. And then on the right, you can actually see the metadata that's kind of being served out, that's contained in the file. And in this instance, is being served out and displayed kind of in the stream server format. And I want to emphasize that, since this is being read directly, it's not using ArcGIS Enterprise, ArcGIS Online as an intermediary to load the data. Because of this, if I grab another I3S file and I paste it into my folder, and then I sort of restart my web server and refresh my page, we're going to see that our new data set is sort of automatically loaded here inside of this page. And I can now interact with this data set just like I could the other ones as well. So next I want to do is actually show you sort of an example of the point cloud spec. This is a coastal scene in New Jersey. It has over 1.1 billion points, but it's still, extremely fast as I kind of move and sort of pan around the frame. And as I mentioned before, since the point cloud includes all the attributes, they can very quickly change the visualization from something based on, LES classification or elevation or just intensity values themselves.
Matt, 1 minute.
Right. So in the end, what are the major benefits to using I3S files in a cloud-native format? To me, there's really three main things. First, it supports a wide range of 3D geometry types. Second, it was designed with streaming in mind. And third, it's an OGC standard. So if you're interested in learning more about I3S, go ahead and check out the OGC page about it, or check out the Esri GitHub page as well. Thanks. And if you have any questions, I'll be on Gitter after this.
Great, thanks, Matt. Yeah, really cool seeing all this 3D stuff going on. Okay, so we're rapidly running out of time, but actually these talks all added up to more than an hour anyway, so I don't think there's any way we would have been able to succeed. So let's see, where can we go with? I still don't see Sergio on here, so Quirkus, are you ready? And did I pronounce your name properly?
Yeah, yep. Hello. Get the webcam on here. Okay, share screen.
Okay, it's all you.
Okay, you seeing my screen?
I did, but now it went away. And now I see it again.
It's okay. Are you seeing it now? The presenter or the full? Okay, great. Thanks. My name is Quirkus Hamlin. I'm a geospatial analytics engineer at Airspace Link. And today I want to share how we're using cloud-optimized geotiffs and other cloud infrastructure to support scalable on-demand drone solutions. So first, a word on Airspace Link and why we're doing what we're doing. Every few decades, over the past 150 years, there's been a major inflection point in the infrastructure industry, whether that's been vehicles, telephone, or highways. It's really changed how we do business and live our lives. We see drones as this next inflection point and a way to fuel human progress and good, whether that be delivering packages and taking cars off the road to reduce carbon emissions, or delivering organ transplants more efficiently. Today, our mission is to integrate drones safely into the federal airspace and communities at scale. I'm hearing someone else in the background here.
Okay, I think
I got it.
Okay, thanks. So we have a variety of tools to do this, things that help both pilots, local governments, and the federal government. But today I want to share what we're doing for advanced solutions using our geospatial analytics. So we're doing this on ArcGIS Online and an Azure Stack, making use of Azure functions, the serverless computing similar to AWS Lambda. And we're doing this in Python, Go, and JavaScript with a variety of open source geospatial tools. Since this is Cloud Native Day, I want to focus on what we're doing with COGS in particular. One thing that we see differentiating us from others in the market is our commitment to data sets and particularly geospatial data. We've aggregated a repository of over 60 data sets in our AirHub Insights lab, And these are ranging from cogs stored on Azure and vectors stored in ArcGIS Online. One thing that is an issue sometimes with data and having so much data is how can you get it to all talk to each other and be harmonized, be able to use it in analytics. And that's where we've turned to H3, which is Uber's hex grid available at multiple resolutions. So we're able to, on the fly, aggregate all of this data and have it in a format that we can do things like risk analysis and routing to minimize risks or site suitability. I would do a demo, but with the Lightning format, I was just afraid of tempting fate with technology. So these both took just a few seconds to aggregate, and there aren't any hexagons stored anywhere. It's all on the fly, pulling from those data sets in the cloud. The other tool that I wanted to talk about that I've recently developed is our Elevation API, and this relies heavily on cogs and how easy they are to query at scale. So elevation and altitude are a tricky thing in the drone industry. Drones are regulated based on their height above ground level, which means both knowing what ground level is and agreeing on it with both drones and other aircraft and models. So we've turned to having DMs stored as cogs and are able to retrieve those and do the necessary datum conversions via raster.io in an Azure function. So whether the measurement is coming from a GPS system or a digital elevation model, and soon we'll have barometric pressure, we're able to convert it and do this on the fly. So this can be used for things like deconfliction, whether that's between drones and other drones or drones and airplanes, as well as compliance monitoring. So continuously making sure that drones are not flying too high as this information comes back and forth. The other thing that we're doing with this is route planning, a way to both use 2- and 3-dimensional visualizations to help operators know what terrain challenges they might run into and what they need to do to stay compliant with regulations. And so as that ground level changes, the altitude you need to fly also changes. Cogs are key to this. The ability to query small pieces of large rasters in the cloud environment allows us to do this in a telemetry format. So drones can continuously just ping this service and we return that value and conversion in less than a second to do this. That is what I wanted to share with you all today. Thank you. I've really enjoyed this event and I'm excited to see what we can also do with things like XAR and GeoParquet. Thank you.
Thanks so much, Quarkus. That was great. Yeah, I mean, I'm a back-end developer, so I'm usually interested in like the details of like the formats and all that. But seeing these end-to-end applications, like it's like, oh, like this is how this stuff is actually used, which is really, really cool to see. So thank you. Okay, do we have? Let's see, Abdul from Dewberry. It looks like you've been made presenter. Can you hear us?
Can you guys hear me?
Yep, we can hear you now.
I provided the presentation, like recorded video.
Okay, there's a recorded video. Okay. So do we have that? Do we have that, Jonathan?
Let me pop over and take care of that right now.
Okay. If you need a minute, we can go to the next person.
Nope, we have it.
All right. Awesome. Thanks.
Hello, everyone. My name is Abdul Rahim Siddiqui, and I am a scientific programmer for water resources and GIS at Dewberry. I am also a QGIS enthusiast. I have developed 3 QGIS plugins. In today's talk, I will be demoing on how to use cogs in QGIS and what they can do for you. In particular, I will be using a land cover dataset created by Esri partnering with Microsoft AI for Earth that is stored as cogs, and cogs here means cloud optimized geodifs. The server is published for general public as an image server, but since that is an Esri specific format, QGIS cannot load it. And even if it would have loaded that, it would have presented that as an image. And if you wanted to perform any geospatial operations on an image, that would not have been possible. Though the good news here is that the QGIS can load cloud optimized geotiffs, and the source data for this land cover data set is stored as cloud optimized geotiffs on the cloud. Now to load any cloud optimized geotiff in QGIS, all you need to have is the URL of the cog, and then you can go to the layer, add layer, add raster layer, and then protocol, AWS. If it is stored on AWS S3, then you can just provide a bucket name and the object key, and you can click add, and the QGIS will display the raster for you. The problem here is though that the data set is global and it is stored as 701 cogs. So I do not know what is the URL for the raster that is stored for, let's say, this area. Luckily, Esri has provided a grid that tells which raster is corresponding to which area. I have it downloaded here and I will add it. You can see there are multiple bounding boxes here, and each of them has a file name attached to it. We will use this file name and attach it with the URL of the bucket where this whole data set is stored. And then after that, what we can do is we can utilize a feature in QGIS called QGIS action, which is something that can happen once you click a feature. So a QGIS user, Thomas Gracier, has added the QGIS actions to this particular layer, and let's view them. So you can see when I go on the layer, I go to actions, I can see there is an action added here. What this action does is that it adds to this URL where the whole data is stored the file name based on where I click on the layer, so which feature I click on, and then it tells the QGIS to load that path or that cog to our canvas. So now let's see this action by demoing. So I'm on that layer. I would go here and click add geotiff and click on any one of the box. You can see that it's taking a minute because it's loading from the cloud. And we can see that we have the raster data set for this area. Let's add a couple of more areas. Okay, so once we zoom in, we can see that we are getting the highest resolution possible and we are not losing any resolution. Thus, using the power of two open source geospatial tools, QGIS and COGS, we are able to download and visualize the land cover of any area on the globe. Thanks everyone for watching this presentation. I have published the presentation as a Medium article as well. You can search it on the Medium website. The article contains link to the layer that I had used in my demo. You can download it and load it in a QGIS project. It will appear same as it appeared for me and would have the actions already added to it. All you would need to do is go here and click this add geotiff button and click on any area, and you should see a cloud optimized geotiff loaded in your QGIS project. Thank you.
Great. Well, thank you, Abdul. Of course, we don't have time for questions, but yeah, thanks for your contributions. This looks really cool. Okay, so we're going to go to Serhi is on now. And then we'll go to Jerome. So we have two talks left. All right, perfect. I can see your slides. Or is Chris running them?
Can you hear me now?
Yes, we can hear you.
Cool. Let's start. So, my name is He, and I am Geospatial Python developer at Up42. My topic is defining stack in an uncompromising way. Stack is a young format on its way of constant improvement. It's pretty flexible, and flexibility is essential for handling this variety of data from different providers. I want to give you an idea why making it stricter can improve its overall experience with Stack without losing any functionality. As its website says, the goal is to all providers to expose their data so that the new code doesn't need to be written whenever a new data set or API is released. While it's true within one API, but if you have two different APIs that follow same version of Stack, it doesn't guarantee that they're interchangeable. Usually you need some tiny tweaks to match each of them. One of the example is polygon geometry from search response. I assume that each stack item is an image, so we can narrow generic type of geometry to more specific polygon. It feels like obvious thing, but I face a provider with multi-polygons for polygon. Working with multi-polygon is not a big deal, but it's a tiny tweak that you need to be aware of. Another example is the pagination. Stack doesn't define the only way to set up the pagination for it. And as it says, implementers may use any names or fields of their choosing. Pagination can be provided solely through header values, solely through body values, or through some combination, something that you need to be aware of. And defining these tiny things in specification will lead to more precise models in different programming languages. And some potential errors can be found on schemas validation stage, such things as setting non-negative integer types for things like limit, number page, etc., or something like that start date should be before the end date. I want to emphasize that I'm not going to tell which way is better. It's topics for holy wars within Stack community. In the end, it really doesn't matter. What matters is having the robust standard that sets developers free from interface details and let them focus on more important stuff, such as business logic. And I want to end my presentation with a good example of strict format from Python community. PEP8 is official standard for formatting the code of Python. But according to GitHub, it's not the most popular one despite its officiality. The leader is Black, the uncompromising code formatter. It even dictates one and the only one way to write the code. And its popularity may tell us that having strict format, maybe it's a good practice. Thank you.
Thank you so much, Serhii. Yes, it's great seeing that sort of feedback with your experience in using Stack. I've run into the case of multi-polygons for geometries when they're actually just polygons. Although I would note that when you reach the anti-meridian, one way to handle that is by having a multi-polygon on both sides. So I don't know the best way to handle that, but thanks for your thoughts on all of that. Okay, so finally we have Jerome, and I believe that Chris is going to be running the slides. And we should have Jerome as a panelist.
I don't know that he'll get to be a panelist. He's on the web, but I think we can give him audio rights. And if someone could switch the screen to me.
I'm in the process of looking for him in the attendee list right now. I don't see him.
He's there, Jerome St. Louis. J with an accent.
There we go.
Hi, can you hear me?
Yes.
Yes,
Great.
we can.
Thank you for having me.
Let me get the slides up. I think they need to give me presentation rights. I see it. Cool. Is that working?
Great. Thanks. So I'm Jérôme Saint-Louis from HRA, and I'm also the co-chair of the OGC API tiles and the OGC API coverages standard working groups. Next slide, please. And basically today I would like to talk to you about the relationship between cloud-native formats and how they can fit within the OGC API framework or family of standards and draft specifications. So I see two ways that the two can work together. So on one end, the cloud native formats like Cloud Optimized GeoTIFF, GeoParquet, and Copic and ZAR, they can be the backend for what in the OGC API common is called a collection of data. So basically, yeah, it can be a efficient storage either for locally on where the API is located, or it could also be a way to bring in data and offer additional functionality on top of data that's available from affordable cloud object storage. So that's one aspect. The other aspect is those cloud native formats could actually also be the output of these OGC API specifications. So for example, in the OGC API data delivery specifications like coverages, maps, and features, we could have conformance classes that say that you can negotiate cloud optimized GeoTIFF or ZAR, for example, for the /coverage endpoint, and those endpoint could support all the HTTP range requests, so you can have efficient access to your data. Next slide, please. So what's the advantages of this? So from the backend perspective, what these cloud optimized formats provide is they provide the ability to the organization of your data to do efficient subsetting and downsampling so that you can focus on a specific area of interest, and which usually also corresponds to a specific resolution of interest. So that can power these conformance classes that we have in the OGC API specifications. For example, OGC API tiles is really all about that, about overviews and tiles following the 2D tile matrix set standard. And in OGC API coverages, there are conformance classes for downsampling, the scaling conformance class. There's also a subsetting conformance class. In OGC API maps, we have the width and height parameters to control the output resolution, and also a way to subset the data using the bbox or subset query parameter. And OGC API features, there is a planned simplification extension, which will allow similar functionality for vector data. So basically, this provides an organized data storage to make these possible. Because if your data is not organized this way, it can be very computationally. It doesn't provide the efficiency that these conformance classes are supposed to give. So to be able to have these in the backend really enable these capabilities and make the data a lot more usable for large and high resolution data. Then for the output format, it's simply that you can use the usual approach to accessing cloud native formats, but the backend can actually be an OGC API. So the clients don't need to know anything about the OGC API specification, really. They can just directly access the items, the coverage, or the maps endpoint the same way they would access any other deployment of those cloud native formats. Next slide, please. So what do we need from the specifications perspective to make this possible? For the backend, there's nothing to do at all because it all happens behind the scenes. So these cloud native formats just make all this possible. They make it easy to implement those efficient ways to access the specific resolution and area of interest. And for the cloud native formats output, I think what we need in the OGC API specification is to define specific conformance classes for these cloud native formats. Another thing that might also be useful is to advertise the particular tiling scheme that was used to generate those cloud optimized formats. For example, if the tiles and overviews follow a tile matrix set, that could be advertised. And this could be done outside of the format itself, for example, in the collection description endpoint. Next slide, please. So that's pretty much all I had to discuss. So thank you very much. If you have any questions, feel free to reach out to me by email, or I'm also on the Gitter. And there is one related discussion, which was specifically on the topic of Cloud Optimized GeoTIFF on the OGC API coverages. That's issue 93. But I think the same idea about making these output available applies to ZAR and to the Copic and even to GeoPark. And also there's in the testbed 17 Geodata Cube API, we did discuss this, the output as cloud native format. So please have a look at this testbed 17 Geodata Cube API engineering report. Thank you.
Thanks so much, Jerome. Yeah, and with that, that's a wrap. We really want to thank all of the sponsors, Cardo, Planet, and Development Seed, as well as the bronze sponsors or whatever they might be called. I don't know, did they have medals for them?
No medal colors this time. They had names. I think those were the supporters.
Supporters. Yeah, so thanks all. And also thanks to all the presenters and attendees. This has really been a great turnout. I was really, this is a great job, Chris, on organizing this, and thank you to OGC and Nadine. I think this has been a great event. And like I said before, I'm looking forward to going back and revisiting some of the videos and seeing some of the ones that I hadn't seen. Did you have any closing remarks, Chris?
Yeah, just OGC, I want to thank especially Jonathan and Greg and Pavia, yeah, sorry, who have been doing all the behind the scenes stuff to make this all happen. And thank you, Matt, for moderating this last session and giving a great stack overview. That was, yeah, I think the overviews were really great. And yeah, thanks everybody for showing up. And yeah, this has been super awesome to see. And there's videos are starting to get posted on the YouTube channel, and I think we'll hope to get most of them up soon. And yeah, share them broadly with everybody who couldn't make it. But yeah, thanks very much. And with that, we'll end.
Bye.
Thank you all very much.
Thank you, everyone.